Hello everyone, thanks for subscribing my YouTube channel. Today we are going to learn about CCNP Core Enterprise Core. This is one of the core paper and there are two benefits. First of all, if you are looking for your CCNP certification, so this paper is must. You have to pass this paper and then you can go and choose any of the elective paper. I'm going to explain this in few minutes so you will understand the new certification track related to CCNP. That's the benefit number one. The benefit number two is now Cisco has removed CCI written. So if you are looking for CCI in enterprise, you have to pass this CCNP in Encore. So anyways, it is very important if you are looking for professional level certification, it's very important and this is a stage number one. If you are looking for CCI certification, this is again very important and this is a stage number one. So please continue, complete this video and gain the knowledge related to CCNP Encore. So what is the syllabus? Here you can see that syllabus that is covering architecture, virtualization, infrastructure, network assurance, security, and automation. Actually, the syllabus is quite robust, and in this training course, what I try to do that I have covered each and every single topic in greater detail. So for example, if we are talking about the architecture, so I have covered architecture related to the campus area network, then architecture related to WLC design, then SD-WAN, small piece of SDA, software defined access as well. QS you'll find in detail, and whatever topics that you're seeing here in the list, each and every topic point by point I have covered in this curriculum. Then virtualization also has been covered in detail. Even I have gone beyond this syllabus and then I have added virtualization that is core for VMware networking or for VMware. So that things also I have added in these sections. Then infrastructure. So if you go and check this entire syllabus, you'll find that the core of this CCNP core itself is the infrastructure module. So in this module, you'll find that you have to know about layer 2 technology, layer 3 technology, wireless, and then IP services. And this is actually one of the lengthiest uh, module we have in this particular curriculum. This is very important where you are learning the layer 2, layer 3 wireless and IP services. So that will again add the tools inside your core fundamental of the networking technology. Then we have the network assurance. Inside that, you have to configure the basic troubleshooting and monitoring stuffs. Then finally, we have the security topic. Again, this security topic is as it is that we have in the old CCNP as well, I can say. So you have to know about the ACLs, the COP, some of the wireless security stuffs, some of the upcoming security stuffs as well. And then finally, we have 15% weightage for automation. We should know and understand say Python, JSON, APIs, how the APIs are working, Cisco EEM scripts, then finally the Chef, Puppet, Ansible, and Salt Stack. So in general, you will find this syllabus is quite robust and even challenging as well, because not only we have to know the existing or you can say the old stuff as well, but you have to understand the new stuffs as well. And Cisco has taken care of this thing in the mind that maybe tomorrow you have to migrate your WAN to the SD-WAN or your LAN to SD access or SDA. So all these things has been taken care in this CCNP enterprise syllabus. Either it's a CCNP curriculum or it's a CCI curriculum. Each and everything has been taken care whenever Cisco has formed this or drafted this syllabus. They have taken care of this thing in the mind that there are cases that you are supporting the existing network, or there are cases that you are doing the migration, or there may be case that you are supporting the brand new upgraded SD-WAN or SDA network. I'm going to walk you through the CCNP Enterprise certification, and we'll see that what are the changes that Cisco is putting from this coming Feb inside the certification. There is complete strategy change you can see inside the CCNP Enterprise. We know that Cisco certifications are always valuable. You will get much salary hike, means compared to other certifications in the market. You will get much more reputation, and they are highly valuable certifications. We have complete sort of certification, means different type of certification like associate, professional, and expert. And as per your certification, even you can negotiate with the companies in terms of salary and other aspects. So they, as per your certification, they will think that you have the right knowledge, skill. You are very skilled in the IT. You are a skilled IT professional, and then you can go and ask for the salary because you are able to take the responsibility. So that's the reason the company will pay you. Here you can see that 99% of organization use certification to make hiring decision, because these certifications are structured in a way that they are going to test your different level of skills. So for example, if you see the old certification stack that we have, means now it's 28th of Feb. So now this become old, and now in the next slide I'll show you the new that will be available from 24th of Feb. So this old certification, you can see most of the people at the moment, at this point of time, they have we have associate level certification, professional level, then the expert level, and different type of technologies are there. So for example, routing, switching, security, service provider, wireless, others. Now this has been changed in this. So now you can see that certification has been simplified, but on other hand, that will become much more focused. So now this CCNA, that is the associate level certification, this is the basic for all the professionals, and then again you can go for the expert. But CCNA become basic for the professional level. Now this CCNA will serve the purpose for enterprise, service provider, data center, collaboration, and security. And parallelly, you may have the expert level certifications in that particular domain. Now again, Cisco has other certification as well, and that is the DevOps. And their track is different, but you can see that 95% or maybe 90% of things relates with associate CCNA, and then the professional, and then the expert. Now here you can see that if you've done your CCI, so you know that inside CCI, you initially, means before this program, you have the theory and the lab, and that is 8 hour, um, very difficult type of exam. And there you must need very high percentage, for example 75 to 80% of marks in all the sections to pass your CCI. Now, comparative to CCI, CCNP exam is also very highly skilled type of things that they are going to ask you. It means they are going to check your depth knowledge inside that particular domain. Here you can see that you have the enterprise core, security core, service provider core, collaboration, data center core. So things has been grouped strategically inside different type of core. So you have one foundation, you have one core, and then you can choose the uh, expert level, or more precisely the specialist level. So you have the core. First of all, you can see that you have the CCNA, and then you have core in these, say for example 5 domain. So you need core knowledge, and then you can go and get your CCNP, and then you can go and get your CCI. So from your core, now you can see that you don't have written and a lab exam, although your core, after your core you can go and write your lab exam. Okay, so choose between two lab exam inside this enterprise core. And what are two lab exam? If I go back, you can see that you have enterprise infrastructure, you have enterprise wireless, correct? So like that you have to choose. Now if you are in the security, choose your concentration, means you do your core, choose your concentration, and then take the lab. Like that you have all the tracks. You can see that from the slide, it's very much uh, clear and what to do at what point of time. Again, here you can see that you have enterprise, security, service provider. For everything, you have core exam, and you can go and have your CCNP. Means CCNP has two paper. One is core and one is the concentration, or one is the focused exam, and then you can go and write the lab exam. So for example, for enterprise, you have enterprise lab related to wireless and the CCI infrastructure, where you have different things like SD-WAN and SDA. Those new things are also added. All right, so now you can see that today means, again, today is 27th or 28th. So now we are in this certification track. So 24th of February, we have enterprise core that is mandatory, and then you can choose one. So either it's advanced routing or SD-WAN or enterprise wireless or wireless implement. Like that, you can choose the certifications. Summary, that Cisco has tried to reduce the number of amount of certificates, and it has been focused and grouped well logically inside single technology, or inside single group. And it's still um, and even they have removed the CCI written as well. So you can do your CCNP core and you can write your CCI. You can do your CCNP core and then you can go and focus on any of the specialized exam, like say for example SD-WAN or enterprise design, etc. All right, so this is the track. Everyone has a home, everyone gains, everyone maintains their certification, everyone awarded badges. So obviously by the end of day, once you complete the track, you can see that you have different type of badges. You have a specialist, then you have CCNA, then you have CCNP, and then you have CCIE. So you can start your journey, and then you can slowly move your career from a specialist to the expert, and that's the goal. And once you complete your CCNA up to CCI in one particular domain, then you can move to the other domain. Okay, so there is a wealth of knowledge available, and if you want to gain it, if you want to become expert, go to one technology, complete it, and then move to other technology. That will be the strategy. This particular course is focused on CCNP Enterprise, and once we have one of the core topic, then we'll go and check the SD-WAN. Alternatively, we can go and check the other stuffs as well, like design, advanced routing, enterprise automation. But at this point of time, we can check CCNP Enterprise and the SD-WAN, because the combination of enterprise and SD-WAN will give you weightage. At the moment, SD-WAN is very hot in the market. It's very demanding, and if we combine like these two, core plus SD-WAN, so market value will be very good. What are the core skills you need? We'll see that we have complete syllabus. You can go and check. So now this was the past, where you have route switch, shoot arc, and other stuffs. Now in future, now present, I better tell this. This is the present. So you have enterprise core batch. You have a specialist. Uh, then you have the advanced routing batch. Wireless batch means for individual exam also you will get that exam certificate, but better that will go and club. So CCNP Enterprise with any of the four, correct? All right, so now here again you can see the summary that you have. Like if you want CCNP Enterprise, you do the core, and you can do the advanced, or you can do the core, you can do wireless, any of these two. You can do the core and then you can do the design. And here you can see that CCNP enterprise, enterprise, enterprise. Okay, and just try to tell that how it is equivalent to CCNP RNS, CCNP wireless, CCNP DP. So suppose if you want to do CCNP DP, you do the core and then design, and you are the DP. If you want to do CCNP in wireless, the do all these three, and then you are CCNP in wireless. If you want to do CCNP RNS, do these two, and you are CCNP RNS. If you want to be CCNP in SD-WAN, you do core and SD-WAN, and you are the CCNP in SD-WAN. All right, so this was the certification changes, and I hope that you understand that what type of changes, what certifications we have to obtain our new CCNP, and from there we can go and prepare for CCIE as well. Hi everyone, welcome to CCNP Enterprise Core course. This course is divided into 6 different parts. Here you can see, starting from architecture, virtualization, infra, network assurance, security, and automation. You'll find the detail of these topics and the subtopics in this particular link. I hope this course will be informative and you'll gain new knowledge from this course. Thank you. Let us start with 1.0. That is the architecture, and what are the things we have to learn in this? We need to understand the design principle, the resiliency, the scalability, the redundancy, the WAN deployment options, etc. So here you can see that you have a long list actually, starting from 1.1, then 1.2, 3, and then 4, 5, 6, 7, up to 1.1 to 1.7 you have. Now here you can see that inside 1.4, you have to understand the SD-WAN design principle. 1.5, you have to understand about DNA or SD access design principle. 1.5, you have this QoS both in wired and wireless. And then 1.7 is taken from the old curriculum. Even in the this 1.6, that is the QoS, that is also taken from the old curriculum. So it's again the mix of the old CCNP plus whatever new technologies we have, and why we have such type of mix, that I will explain you in the upcoming maybe third or maybe fourth slide. You'll understand that. Now let's cover point number 1.1a up to B. And what is the agenda for that? So you have to understand the enterprise network design, such as tier 2, 3, what is fabric, fabric capacity planning, etc. And then the high availability and redundancy, like first of redundancy protocol and SSO. We'll see that, because although this is only point 1.1a and b, but we have multiple videos to cover these topics, because again this is a big topic. So let's try to understand this 1.1, and let's try to figure out that what type of design principle we have and why we have. Say once we understand that why we are using this, that will solve our purpose. So we should understand that why we need this. Now let's see this WAN transport technologies. In this slide, you can see that the evolution of the architecture and design principle. So early network, we have the fix and the bridge network, maybe 35 years back when Cisco has invented routers and again the switches, and they try to connect different type of network. Here you can see that actually if we go from back behind that, say if we go and check the ARPANET and their principle and the TCP/IP discovery and their evolution, you can see that when the protocol first invented, and then again when Cisco come into the picture and they have uh, revolutionized the uh, complete network domain or the industry. So here you can see that from 1990, when we have the multi-protocol and the business support model for IT. And at that time, we have various protocol like OSPF, BGP. Those are the commercial protocol. Say, still in some of the places, you can see that we are using RIP RIP. This again the old traditional methodology. Even we are using frame relay. Still, some places we are using frame relay or X.25, etc. But now we are moving. So now if you see the journey from 1990 to 2000, where we have mission critical network, where we are supporting real-time traffic, we don't have even 1 minute of downtime, etc., etc. Means it's a highly mission critical network. And uh, if we are dealing for those topologies, how we are going to build those topologies. And again, if you move from 2000 to 2020, now you can see that the evolution of SDN, and companies they are start deploying the SDN, either it's SD-WAN or LAN or campus automation or DNA, etc. So now is this the complete movement. Now again, this is the movement of network. So if you know the architecture principle, that what we are using in mid 90s or 2000 and now what we are going to use in 2020, actually each and everything has covered in this core. So we can start from our fundamental BGP, OSPF or other routing protocols, and then we can move and check that what type of protocol has been used inside SD-WAN or DNA. So for example, BGP, OSPF we are using here in the existing network, and OMP and TLOC we can use in SD-WAN, or Lisp we can use in DNA, etc. Okay, so we should have the clear picture. And if you're doing the migration from your existing network to the upcoming network, so if you know your existing network, if you know the upcoming technology and network, then only you can do the migration, and uh, a less number of issues will be there. All right, so this will be your summary slide. What we are moving, what we have at this point of time, and what we need in the upcoming network cycle. I mean, when we are refreshing the cycle or when we are migrating the cycle, and what type of challenges we have here. You can see that's again the uh, a small thing. Means everywhere in all the places you will find the same type of challenges. Means the challenges are not as small, but in terms of gathering the facts, that's the common. So what are the common factors you want to improve, or what are the challenges you have that you don't want inside the SD-WAN or in the next gen network? So we know that scalability is one of the biggest issue. Means you can't scale. So you have this scalability, and we can discuss a lot and lot about the scalability. Now when we are talking about scalability, the scalability not only in terms of your network or how many devices you have, but scalability in terms of routing capability, your IPsec capability, or even you can go and do some sort of deployment over the cloud. So scalability plus cloud integration means you can mix these things and you can think all in a single bucket. Then how you are going to integrate with IoT, Internet of Things, because again this is a big huge topic. And we know that Cisco DNA, Digital Network Architecture, or ST Access, they have the capability to understand. Even Cisco is making the IoT related products as well. So we have the chance that we can integrate IoT devices inside the enterprise network. Then what is the fast IT changes? What is the next? Can you do the automation programming? Do you have single pane of glass from where you are managing all the devices? Okay. So if I go and summarize these topics, again, I told you that all these problem and the complexity that we have, they are common at this point of time. And if you see the existing network is still we are using the access distribution and core routing layers or L3 layers. So we have some sort of C and then P and then P and then the network. They are divided into multiple routing instances or forwarding virtual routing forwarding instances, etc., etc. So you can go and support the network level virtualization as well. So what I will do, let me quickly mark here that what is the common issue we have in the existing network. I will not add cost at the moment, leave this. We can discuss cost later on with this cost aspect, because you may find that cost is also one of the driver to make or to do the refresh in the network. So what we want is scalability, and this scalability we want in routing and we want in IPsec as well. And that's why we have DMVPN versus new SD-WAN IPsec or new SDN IPsec. Second thing what we want as a network, that we want integrated security. So at the moment I bring up my controllers, control plane, data plane, etc., I should have one solid, common, unified, secure fabric. Correct? So that's why this is also very, very important. Thirdly, what you want, we want that the overall cloud integration means now it is to, again, this have some cost effect. So companies, they don't want to go to the central hub or data center and then they want to go and use either DIA, direct internet access, or direct cloud access. Rather, from branch they want to do local breakout, and then they don't want to use the resources hosted over internet or the cloud. So that's again important in cloud integration. Now these things you have. Apart from that, one very important thing here, I will add it, that is possible in the existing network as well. In the SDN solution, it's by default. That is the segmentation. So once you do the segmentation, the scalability, security, cloud integration, and segmentation. Apart from that, you want other features like you should have full visibility. Then you want monitoring. You want single pane of glass from where you want to do all these monitoring. You want solid reporting. You want easy way to do the troubleshooting, etc., etc. Correct? So these are the things and these are the terms we have, and we should consider these things inside the architecture principle. So let's just stop here, and in next section, uh, let's continue the same architecture principle, and I will add some more valuable point in the upcoming sessions. Let us continue our discussion and understand more that what we have discussed earlier. So we have discussed that yes, we have different technology, means in terms of evolution of network. So we can check the 1990 network, then 2000, then 2010, and then 2020 and coming forward. So what is the major change and how we are going to reduce the complexity in terms of design and deployment? That actually it's very interesting. So here you can see that with the evolution of MPLS, and when the MPLS network it's start gaining the popularity, at that point of time you can see that how you can visualize the network. So here in the diagram you can clearly see that you have hub network and then you have a spoke. Somehow this design, this is giving some sort of idea that in upcoming iteration we are going to use some sort of spine and leaf structure. Sometimes it is referred as a cross fabric. So you have your leaf, you have your spine, all the leaves they are connected with the spines, and these leaves they are not connecting to each other. And that's the thing we are achieving. Now again, when you are achieving this type of topology or this type of network where you have all the devices by default, they are one hop away. At that point of time, are you able to do the segmentation? For segmentation, we have already VRF, virtual routing and forwarding, and this is now from the years. So we are using the VRF technology, and later on you will come to know that in SD-WAN we are using VPN, that is nothing but the VRF only. Name or the term going to be used as a VPN, but logically or technically also they are also VRF, virtual routing forwarding. So now the complexity will increase when you have multiple devices, when you have different type of traffic and you mark those traffic as different type of VRF. How you're going to do the routing or maybe overlay routing, etc., etc. This is still we are using in the existing network. It is possible, but the thing is that the we need to write actually the more line of codes, more number of configuration you need it. Okay, but still we are using, and you can see that we have multiple technologies like VRF Lite or MPLS VPN, because BGP is a nice protocol which is supporting all sort of address family related to VRF and even other address families as well. Now again, in this design principle, uh, how we are going to deploy the network. Do I have a single provider design? Do I have dual provider design? Again, if you go from single to dual, obviously the cost will increase. The high availability and the redundancy feature will increase. But anyways, the cost will increase. Or you are going to use the overlay network design. And this is actually the future. Cisco has started their overlay network design, means technically we are telling this independent of transport. So either you have a dual or three or four different type of ISPs, you don't care. You are creating tunnel on top of that. That's the overlay tunnel. And Cisco has introduced their intelligent WAN where they are using DM VPN as a overlay tunnel. Okay, but again, we are using IWAN and DMVPN, although so many companies they are using it, but again you have to write n number of codes or more number of lengthy configuration. So Cisco is telling all their existing network that from IWAN you can migrate to Cisco SD-WAN. Okay, why? Because again you can see the cones that increase design complexity, additional technology needed for SLA over commodity transport. So there are some extra overhead that is there, although the design and the solution is neat and clean and beautiful, but still you have some extra things that you can't do in the SD-WAN and the automation and the SDN solution that is there in the IWAN. So that's why this movement is there. Now let me quickly show you some of the slides related to single carrier and double carrier or dual carrier. So here you can see your network may look like that. So although you have different link, but you have single carrier. Suppose if one of the carrier, or because obviously you have single carrier, but suppose if that carrier will go down, at that time you have loss, and that's why it is listed here in the con that bound to single carrier for feature velocity does not protect against MPLS cloud failure with single provider. Obviously, if that cloud will go down, I don't have resiliency or availability that I can go via the other carrier. Obviously, this thing I have in the dual carrier, but again, the complexity is there, the cost is there. So you can compare here the pros and the cons. The con is that increase bandwidth paying for bandwidth twice, increase overall design complexity, may be reduced to common denominator between the carriers. Means overall you are increasing the resiliency, but cost wise there is issue. Now considering this diagram and this diagram, and again considering the overlay network design, if we have best out of all these three, so that will be the exact solution we are looking for, and that's why we are looking forward for SD-WAN solution. Again, we can see this all these things inside section 1.5. So let me quickly show you that 1.4. So we have 1.4 and 1.5 where we can address those design issues and how SD-WAN and the DNA or SD access combine together, and they're going to solve these issues. That also we can discuss in the upcoming sections. We are still in the basic section where we are learning what type of existing terminologies we have, and then what are the new things we are going to learn in the new CCNP curriculum. So let's discuss the WAN overlay technologies. Inside this, we have a layer 2 overlay and a layer 3 overlay. Means this overlay technology or terminology is not uh, new actually. This is coming from the old technologies. Now we'll see in the SD-WAN and the DNA and maybe in ACI, that is again the data center topic, that this overlay terms will come again and again and again. So now we have something called underlay, that is your physical infrastructure, and then on top of that you are creating virtual dynamic tunnels. This can be layer 2, this can be layer 3. Layer 2 tunnel examples, here you can see that you may have layer 2 tunneling protocol L2TP version 3. You may have OTP or VXLAN, that's the very popular term we have, VXLAN, and this we'll learn more and more in the upcoming session. When we are talking about layer 3 overlays, we have IPsec, we have GRE, we have Lisp as well. Now this Lisp I'm going to cover in the next slide, but at least you can understand that yeah, you are extending layer 2 fabric or you are extending layer 3 fabric, or to extend the fabric either you need layer 2 or you need layer 3 uh, address families or addresses, etc. Now, what is there in the SD-WAN or what is there in DNA is that we are going to automate this process. So you need not worry. So for example, in SD-WAN to create the IPsec tunnels, like in I-WAN, we are creating the DMVPN phase 3 tunnels. Here you're not worried to create the IPsec tunnel. At the moment you bring up the fabric, automatically those tunnels will get formed. Now, when we are talking about the tunneling technology, a normal IP packet, a normal packet, we have the payload and the IP header. In GRE, again, you have the payload and the IP header, and then you have extra overhead for GRE. Correct? In IPsec mode, either you are using IPsec mode in transport or tunnel mode. In transport mode, you have less overhead in terms of packet, but in tunnel mode, that is much more secure, and by default, most of the technologies they are using the IPsec tunnel mode, where you have the inner header and the outer header. So at that point of time, obviously your header size will increase, but the level of security will also get increased. Correct. I'm not going deep inside the IPsec and how IPsec is working and GRE and how GRE is working. It's just the overview. We have just started the course, and as per the agenda, whenever these things will come and it will tell in the exam or in the curriculum that we have to go deep dive in this particular topic, I'll go deep in this, that I'll do the packet capture, will analyze the packet, etc., etc. But at the moment, we are just getting familiarity with these technologies. Already these technologies are existing, and what new we are going to get in the uh, new enterprise setup or in the CCNP enterprise. And now, for example, Lisp, locator ID separation protocol or identifier separation protocol. Now, if you understand Lisp, so for example, I already told you that you have LAN based SDN. So SDN solution, you have three things. You have LAN or SDN for LAN, SDN for WAN, and then you have SDN for data center as well. So data center. Now for LAN, the common term is SD access. Obviously, I'm talking only in terms of Cisco. So in Cisco, we have DNA is a name, but the SD access is the technology. In WAN, we have SD-WAN, and in data center, we have application centric infrastructure or ACI. Now, if you go and learn deep all this technology, you will find that everywhere you have some sort of leaf spine type of a structure. So suppose if I have two spine and then leaves like this. So again, I'll take one more leaf so I can show you the redundancy. So all these leaves will go and connect with the spine, and leaf they will never connect. These spines, they are working as a route reflector, means these spines, they have the database. So now these leaves, whatever endpoints or whatever devices are connected with these leaves, in DNA they are termed as a edge node or edge devices. So these edge devices, whatever network, whatever entries, MAC address, IP address, etc., whatever they have, they are sharing with their spine or their parent. Now this spine in DNA is mapping system or mapping resolver. Now this spine in ACI is spine and leaf. The spine and leaf is a term inside ACI. Now in SD-WAN, loosely if you analyze, you'll find that you have something called vSmart controller who has all the database for all the routing information. He is the controller or the control plane device. And he is working as a route reflector. In ACI also, these spines are working as a route reflector. And suppose if you are not knowing all this technology, so there are chance that you will get confused that, oh, what I'm telling that, okay, in SD-WAN, the vSmart, in ACI, this fine, in DNA, uh, it's actually the control plane device. Sometimes we are telling this as a control plane routers or maybe border router, etc. So again, we'll see later on, but what at this point of time you can mark or understand is that you have some common authority. You have say common authority just like DNS server where they have all the topology information, all the database information. You think that you have the database information. Now these endpoints, they have offloaded with the information, so they don't have entire topology information. They know their local system or local endpoints, local entries. Once they have their local entries, they are teaching or they are telling the common authority that this local system I have, this local IP MAC I have, you please store at you. Likewise, he will also tell, okay, you please store with you. And when this guy wants to communicate with this guy and he don't know how to reach it, he will send the query packet to him. I want to reach there, and he will reply in a way that now they can communicate directly. Okay, so these are working as a proxy on behalf of, and most of the technology, most of the SDN technology, we have the same analogy. All right, so now we can understand all the different technology. If you say, for example, if you know other non-Cisco technology as well, for example, NSX T or any other SDN solution, there also you'll find the same type of thing is happening. Okay, and then once you start comparing these technology, it will become easier to learn and understand, because again, every day some new thing will come and it's almost impossible to learn and memorize all those things. So better you start comparing different technology, and then we can learn it easily. In section 1.1a, we need to discuss about quality of service as well. Now we are going to see the design aspect of this, because we should understand the core quality of service things, and then we should understand the SD-WAN quality of service things. Now the basic principle will not change. So how we are going to do the classification, marking, policing, shaping, scheduling, etc., those things will not change. So what are the things are going to change? The way that we are going to implement to the devices, those things are going to be changed in the SD-WAN. So I have already uploaded complete course for SD-WAN. There you can go and check how we are going to use this QoS actually inside the SD-WAN. Now, at this point of time, let's focus that what are the basic components of quality of service. So here you can see that we have three important things: classification and marking. You classify the traffic, you mark it. We have policing. Policing is something like you have some sort of a strict rule with the traffic. So if certain limit or threshold will breach, it will start dropping the packet. And then we have this scheduling, including queuing and dropping. Means you want to give some sort of buffer in case if you have congestion. Means you don't want to directly drop the traffic, but you have some sort of buffer for that. Now here on top, you can see that you have different type of class of traffic. Say I have voice class of traffic, then I have video class of traffic, telepresence and data. Now for all these type of traffic, they have different requirement. So some of the traffic are UDP based, some of the traffic are TCP based, some of the traffic that we have need high latency, some can tolerate with delay, etc., etc. So now you can see in the bottom that say for voice traffic, you have UDP priority, but latency should be less than 150 millisecond. Otherwise, this voice will auto destroy. There is no meaning for that. Means whenever we are sending the voice packet, you think that your TTL is set with 150 millisecond. If it is not delivered between that time, it will get lost. Something like that. You can see the jitter should be less than 30 millisecond, loss should be less than 1%. Now why we are discussing this? Because the first fundamental of QoS is classification and marking. So you can do the classification of the traffic, and you are understanding that what is the loss latency and jitter requirement for different type of traffic, including that what type of protocol they are supporting. So you can see this voice, video and telepresence, they have UDP, means they are very much real time traffic, but you want trustworthiness as well, you want security as well, and that's why you have the business traffic, or you have business data that is using TCP protocol. And that's why here you can see in the bottom that you have mission critical application, maybe SAP, maybe any type of database, etc., etc. Now the bottom line that you are seeing here, that is actually important when you are going to create the QoS policy. In other words, when you are going to create the policy, if you breach certain SLA as specified in the bottom, then that policy can take some decision. So dynamically changing the route, etc., etc. And that's it. And this particular feature has been optimized in the SD-WAN solution. So here it's very much coding based. You have to understand the protocol, means the device should understand the protocol. According to that, you have to write the code, and then it will take action. Correct? So first thing is that to do the classification of traffic, there are several methods in QoS that you can go and deploy it. Here you can see one of the example for that. So you are creating the policy map, then you have class voice, because this is high priority traffic. You're giving priority for voice, you're giving priority for video. Then you have the critical data. You're giving 15% for that. You're using some random detect DSCP based. Again, there are different type of drop methodology. Means you're going to use RAID, random early detection. You're going to use tail drop. So those methods you can use. Again, you can see the data bandwidth percentage is 19%. This is again just an example. Your scavenger traffic, you are giving a less bandwidth percentage. Network critical, you are giving this 3%, etc., etc. So bottom line is that you need to write the code for all the devices inside your enterprise infrastructure, and then you have to configure it manually one by one by one. See, suppose if you have same type of hardware at 1,000 places, you have to write this code, or at least you have to do the copy paste to all those 1,000 devices, rather than if you do this thing via the SD-WAN. It's like you have, once you created the template, you can push from the management plane to all the devices, correct? And here you can see that how this queue look like. So the important thing here is that you need to do the classification and then you have to map with the queue. So classification or forwarding classes to queue mapping, that will be the step number one. Again, on top you can see this is for low latency queue or class based weighted fair queue, where you're adding the voice, video, etc. Now we have a nice example here that is clearly telling us that traffic shaping. So without shaping, how it look like. Once you apply the shaping, then how it look like. Once you apply the shaping, then the shaper typically delay excess traffic, smoothing burst, and preventing the unnecessary drop. If it is polisher, it will chop up, it will directly drop the traffic. Again, we have other example. So suppose this is your configuration, and once you apply it, obviously you have one bandwidth pipe, and generally we are applying this policy to the WAN facing interface. So suppose if you have 300 Mbps speed, correct? So you have 1 gig interface, but as per your agreement you have 300 Mbps speed. Now how you are going to use that uh, classes, and how you're going to allocate that 300 Mbps speed with priority, with some scheduling, with some RAID to the device that you can see here in the example. And again, we are making this as a child is called under inside the parent. Inside the parent we have the shaping, we have some buffer limit. Okay, so this is the way that we can go and apply the QoS. Again, we have one nice example here that you have your enterprise devices, you have your MPLS devices, where means in inbound what type of policy you want to apply. And these examples that you are seeing here is the standard one that Cisco is recommending. Still, if you want to learn more about QoS, you can go and check the QoS, Cisco QoS deployment guides, and there are tons of information we have um, over Cisco URL that we can go and get it. But this is something like a standard format. So all the companies, they have this type of existing network where they want to apply QoS. Now here you can say that you can't apply QoS to the ISP side. So whatever QoS you have to the ISP side, the same thing you want to match to your side as well. And that's why if you go and check the E and F configuration, so outbound policies, here you can see the outbound policies as LLQ or class-based weighted fair queue, remark, real-time traffic, class-based weighted fair queue, etc., etc. Then you can go and check the service provider in the bottom. So what is there in the outbound, what is there in the inbound? So obviously my outbound will be the inbound for the service provider, correct? So we are going to manage this enterprise network, and then according to our QoS we can consult the service provider, and we can tell them, okay, you can map this DSCP, this policy from your side as well. As long as we have the common agreement, the common configuration, things will be better. Now again, this design strategy that you are seeing here, there is major change in the SD-WAN. Now to reduce the cost for the SD-WAN MPLS, because you know that MPLS cost is too much. What customer are doing, instead using 100 Mbps MPLS, they are using 1 gig internet. So you will see even here also, in upcoming sections I will give you some slight design related things or stuffs that you can compare later on in your study as well, that what is existing design means what is existing hybrid design, internet plus MPLS, and then when we are moving to next generation SD-WAN type of network, what design possibilities we have. And again, you can argue that okay, MPLS has this advantage, internet has this drawback, etc., etc. But nowadays, the big enterprise, they are using dual internet connection. Primary, secondary, both they are using 1 gig or maybe 2 gig internet interfaces, and then they are load balancing the traffic. All right, so if you have GRE or IPsec QS consideration, on top you can see that you have normal packet without QS. Obviously, we know that in IP header we have TOS type of service. Now, if you are using QS with GRE, so you have your inner header, you have your GRE header, you have your outer header, and then you can see this TOS is propagating from inside to outside. Likewise, if you have IPsec encapsulation where you have inner header and outer header in case of IPsec tunnel mode, so you can see that we are retaining the QS marking. All right, so these are the examples related to QS. And just again, this is again very much high level, but you should understand, and as per our curriculum, exam or this is to expect that we should know these variations. We should know that what we have in the existing and what we are going to have in the upcoming SD-WAN QS. All right, so let's stop here. This session is quite interesting because we are going to discuss about the WAN and the LAN architecture designs. And actually, we have started this course and we are studying about design principle, what is existing, what is going to become, or what is the SD-WAN or DNA, etc. As per this the scope of the CCNP exam. Now, thing is there. So I have one dedicated slide. I'll come after 2 to 3 minutes to this particular blank slide. Let me quickly walk you through 2, 3 slides. So we know that there is demand, there's drastic demand in the networking. Means there are so many things that try to connect with the network. Means we have IoT, we have so many handheld devices. We are managing different type of mobility features or mobility devices. We are managing everything maybe from the cloud, so we can integrate with the cloud. We have different applications. We want to do the visibility for the applications. To manage all these devices, the complexity will be very high. If you directly going to the cloud, your threat surface will increase, so you should provide security even from the inside or outside your, etc., etc. So the bottom line is this, that you have demand because you have to integrate different type of devices inside your networking infrastructure, and then due to that complexity will increase. Manageability will be the challenge. In that case, your security, or you may have the holes in the security. So everything should be integrated, should be tight. And what will be the solution? So the solution is that instead using the monolithic, or instead using the existing way to manage the IT infrastructure, you can check the SDN, software defined type of architecture. Now, what SDN will provide, at least at this point of time, is that you can focus on application. So SDN, the true capability of SDN is that now we can build the policy based infrastructure. Now, what does it mean? So for that reason, I have this particular slide. So I'm going to draw one very nice difference in between all the technologies that we have, all the technology related to SD-WAN, and this will give you nice idea about different type of complexity that we have in existing and where we are moving actually. So for example, we have LAN, we have WAN, and we know that we have data center as well. Now, for all these devices, if we are connecting LAN, obviously you have LAN. If you have multiple ISP, you can go and connect with the WAN, and then somewhere you may have your data center, correct? This is something like your existing network where you have spread branches and you're using existing methodologies to manage your IT infrastructure. Now, what is the different when I'm going to use SDN approach in to manage the LAN, WAN, and data center? For LAN, we have something called DNA or SD access. For WAN, we know that we have Cisco WebTel SD-WAN. For data center, we have ACI. Now we know at this point of time that all these infrastructure, all these component of the IT infrastructure, they have control plane, they have management plane, they have data plane, they have policy plane. Somewhere you will find the orchestrator plane as well. So who is the control plane for DNA, the management plane for DNA, data plane, and policy plane, etc. So now this thing you have to study, and you can compare different technologies. So the control plane is again you will see that Lisp is a protocol who is managing the control or who is providing the control plane information. But for that you have border routers. For SD-WAN we have OMP, overlay management protocol, who is managing this, but the controller is vSmart. ACI, we know that we have a spine and leaf architecture, and we know that we have the COOP protocol. Maybe you have MP BGP protocol to manage the control information. Correct? What about management plane? For management plane, we have a DNAC center, that is nothing but Epic EM, Epic Enterprise Module. This ACI, they are also using Epic, but this Epic and this Epic is 100% different. This is for your DNA or DNAC at this point of time, we can understand. And this is there for your data center manageability. Then what about SD-WAN? In SD-WAN you have vManage. Then the data plane, you are going to use VXLAN. You have edge routers. For SD-WAN, your data plane is nothing but IPsec tunnels, but you are using vEdge or cEdge, the Cisco edge devices, Cisco routers or Viptela routers. ACI, you have leaf and a spine structure. So your leaf will be your Nexus devices. Here in the spine also, those are the Nexus devices that you can check the reference sheet or data sheet. But Cisco is using IVXLAN, something you can tell that intelligent VXLAN, because they have this one field for having the contract information as well, okay, or maybe policy information as well. Some extra bits are there in that VXLAN format. Then the policy plane, who is the policy plane? The ICE we are integrating with DNA. So ICE is the policy plane. For SD-WAN, your vSmart is the policy plane, and for ACI again your Epic is the policy plane, because there you can go and build the policy and then you're pushing to different type of devices. This is the reference, and we can see, and now you can think that, oh my god, my existing network is better than what these stuff. So now you have to learn, understand DNA, SD-WAN, and if you are doing your data center study, you have to learn ACI and lots of programming as well. Okay, so this is the overview we have for all the upcoming technology. At least you will learn the SD-WAN and the DNA plus the WLCs. I haven't shown you where the WLC is fitting in the picture. I will check later on in the DNA section. Again, this is the DNA framework that you are constantly learning the network, and then you can take the decision. We'll discuss more and more about this framework in the upcoming session. But at least you can see that you can manage the entire network from the cloud management. Then you have this full automation capability. You have analytic engine inside DNA. It's a big UCS box that DNA boxes are. You have full visibility because these devices, these Catalyst devices that we are using, or the hardware that we are using for DNA, they are very smart, intelligent, and they have programming chip inside that. And due to that, the telemetry feature by default will be there. So we have the full visualization for all those events and things are happening with help of DNA. We can visualize the network. Then we have the full programming facilities, either for the physical or the virtual infrastructure. Everything is integrated inside the security. We know that we have the policy plane that is nothing but ICE, from where we can push the policy to the DNA devices. So the principles are open, programmable, API driven. And obviously we can do everything that whatever we can do with the CLI or GUI, we can do with the API as well. Now here you can see in the diagram that you have the DNA center, that's your management plane. You have SD access and SD. So DNA is a term and SD access is the technology actually that is used. Then you have the hardware as a Catalyst 9K, and then you have the security features that you have in encrypted traffic analytics. It's a big thing. Actually, DNA is a big thing. SD-WAN is also big because now whatever we have a study, we have to rethink our study, or we have to redo the study. And if you compare, or if you try to compare that what we have done in the existing network and what we are doing here in the DNA or SD-WAN, so actually there is no much a scope of comparison. We should think that this is the new thing we are learning, and then we can start from the scratch. All right, so let's just stop here, and next section is interesting. That is our core existing technology that I'm going to discuss in campus design, and other topics are also there. This section we are going to discuss about the technology that we know, the multi-layer campus design, and obviously in the upcoming section we'll discuss more about the upcoming technologies. So we know that we have our core layer, distribution layer, and access layer. Again, I have slides for all these layers, so we can go and discuss there, but everything is going and connected to the core, and then core is taking decision that how to send and where to send the summarized routes, etc. So here you can see this core is connected with the devices again at the distribution layer, and then you have the access layer where we have the WAN, where you have the internet, means you may have hybrid topology where you're connecting with the WAN, internet, and you're connecting with your data center as well. Again, this is one of the campus design, and maybe at this point of time, 80 to 90% of campus design is like this only, because now we are slowly moving to the DNA. The adoption rate at this point of time for DNA or SD access is not that huge, but we are expecting that it in coming 1 to 2 years, or maybe 2 to 3 years, we'll see much more adoption for SD access. Okay, so this is the core that you have, the core, distribution, and access layer. And again, if you split this diagram, you'll find that you should have, say, a structure, modularity, and hierarchy, that you have the core, access, and core, distribution, and access layer, and where you are going to connect your MPLS circuits, where you are going to connect with your internet, where you are going to connect your IP telephony services, etc. Okay, so let's quickly check that all these layers, what they are offering, what exactly they are looking for. So here you can see the diagram left and right. You have the boxes and how it look like. So you have the core, distribution, and then you have access. Like that you can think. We have dedicated slide for all these layers, so better we'll check all these slides one by one. So what's the use of the access layer? What access layer is doing? You have L2, L3 features. You can go and use the high availability security QoS, IP multicast, etc. You can go and use QoS. You have IGMP trust boundary. You have broadcast or multicast boundaries as well. If you want, you can suppress those requests. You can go and use various type of optimization method for loop prevention if you are using L2 methodology. If you are using L3 methodology, you can use routing protocol like EIGRP, OSPF, etc. If we are doing high availability and redundancy, we can use PAGP, that very less guys are using Cisco proprietary port aggregation group protocol. Generally, we are using LSAP, link aggregation control protocol. If you have if you are using UDLT or FlexLink, etc. Okay, so this is something where you have your trust boundary, where you want to protect your network. Obviously you want to protect your network to all the places, but this is the place where the endpoint will come and connect. So at this point of at this particular level, you want higher security, you want segmentation, you want MACsec, BPDU filters, filter guard, etc. Correct? Now, next you have the distribution layer. Distribution layer is there. This is the second type of backbone or second level of backbone we have, where you want to apply some more mature policy and high availability features. So that's why we have the high availability load balancing QoS. We can do the aggregation of all the access at the level of distribution, means you have less number of devices that is there in the distribution label at compared to the access layer. Even in access layer, you can use 2K series or 3K series switches. In distribution layer, you can use 4K or maybe a 6K. Now Cisco is requesting everyone to use 9K model of switch, so you can choose those recommended or the supported models in terms of hardware capability. They can do the route summarization, fast convergence, and HSRP GLVP. That we have separate section for first hop redundancy protocol, HSRP, GLVP, BRRP in upcoming session. So we'll discuss more in the upcoming session about that. Core layer, obviously it's the core. This is the backbone. You want high availability and the scalability for the core layer. They are the aggregator point for all the routes. And again, if you go and refer this diagram, this particular diagram, you can understand that things are converging towards core layer, and then from core layer, you can distribute those routes to the other locations as well. Again, here you can see in this diagram how it look like. So you have layer 2 access, you may have routed access, you may have virtual switching, etc. Then you have the distribution level switches, everything is coming to the core, and then it is going to one of the branch or the data center or other branches. So this is the network that we are very much familiar. And again, with respect to design, you'll find that there are variations that we need to consider. Obviously, there is the evolution for the hardware. For all the devices, there is evolution or there is upgradation for the softwares also for all these devices. So how much virtualization these devices are supporting, uh, how much hardware, again that depends, means how much throughput as a customer or as a user I want from these infrastructure. So according to that, the hardware can be implemented, and it's recommended that even if you have this network and you want to upgrade the switches in this network, use Cisco 9K switches. So in the future, if you want to migrate to DNA, you have some sort of switches where those are supporting DNA. That's a strategy nowadays all the company are using. So they are not ordering for the legacy or the old hardware, rather than they are going for the new hardware. So in future, if they want to migrate, they can use that as strategy. Again, as per design perspective, here you can see that you may have layer 3 distribution interconnection, or you may have layer 2 distribution interconnection, means you want to stretch the boundary up to distribution layer. So this red color wire that you are seeing here, those are L3, and this bluish color connection that you are seeing, those are L2 domain. And that's why it is telling that what you want layer 2 access. So obviously in the bottom, in the access switch, you have the VLANs, you want to do inter VLAN routing. You have the obviously by default the STP will be running there. You have the HSRP or GLBP. You want some Ether channel. You have some BPD guard, etc., etc. So all type of prevention you have. Some of the companies they are using layer 2 boundary up to the distribution layer. So here you can see the difference. Let me quickly show you the difference. So you have layer 3, this red color link in between the distribution switches. They are using a routing protocol to forward the traffic, and that's true actually. If you see any of the upcoming network or any of the SDN solution, you'll find that even for layer 2 carrier or even for layer 2 also, we are using routing. So what does it mean? So for example, if you go and check Cisco ACI, application centric infrastructure, where you have leaf and a spine, they are connected behind the scene, but they are using layer 2 type of routing strategy. Means MAC addresses also can route. That you can check, but that's true, uh, that the routing is better than that we are doing in terms of switching for high available network or for a scalability reason, and that is again one of the design aspect we have. So suppose if you have two different fabric, a stitch fabric, you don't want to extend the L2, although you can extend the L2, but routing is always preferred uh, on top of the L2 tunnel. So for example, the L2 tunnel is not preferred over L3 routing tunnel. All right. In short, routing is preferred design rather than stretching the L2. This is also supported model. This is not for the reason that we are talking that L2 is supported model or L3 is supported model. This is something that which is giving the capability of, say, for example, VSS, virtual switching system. So uh, there are parallel enhancement in the network. Suppose if we have switches, if we connect, obviously you know that as per their priority and MAC address, they will choose who is the root switch, who is the secondary switch, etc., etc. All priority and everything. Now, what you can do in this case that you don't want these triangles in a network. What you want straight line. So you collapse these two switches inside one unit, and then the bottom switches also they can think. So this diagram will be like this, or maybe this diagram will be like this. Means two switches, they are connected back to back. Physically they can be like this, but logically they will be like this. That's the overall idea if you are using this type of technology. And then that's the evolution you have. If you see the data center evolution, you'll find that it started with 6500, then it moves to Nexus 7K, then Nexus 9K, and then now Nexus 9K CI. So started with normal this type of network, then moved to, for example, VSS, then moved to VPC, then moved to leaf and spine, and then leaf to spine ACI. Okay, so evolution is there. Up to you which network or which type of a standard network or design you're supporting. You will find this type of network as well. You'll find this type of network as well. Both are supported in an existing model we have at this point of time. So you can have these devices in same unit, these distribution devices. So you have, for example, one control and two data channel, and these devices they are working as a MEC, like multi-chassis Ethernet, etc. Means you are eliminating the L2 loop rather than you have a straight line in the network. All right, so this session is actually becoming lengthier. Let me stop here, and next section will continue from here. Let us continue the previous section, and we have seen that we have option that we can use L3 distribution link, or we can use L2 as a distribution link in between that. If we are using L2 capability, we have option that we can go and use virtual switching system, where we want to reduce the number of triangles in a network. Now here you can see the convergence time with respect to RSPVST or RPVST plus, then the routing protocol like OSPF and EIGRP. And that's the thing that we are considering, that when we are using the routing protocols, their convergence is faster. They are not using the blocking interfaces like if you are using L2 interface, then STP will run automatically and 50% of link will be unutilized. So those things are not there. That's why always this routing design will be preferred with the switching design or L2 design. How it will be looking like inside the DNA, that we are going to discuss in the upcoming session. But if you see this diagram, from this diagram, let me try to explain a few of the things. So here you can see that you have border router. So for example, BRBR, then you have edge devices. Maybe they can do switching and routing both. So you have the edge devices as well. Now, with the use of these edge devices and plus this APs that you are seeing here, that they are near to the end point. So now these routers or now these edge devices, they are not learning the entire routing table, entire topology table, not everything, but they are knowing that what is connected to them, and then they are sending those information to MSMR. So we have this resolver, or we have the servers where they are pointed to, or they are sending all the information to the global routing table. Like that, you can think. You have one DNS, and that DNS having the information from where to where I have to reach. So those all information that DNA has or having. Then you have the access point that you can see, and then you have the WLC, that all the access point control information, or all the access point, those are managed via the WLC. We are going to discuss this also. So we have the underlay architecture or infra, we have the overlay architecture and infra, and this underlay and overlay in conjunction, they are working for SD access. Here you can see that the ID challenge, new services, you have the mobility services, scalability, flexible and programming infrastructure. Those are the things that you'll find inside DNA or SD access. We have the controller, we have the control plane, and this thing we have discussed. We have the policy plane, that is the ICE identity services. With help of control plane and policy plane, or with help of the DNAC plus policy plane, we are going to manage the DNA fabric or DNA center. So you have the endpoints, and the way that these endpoints are thinking now, they are they have offloaded the load that we have in the existing campus area network, or in existing enterprise campus area network, correct? So these are the things that is going to be new thing, or these are the new innovations we have from the existing campus area network. So now if you see this existing network, and again you can go and refer this MPLS WAN technology design guide, you will get a nice document from Cisco. Now if I go here and highlight you certain things, so here you can see that you have your core, then you have your campus area network where you have the distribution switch. You may have one building with one switch, other building with one switch, where you have connected the access point. Here you can see you may have uh, one floor where you have much more number of users. So then you have the endpoint, IP phones, you have wireless access points, and you have roaming users, etc. So you have the access layer endpoints, maybe you have IoT devices as well in the existing network as well. Then you have the distribution, and then you have the core switch. Now here you can see that your core switch, one portion is going towards the WAN, and maybe this is my data center or main location. One portion it is showing that it is going to data center. So you have the Nexus switches where the core switches are connected, and then you have Nexus 5K, then you have MDS and your storage network and your application servers, etc. So you have your data center. Here you can see that you may have CE to P. So suppose this is your CE. Customer is here. You have PE. Somewhere you have the MPLS backbone that you have the P devices, so PE and P devices. So here also you can see that your core switch is connected with the core router, and then it is going to be terminated to the WAN. Here you can see that you have the VPN endpoints for the remote users, or suppose if you are using DIA or maybe DCA, direct internet access or direct cloud access, then your traffic is going via the firewall to the internet where you have IPsec tunnel for the remote users, or maybe those users who are connecting with IPsec. So either teleworker, mobile worker, or the remote user. So maybe in few of the branches they are using internet and the WAN both, means they are using the hybrid type of branch, or they are the hybrid type of branch, or maybe we have the dedicated MPLS type of branch. So that's the reason everything is shown in this particular diagram, and this is one of the validated campus area network. In this particular curriculum, you will not study this data center portion, but you should know each and everything that is showing here in this diagram with new format, with SDN format. And that's the overall goal with the CCNP Enterprise Network, that you should know the DNA and SD-WAN, but you should know the core as well. Again, the same thing here. You can see that how the core distribution, and then again you're going towards dual MPLS or dual carrier. Maybe you're going towards layer 2 WAN. Maybe you have some internet and you're creating IPsec tunnel, and then you're going to the internet. Okay, so all the summary routes, they are coming and collected to the WAN distribution layer, and then it is going to the core. Now this slide is also very important, and this is equally important for SD-WAN as well. So whenever you are doing the migration or the new SD-WAN deployment, at that time you have to mark the site. So you may have sites, say for example, gold, silver, you can mark it. It's just the name, and maybe bronze. Now gold means that you are using uh, uh, say for example you have dual devices and dual ISP, that is your core, this type or maybe this type, that is your high available network. Silver may be that you have only one device but you have two ISP link, either two MPLS or maybe one MPLS, one internet, or dual internet, correct? And bronze means that you have one device, one connection, one device, one connection. So as per the type of branch, you can categorize the branches or branch type, and then you can create the templates, and then you have to push the templates, or you can create the configuration and then you have to manage them. So for that, you should understand that what type of remote branches will be there. Now, once you identify your remote branch, that one part of this course, the other thing that you should know, that what is behind that, correct? So once you know that the WAN part, you should know the LAN part, and then that will become the enterprise network, correct? So for that reason, you may have multiple option, but I'm going to show you that a few of the examples. So maybe you have shared LAN, maybe you have L3 connection with the switches that is behind this edge devices, or maybe you are using some sort of highly available and redundant design, or maybe ether channel, multi-chassis, or a stack of switch. Actually this is the recommended way, and suppose if your WAN is your internet, so obviously you have to put the firewall as well in between that, correct? So these are the design options we have the last recording and this recording. Actually, it's very important. You can, I'm going to upload this document so you can have the reference, whatever have discussed in the previous section and this section, and these sessions, these slides, these recordings are the fundamental of how we are going to design what is in the existing, what is going to come in the DNA and SD-WAN. Inside 1.1b, we have to understand or discuss about the high availability techniques such as FHRP and SSL. So let's discuss one by one. FHRP is nothing but first hop redundancy protocol and how it is working and what are the flavors you have. You can see that we have HSRP, that is the hot standby redundancy protocol. Then we have VRRP, that is virtual routing redundancy protocol, and then we have the gateway load balancing protocol. Now, VRRP is the industry standard. This HSRP and GLBP are Cisco proprietary. Mostly, we are using VRRP. This VRRP and HSRP both are very much similar, but this GLBP is different, and we can discuss that how different this gateway load balancing protocol is. Basically, what is happening in all these gateway first hop redundancy protocol or gateway load balancing protocols are that, say, these, suppose if we have two routers or maybe switch, and these switch, they have the common interface going towards the LAN, and suppose you have one PC here. Now this PC can have gateway here or can have gateway here, but the common term here is, or the technology here is, that we are not giving gateway, say for example dot 1 or dot 2 for this particular IP who is dot 10. Rather, we are giving the gateway to some virtual IP, and that is glued with this device and this physical device. So what is the benefit? The benefit is that, for example, this particular device or router, so for example, this is router A, this is router B, he is working as an active member and B is working as a standby. So that means that packet is forwarding in this direction, and suppose if the link going towards the WAN or going towards outward is down, or the device is down, automatically the packet get gateway from this direction. Okay, so that's the term, and that's the mechanism, some sort of high availability mechanism, we can say, that if one of the device is down, or maybe if the link that you are tracking is down, you can go from other direction. Again, if this device will come back online and you have set some prompt, then again the traffic will go in this direction. Okay, so that's the thing that we are using with VRRP and HSRP. GLBP is bit different, because now if you see these terms or technology, you'll find, oh, so is it like a spanning tree or something, that all the time one of the member is active and other is working as a standby, means 50% of the resource utilization we are doing? The answer is not exactly what we can do. Say for example, for certain VLAN 10, 20, for example 30 and 40, if I have these four VLAN, for VLAN 10 and 20, as per high priority, here higher is better, you can set priority 200 towards router number A. So suppose this is router A and this is router number B. This A is for active, is for standby. A and B is the name of the routers. So for 10 and 20, he is the active member, and so for example 30 and 40, this B is the active member. So that means that they are using some sort of active mechanism to send the traffic, and obviously you have different virtual IP for all these different subnets. This way, In case of HSRP and VRRP, you can achieve active-active type of load balancing. GLBP is a bit different. That is doing the load balancing by default. So let me show you this in the diagram. You can see that when you have the distribution layer, here you can see that you have the first hop redundancy protocol. You can go and use first hop redundancy protocol. So used to provide a resilient default gateway. These are the technologies. They are providing millisecond of convergence time. Means if one of the active memories fail, it can go to the standby or the backup. BRRP, if you need multi-vendor interoperability, BRRP is nothing but the industry standard that we have already discussed. GLBP facilitates uplink load balancing, and the name itself is Gateway Load Balancing Protocol. Preempt is there to avoid the backhauling of the traffic. Means preempt is something that if your device will go down and if it will come back up, again it will become the primary member of the active member. Okay. Now here you can see that how they are working. So they have these devices, they have their IP, they have their MAC, then they have their virtual IP, they have their virtual MAC. Now this virtual IP is shared, so you can think as you have some ghost router in between, and that is glued with these two devices. So when the traffic is coming, here you can see, and if he is the active, the traffic will forward it in this direction. Okay, so traffic will come, it is going in this direction because he is the active guy as per the priority. And here you can see the example for all the IP, the MAC, the gateway. Gateway is the virtual IP, and the ARP entry. Now this is the standby or active and backup. If this will go down, obviously it will reroute it to the other direction that we have discussed. That's the mechanism, 100% same with HSRP and VRRP. Uh, but if you go and check the VRRP methodology used in SD-WAN, that you can go and refer the SD-WAN course, you'll find that there is customized VRRP inside SD-WAN where we are tracking the OMP, we are tracking the prefixes. So track OMP, track prefix. Rather than here, if you want to track the interface, you have this option that you can go and track the interfaces as well. So what I'm telling that, suppose if you have WAN and you want to track this interface, you can track it. Suppose if this will go down and its priority is 200, its priority is 150, automatically you track the interface and decrement the priority. So this priority at the moment the link is down, this will become 200 minus 100 means 100. Now 150 is higher, so traffic will go in this direction. So that's the tracking thing we have. And again, the preemption option we have, you can preempt it. So if the device is down, the traffic will go in this direction. When it will come back up, then again it will go from the primary member, from the active member. Same thing we have in the VRRP, so that's why I'm not discussing here. Same methodology we have, because VRRP is open for all the vendors. It's a multi-vendor support. Rest of the things are almost the same. Now, next we have the GLBP. So let's quickly discuss about GLBP. GLBP is doing some sort of gateway load balancing. So here you can see this IP, MAC, virtual IP, and virtual MAC. Now you have virtual MAC here, and here you have two different virtual MAC. So what will happen that sometime traffic will go in this direction and sometime traffic will go in this direction. That's why you can see that both the direction we have the traffic flow. Although I haven't seen much of the customer using this methodology due to some internal load balancing issues related to MAC addresses. But yeah, we have this option that we can go and use the GLBP as well. So where we don't have to group the VLANs that we have discussed earlier. So you don't need to group the VLANs, but they will do the load balancing at their own level. So they can do their MAC address based load balancing. And here you can see that how some of the traffic is going via B, some of the traffic is going via A. One is the active virtual gateway, one is the active virtual forwarder, like that. Okay, so this methodology that they are doing the MAC based load balancing, this methodology you can create some sort of VLAN based load balancing. So some traffic will go via the gateway 1, some traffic will go via the gateway 2, and as a whole unit they are working as a active load balancer. All right, so let's just stop here. Let us continue the previous section and discuss about the other high availability features that we have. So we have SSO, that is the stateful switch over, and how it is helping to provide high availability in the campus architecture design that we are going to discuss. Now here you can see that we have two different type of network design. We have layer 2, layer 3 topology. We have multi-tier layer 3 topology. Here you can see that this blue interfaces, or this blue lines, are a layer 2 interface, and then this red one, red color connectivity lines are L3 interfaces. Here in this diagram you have L2 plus L3 link. Here in this diagram you have everywhere the L3 link. So either it's L2 L3 topology or complete L3 topology. We have option to do SSO. We can do stateful switchover. Now, what does it mean and why this is important? You can see here that you have two use cases for this. Either you have a big catalyst chassis box where you have active and a standby supervisor engine, or you have a stack of switch. Now suppose if you want to upgrade the image but you don't want to take the maintenance window. So you don't want to uh, tear down, or you don't want to stop the production traffic, and then you want to upgrade the image. That's the one of the use case with we have with the SSO. In that case we can go and achieve this target with help of SSO. Now when we are using SSO, there is one problem that uh, suppose you are doing iOS upgrade and you have this SSO feature enable. You have active supervisor engine, you have a standby supervisor engine. The problem here is that if you do the switch over, that will not be a stateful. Now to do this a stateful switch over, you should have the common database between the active soup and the standby soup. Here in the diagram you can see clearly that their active and their standby supervisor engine, they haven't synced their routing database. So particularly with respect to routing database, they are not doing the stateful switchover until unless you go there and enable one of the feature that is nothing but NFS, non-forwarding, non-stop forwarding. So here you can see that if you go to these protocol like OSPF, BGP, etc., and you have to enable the feature called non-stop forwarding, NSF. And for that you should go and check the dataset that which particular version or hardware or model that is supporting NSF, non-stop forwarding, which is not supporting. Okay, apart from that, it's okay that we have this SSO. We can go and use SSO with NSF, and then they will do the stateful switchover. That's the one very important point we have. The other point is that suppose if you are using ISSU, that in-service software upgrade. Now in that case also you should know that which particular supervisor engine, which particular image, what is the hardware platform that you want to upgrade. Suppose if you want to do the major upgrades, so for example 6.0 to 7.0, it is recommended from Cisco TAC or Cisco that you do not do in-service upgrade, or you do not do inline upgrade. Rather than you take complete uh, maintenance window, take complete downtime, and then you do the major upgrade. Now these SSO and these ISSU, or uh, these fast upgrades, whatever we have, uh, for these upgrades we can go and use this SSO, and it is quite a bit handy. Okay, so that's the feature we have with the SSO. All right, so let's stop here. We have completed 1.1, and now we are inside 1.2. In 1.2, the topics are that what is the principle for wireless LAN deployment, the wireless LAN deployment, and the services involved inside that. So let's first try to understand the design and deployment option for the WLAN or wireless LAN. We have controller based architecture, we have mobility architecture, how it works. So here you can see that what components we have. We have the wireless LAN controller, we have the access points, and actually if you compare these technology with the SD-WAN, so we know that we have the evolution of SDN technology or SD-WAN, or any type of SDN, SD-LAN, or ACI. Now in that, what are the things we have? We have something called control plane, and we have the data plane. Now, if you think WLC, wireless LAN controller, as a control plane, you can think access point as endpoint devices. They are working as a data plane. Means these access points, they are dependent upon their control plane or the controllers. Then you have the management plane. You can use Prime, Cisco Prime infrastructure, or you can use Epic EM or DNAC, DNS Center. We have the mobility service engines as well, MSE. So here you can see that you have the access point, and they have to join. First of all, they are forming some sort of CAP WAP tunnel, and that is the industry standard nowadays with the control plane. So you can think that the data plane, they will join with the control plane. The data plane is nothing but the AP. The control plane is nothing but the WLC, and then they are working accordingly. So once they join, then they are getting the configuration pushed, kicked from the controllers, and then they are up and running, or they are ready to run. Now, when we are talking about the centralized wireless LAN architecture, here you can see that you have your access point, and they may be spread across the geographical location. You have the controller. Now you have to think, or you have to check actually the data sheet, that how many access point that a particular controller can hold, and according to that you have to go and check the capability of the controllers, and actually when you are designing the network, how many access point and how many users you have. So those capacity planning we have to do. All right, so here you can see that in this design that you have the cap wap tunnel, and this cap wap tunnel, that is the industry standard. It can be for control plane. So here you can see that when they are forming the control plane, they have the DTLS tunnel. Even in the SD-WAN also, when we have the vSmart as a control plane, and we have the vEdge or edge devices as a data plane, they are forming some sort of DTLS or TLS tunnel in between to send and receive their OMP traffic or the control plane traffic. For data plane, they have the DTLS, that's the optional. But for data plane, we know that in SD-WAN we have IPsec tunnel in between that. So there it is different, but most of the things means logically, if you try to analyze, you'll find that yeah, WLC is a old technology, means wireless LAN control is quite a bit old in the market now. SD-WAN is also become older, but they have introduced this control plane and data plane feature long time ago. Even if you go and check the catalyst switch where you have the supervisor engines, so supervisor engines and the line card, so you have the soup engine and then you have the line card, they are also very much have the concept of control plane and data plane. So this control plane and data plane feature is not something that is 100% new in SD-WAN, but somewhere they got inspiration and then we are working inside the SDN. So now we have the cap web tunnel, and one note is that cap web is not supported on the layer 2 mode. Okay, so this is the thing, and let us continue. Here you have one graph where you can understand that your AP access point will boot. They will discover the wireless LAN controller. They will form the control connection that TTLS will set up. They will join the WLC. If you want, you can reset as well. They can check, WLC can check the image as well. From WLC, they can push the configuration and they are up and running. They are ready to run, correct? Again, very much similar to the SD-WAN steps. They are using the plug and play feature as well. The SD-WAN is also using either plug and play in case of C-Edge, that is the ISR devices, and they can use ZTP, zero touch provisioning, in case of V-Edge. All these things are explained with the lab in the SD-WAN course, so you can refer that. Now let's see and compare the plug and play option or feature here. Why we want plug and play? You want plug and play that, say for example, in remote sites, you don't have the IT management staff. So what you can do, simply someone at the remote location, they can connect the interface and that's it. Once they connect the interface, rest each and everything can be done remotely. So they can reduce the cost, they can reduce the complexity. You have the high level of security. Why? Because you are forming the DTLS channel with the controllers and the time and productivity. So that's the reason actually we need or this plug and play or this ZTP are very popular nowadays. So you have IT staff sitting somewhere in some location and he can manage n number of sites with the feature of PNP. How this PNP process is working, here you can see that obviously they have to resolve the DNS, they have to get the IP via DHCP, then they try to initiate the traffic, they try to build a cap web tunnel with the WLC, that's a discover phase. Then they can go and check cloud related features. Actually, what is happening in this at this point of time, that while they are discovering the AP, they should they have to form the DTLS channel, and for that DTLS channel, there are chances that you have your in-premises certificate or you are using some other cloud-hosted certification features. So cloud redirection will happen for these APs, and then finally they can go and join. These steps are very much similar in the ZTP process or PNP process in Cisco SD-WAN as well. So you can go and compare these two features. What you can do, that you can check the PNP process for the AP, and then you can go and search over Google the PNP process for SD-WAN or the ZTP process of SD-WAN. You'll find the steps will be similar. Obviously, the way that we are doing is different, but overall the steps are very much similar. So what will happen here, here you can see the summary slide we have, that AP will boot, it will discover the WLC, they will form the DTLS channel, they will join the WLC, and then WLC will push the configuration, and then the AP will be up and running. Now here you can see that now you have the three different tier. You have the management plane, either you are using prime infrastructure or DNAC, and that is solved or resolved inside DNS center. Then you have the control plane, that is nothing but WLC, and then you have the data plane, that is nothing but the access point. These access point can sit anywhere remotely, and you are using the feature called plug and play. So from the prime infrastructure, you are using WLC to the methodology is plug and play to install all the remotely hosted access points to reduce the complexity, to reduce or to enhance the productivity as well. Okay. So let's stop here. Let us continue our discussion. We have the controller-based architecture and the mobility-based architecture. Now this term mobility and the roaming both are different. Mobility means you are providing the mobile features. Roaming means the user can roam from one place to other place. He can associate and de-associate with a different type of access point. I can show you the diagram here. You can see this user, this laptop that you're seeing here. It can associate and de-associate with different access points, and that's the feature roaming. Mobility is providing you that capability that you can roam. Now, the next important thing we have is to understand that what are the WLC or which type of WLC is there and what is the capability. Again, you can go and refer this Cisco dataset. There you will get much more information about the capabilities, features of the WLC. So for example, we have the Mobility Express who can support 52,000, 50 APs, 1,000 clients, 100 AP, 2,000 clients in these series. As you can see, they are supporting up to 100 AP. Then we have mid-size enterprise level WLC, say 3500, Cisco 5520 series. There you can see that how many APs, clients, and what is the overall throughput. How many is APs client and what is the overall throughput for this 5520. And for the large enterprise, we have 8540 WLC that can support 6,000 AP. Even the rake unit, you can see it's bigger. So this WLC, that is 5520, is one RU, one rake unit. This 8540 has the highest stability, scalability, for redundancy and stability. Stability is again the different thing. Scalability is different thing. Higher availability and redundancy is again the different thing. So we can achieve all those targets, but this 8540 has the highest scalability, means it can support up to 6K, 6,000 access points, 64,000 clients, 64K clients. The deployment models, we have centralized, Flex Connect, and MES. More and much information related to this WLC and their operations and all, you will get inside CCNP WLC course. There is separate CCNP course for wireless LAN controller, or we can say that for wireless. Not only for LAN controller, but for complete wireless, we have separate course as well. But here also you will get the core knowledge, means what is AP, what is WLC, their association, de-associations, and their design related stuffs as well. So now when you are grouping the mobility engines, when you are grouping the mobility devices, here you can see that you can go and group this mobility devices. The mobility group name is a mobility group everywhere. They have their own MAC address, say 1 for this mobility device or the controller, then 2 for this controller, and then 3 for this controller. So that means his neighbor is 2 and 3. So 1 has neighbor 2 3, 2 has neighbor 1 3, 3 has neighbor 1 2. And now this client, if you check this client, he is roaming from one place to other place, and because these all these controllers, they are part of one mobility group and they have their own DTLS channel in between them. So for end user perspective, they don't have much issue to roam from one place to other place. Obviously, behind the scene, they are doing this control plane and data plane message exchange. So we have the CAPWAP tunnel and we have the join. We have all those things that we have discussed initially, and then they can associate and dissociate the SSID or the access point. Now again, you can see that you can go and group the mobility group. So if you want 24 WLC and 72 WLC inside the mobility group, you can go and group them. You should go and check the mobility group, say for example 8.0, 8.2, and 8.3. Even if you go and check the latest data sheet, you will find some new addition, some new revisions. So according to that, we can go and design our mobility groups. Okay, so let's just stop here. Let us continue and discuss the best practices. Uh, we should do the RF planning. We should do the RF optimization, means we should categorize the data, voice, video, traffic, and location and client density. We should have the optimized gig Wi-Fi as a primary and gig Ethernet as a fallback. We should have high redundancy, and we'll see in the upcoming slide that what does it mean by SSO in terms of client, AP, and WLC. And then we have AVC, application visibility control. That means for mission critical traffic or application, how you are categorizing the application, correct? So you are giving priority to one traffic over other. And that's why we have actually AVC. They can recognize the application with the metadata, and then obviously we can put the rule for that. Now here you can see that we have three SSO. We have client SSO. That means that if in case of any type of failover, the client state remain active. There is no problem with the active client state, in other words. Then we have the APSSO, means suppose if you are failovering from one active WLC to other, still your AP, they don't have disruption. They have stateful switchover. And finally, you have the cluster of WLC. So one is primary, one is backup, standby, etc. Like that, you have the redundancy in terms of WLC as well. So here you can see that box 1 to 1 means 1 to 1 availability. One is in active state and other is hot standby. I will show you that you can connect this via dedicated link in the upcoming slide. Let me quickly show you this. Here you can see that you have the redundant port in between two WLCs. Here you can see the redundant port in between two WLC. Correct. So like that, if client sessions are active, those are client SSO. If AP sessions are active in case of failover, those are AP SSO. There is timing in between that. So suppose AAP, which has joined the WLC, and then he is actively tracking the active WLC. Suppose this active is gone, then he will send some probe and he'll wait. He will not get any response from the active. That means he will go and work with the standby. Okay, and it's a very normal situation you have. Say for example, here you can see that downtime during failover reduced to 5 to 1000 millisecond depending upon failover. In case of power failure on active WLC, it may take 350 to 500 millisecond. In case of network failure, it can take up to few seconds. And we have the SSO support for these models: 3504, 5500, 7500, 8500, and Wisdom 2. You can group these WLC, how you can make primary, secondary, and tertiary part of one group. For that, you can go to the high availability section. There you can see that you have the backup primary controller IP, backup primary controller name, because everything we are going to do via the GUI. So it's actually very easy to create the or have the redundancy from the main or the active configuration GUI dashboard. And here you can see that you have the redundant port that you can go and connect these redundant port for SSO. And again, we have 13504 pairing device. So pair of devices, here you can see you have two devices, and you can see the RP ports where you can go and pair or make this as a part of redundancy. All right, so these are the things related to redundancy of WLC. I hope you understand up to this point, because next section again we have some summary slides, 2-3 summary slides, and then we'll move to other section. So let's just stop here. In 1.3, we have to understand the on-prem versus the over-the-cloud deployment. And actually nowadays it's very popular term that you have something on-prem, you have something over the cloud, or you have mix of both. So you are using on-prem and then you are using multiple cloud. Now we have three main player at this point of time when we are talking about the cloud service provider. We have Amazon, one of the major stakeholder for cloud services. We have Azure from Microsoft, and then we have Google as well. Google is also gaining popularity, and then they have done a huge investment in the cloud domain. Now let's just start this section and try to understand that how these terms fit together when we are talking about on-prem and over the cloud deployment. So when we are talking about hybrid cloud networking, here you can see that means that you have on-prem and you have a single public cloud provider. When we are talking about multi-cloud networking, then you have on-prem and you have multiple cloud providers. Correct? Now, what type of terms we are going to use? Um, Overall, if you see that how the technology fits in, actually it is simple, and that's the reason that AWS and other cloud service provider they have gained their popularity. So it's simple to implement and it's very easy to use and it's highly available. So these are the key pillars upon which these services depends upon. Now, for example, I'll skip this slide. I'll come back to this slide. So for example, I'll show you an example here. So now I have my private network, and inside that private network, I have one virtual router or maybe physical router. This router, I am creating gateway with Google VPN. It may be AWS gateway, it may be Azure gateway. Everywhere you have same type of feature and capability. Maybe the name and the terminologies will get changed. So then you can see that I can reach to the cloud, Google Cloud router, and this can work as a gateway for the application that is hosting behind this router. Correct? So you have multiple application hosted here, and those application have gateway as a cloud router. Then I have the VPN connectivity in between public and the private cloud, and then maybe I have a user hosted behind this public private network. Okay, so this way actually the flow will work for all the cloud providers. So let's try to understand these terms. So obviously you want to create the IPsec or IKE version 2 or IKE version 2, 1 and 2. So I think 2 and 2 twice, but yeah, you have option. Some of the cloud provider, they are supporting version 1, some of them are supporting version 2. You have SSL, you have PKI infrastructure. Then routing, it is supporting a static BGP, OSPF, EIGRP as a IGP. So you have to redistribute IGP to BGP. BGP is one of the standard protocol, and BGP is used everywhere. We have the tunneling methodology as well, like IPsec tunnel mode, GRE, MGRE, MPLS, etc. So bottom line is that whatever things that we have learned in Cisco, whatever technology that we have learned in Cisco, the same way these cloud provider they also uh, programmed, or in the same way they have written their code so they can connect either with Cisco or Juniper or any third party or any networking domain companies. Correct? Because any of the companies they can use the cloud hosted applications, not only Cisco. Correct? All right. So these are the terms that are going to be used, and when you create the tunnel in between your private and the public cloud, obviously you have the VPN gateway one place, you have the VPN gateway at the cloud side, and then you can form the tunnel. For routing purpose, you have BGP who can take all the routes from one place to other place. If you want to learn more about this Google, GCP, AWS, and Azure, so these are the links that you can go and verify. Now, why we are using multi-cloud or multiple cloud? Because obviously different, if you are use different vendors, so they have their own availability. If one of the vendor go down, is still the other vendor is up and running. So the reason is high availability. We have all these actually cloud providers, they have some unique features in them. So we can use one feature from one cloud provider, other main core feature from other cloud provider, and we can mix and match our requirement as a customer. Correct. And then per project service requirement, again, this depends upon the service. Now, when we are extending the private network to the public domain or private cloud, say for example, at this point of time to the public cloud, then Cisco has their cloud service router, and obviously they have the compute requirement, so they have the route process, and along with other services it can be installed over ESXi. Here you can see the list of the minimum requirement. So for example, performance elasticity available licenses, we have 10 Mbps to 10 Gbps. We have the CPU footprint, one virtual CPU to 8 virtual CPU, and the licenses. So you can install the CSR over any of these compute. Once you install this, then you can form the tunnel from your private to the public network. And here you have the list of all the dashboard of different type of cloud provider. Most of the cloud provider trainings are having very less cost, or it's free. You can create your, at least you can create the account over any of these cloud provider, and you can go and check the features. So for example, I can go and open Amazon aws.amazon.com. I'll get the dashboard, and from that dashboard I can go and check n number of features they are providing. So you want to do compute, you want to do networking, security, storage, there are n number of things all different cloud vendors are providing. Now, how this topology look like? Again, private network extending to public network. I'm using BGP as a overlay protocol. I have tunnel in between my private network to public network, obviously for security sake. And then even you can see that I can redistribute IGP over eBGP. BGP will carry those prefixes till the Google Cloud, and then it will reach to the gateway router, and then it will reach to the applications. Correct. Now, in case of physical routers, that capability is also there. So I can create the IPsec tunnel between the physical router to the Google VPN, and then it will reach to the Google router. And then same way, they can exchange the routes as well. All right, so let's just stop here, and next section will continue from here. In 1.3, we have to understand the on-prem versus the over-the-cloud deployment. And actually nowadays it's very popular term that you have something on-prem, you have something over the cloud, or you have mix of both. So you are using on-prem and then you are using multiple cloud. Now we have three main player at this point of time when we are talking about the cloud service provider. We have Amazon, one of the major stakeholder for cloud services. We have Azure from Microsoft, and then we have Google as well. Google is also gaining popularity, and then they have done a huge investment in the cloud domain. Now, let's just start this section and try to understand that how these terms fit together when we are talking about on-prem and over the cloud deployment. So when we are talking about hybrid cloud networking, here you can see that means that you have on-prem and you have a single public cloud provider. When we are talking about multi-cloud networking, then you have on-prem and you have multiple cloud providers. Correct? Now, what type of terms we are going to use? Um, Overall, if you see that how the technology fits in, actually, it is simple, and that's the reason that AWS and other cloud service provider they have gained their popularity. So it's simple to implement, and it's very easy to use, and it's highly available. So these are the key pillars upon which these services depends upon. Now, for example, I'll skip this slide. I'll come back to this slide. So, for example, I'll show you an example here. So now I have my private network, and inside that private network, I have one virtual router or maybe physical router. This router I am creating gateway with Google VPN. It may be AWS gateway, it may be Azure gateway. Everywhere you have same type of feature and capability. Maybe the name and the terminologies will get changed. So then you can see that I can reach to the Google Cloud router, and this can work as a gateway for the application that is hosting behind this router. Correct. So you have multiple application hosted here, and those application have gateway as a cloud router. Then I have the VPN connectivity in between public and the private cloud, and then maybe I have a user hosted behind this private network. Okay, so this way actually the flow will work for all the cloud providers. So let's try to understand these terms. So obviously you want to create the IPsec or IKE version 2 or IKE version 2, 1 and 2. So I think 2 and 2 twice, but yeah, you have option. Some of the cloud provider, they are supporting version 1, some of them are supporting version 2. You have SSL, you have PKI infrastructure. Then routing, it is supporting a static BGP, OSPF, EIGRP as a IGP. So you have to redistribute IGP to BGP. BGP is one of the standard protocol, and BGP is used everywhere. We have the tunneling methodology as well, like IPsec tunnel mode, GRE, MGRE, MPLS, etc. So bottom line is that whatever things that we have learned in Cisco, whatever technology that we have learned in Cisco, the same way these cloud provider, they also uh, programmed or in the same way they have written their code, so they can connect either with Cisco or Juniper or any third party or any networking domain companies. Correct, because any of the companies, they can use the cloud hosted applications, not only Cisco. Correct. All right, so these are the terms that are going to be used, and when you create the tunnel in between your private and the public cloud, obviously you have the VPN gateway one place, you have the VPN gateway at the cloud side, and then you can form the tunnel. For routing purpose, you have BGP who can take all the routes from one place to other place. If you want to learn more about this Google, GCP, AWS, and Azure, so these are the links that you can go and verify. Now, why we are using multi-cloud or multiple cloud? Because obviously different, if you are use different vendors, so they have their own availability. If one of the vendor go down, still the other vendor is up and running. So the reason is high availability. We have all these actually cloud providers, they have some unique features in them, so we can use one feature from one cloud provider, other main core feature from other cloud provider, and we can mix and match our requirement as a customer. Correct. And then per project service requirement, again this depends upon the service. Now when we are extending the private network to the public domain or private cloud, say for example at this point of time to the public cloud, then Cisco has their cloud service router, and obviously they have the compute requirement, so they have the route process, and along with other services it can be installed over ESXi. Here you can see the list of the minimum requirement. So for example, performance elasticity available licenses, we have 10 Mbps to 10 Gbps. We have the CPU footprint, one virtual CPU to 8 virtual CPU, and the licenses. So you can install the CSR over any of these compute. Once you install this, then you can form the tunnel from your private to the public network. And here you have the list of all the dashboard of different type of cloud provider. Most of the cloud provider trainings are having very less cost, or it's free. You can create your, at least you can create the account over any of these cloud provider, and you can go and check the features. So for example, I can go and open Amazon, aws.amazon.com. I'll get the dashboard, and from that dashboard I can go and check n number of features they are providing. So you want to do compute, you want to do networking, security, storage. There are n number of things. All different cloud vendors are providing. Now, how this topology look like? Again, private network extending to public network. I'm using BGP as a overlay protocol. I have tunnel in between my private network to public network, obviously for security sake. And then even you can see that I can redistribute IGP over eBGP. BGP will carry those prefixes till the Google Cloud, and then it will reach to the gateway router, and then it will reach to the applications. Correct. Now, in case of physical routers, that capability is also there. So I can create the IPsec tunnel between the physical router to the Google VPN, and then it will reach to the Google router. And then same way, they can exchange the routes as well. All right, so let's just stop here, and next section will continue from here. Let us continue our discussion and add more complexity into the design. So now we know that we can have the interconnectivity between the private network and the public network. So here you can see that your private network, you are creating IPsec tunnel. You have the IPsec IKE version 2 tunnel mode. You create a tunnel up to these VPN gateways, and these you're reaching up to these routers. These routers are actually the gateway for these virtual private cloud. These are some of the compute thing where you have hosted your applications. So these application having these gateways, and from here it is reaching to this point, and here you may have your user. Okay, so this is one of the deployment model, but we have others as well. So let's see that how DMVPN is taking role in this. Before coming to DMVPN, here we can see in the diagram that you may have interconnectivity in between clouds. So here you can see that from AWS cloud to Google Cloud, I have this VPN tunnel, and then these maybe you have the users here and you have servers here, etc., etc. There may be chances, but these compute network can communicate across the cloud as well. Now, if you want to make this arrangement a little more automated and much more meaningful, then Cisco has given the solution. We can integrate with DMVPN, dynamic multi-point VPN. Now this dynamic multi-point VPN or DMVPN, what you can do, that you can define the hub, and then you have the spokes. So here you can see you have the spokes. So this will work as a hub and a spoke methodology, and depending upon which particular phase of DMVPN you are using, it may be hub and a spoke, it may be a spoke and a spoke as well. If we are using, I think, DMVPN phase 3. Again, if you want to add much more redundancy as per your design requirement, still we have the option that we can add primary and secondary hub, and then we have the spoke. So now you can see that we have the redundancy in terms of spokes, or even for few of the spoke is primary, for few of the spoke is the primary. Like that we can do some sort of load balancing as well, and this will give us the perfect design related option. Same thing here, you can see that for one of the cloud, he is, or the first router is the gateway. For other cloud, the other router is the gateway, but they are working as a primary and secondary. Now at this point of time, you may be thinking that then what is the role of SD-WAN when we are integrating our existing WAN with the cloud? Now role here is that you should go at this point of time and can search SD-WAN infra as a service. In that case, even this is much more automated. You can go to vManage. You can have your uh, images. Obviously, you need the images to spin up. Even from vManage, we can manage the ISR as well. We have the virtual edge as well. We have ISR virtual as well. So you can manage n number of devices. You can create the template for those devices, and then you can push the configuration from vManage to the edge devices. Not only you can track the on-prem devices, but you can track the devices that will be installed inside the cloud. Okay, and that's the true power we have when we are using the uh, vManage to manage such type of requirement. So it will give you great visibility, and the use of access or ease of access, or the ease you can access the network and monitor the network, it's really amazing. So you can go and check that how we can achieve the same target with help of vManage. Obviously, the way of doing things will be different, but we are going to achieve the same target in much more simpler way if we are using the SD-WAN and then we are integrating with the cloud. Let us start with section 1, where we have to understand the architecture and various component. What are the topics we have inside the section 1? First of all, we are going to discuss about the architecture and component. Then we have to understand the components of the controllers. We have the orchestration plane, management plane, controller plane or control plane. Then we have the data plane devices. Inside data plane device, we have various things like what is TLOC, how they are forming the IPsec tunnel, what is Viptela route, what is the BFT, bidirectional forward detection. Now there are some common terms that we are going to use. So in terms of data plane device, we have vEdge or Viptela Edge routers. We have cEdge, that is nothing but Cisco ISR/ASR routers or router. Those are nothing but SD-WAN router. Then we have the controller. We have vSmart controller, that is nothing but your control plane. We have the orchestrator plane, that is the vBond. And then we have the management plane, that is nothing but vManage. Now this small v is not virtual. This stands for Viptela, because Viptela was the parent company who has introduced SD-WAN. Now the overall solution will look like this, although this diagram will find little bit busy, but once you understand all the components and the hierarchy, then it makes sense. Now starting from the orchestrator plane or the orchestration plane, you can see that you have a couple of vBond, and those vBond are identified as a DNS or a URL. They may be inside the DMZ zone. So one of the interface is towards the private data center, or one of the interfaces towards the data center. Other interface is facing towards uh, the public interface. So you have the orchestration plane, then you can see that you have the management plane, that is nothing but vManage. It is recommended that you should have cluster of vManage, means three manage or three servers inside same cluster. Now it's actually very big, and here you can see in the slide that it can be in multi-tenant mode or dedicated, means dedicated to one customer or group of customers having multi-tenancy, or maybe one company or organization having multiple sub organizations. So any possibility will be there, but this is the management plane from where you can manage entire fabric. This is the one common place from where you can manage everything. So here you can see that from this management plane, I am managing control plane devices, plus parallelly you can push the configuration template to all the devices. Correct? All the devices in the data plane. Not only in the data plane, but in the control plane as well. So the usability of this is huge, and we'll see some of the use cases of the vManage. But vManage is there. From there, you can do the monitoring, troubleshooting, configuration. In short, everything we can do from the vManage. Then we have the control plane. That may be inside containers, or we have the VMs that you can spin up over the hypervisor. Now, recommendation for control plane that they should also be in group. So maybe you have two vSmart in one group, two other vSmart in other group, but they should have the same configuration. That means These are my control plane devices. They should have the same configuration, or they should have the common configuration. Otherwise, there may be inconsistency in the network. Now, in terms of control connection, whenever the data plane devices, they are forming the control connection, they can form the control connection with one group of VSmart as a primary, other group of VSmart as a secondary. But in any case, all the VSmart, they should have the same information. Then finally, you can see that you have the data plane devices in the bottom. So irrespective of transport, either it's internet, MPLS, or 4G, they have the IPsec tunnel among with other devices. By default, they have full mesh type of setup, means all the devices have the IPsec tunnel with all the other data plane device, correct? They can be physical, they can be virtual. Okay, so now here in the diagram, you can see if I draw it, let me try to draw the diagram so you can understand. Here you can see that this link, either this can be DTLS or TLS, and here also it can be DTLS or TLS. In vBond also you have the control connections, so vBond to VSmart, like that. I'm not drawing all the connections, but this is always, actually vBond connections are always DTLS. Now what is DTLS and TLS? TLS is nothing but your SSL, secure socket layer, plus TCP based SSL, and DTLS is nothing but your SSL plus UDP based SSL. That is nothing but your DTLS. Okay, some space, less space is there, but you can understand. Now you have a control connection like that, and then you may have the data connection or the IPsec connection. So how it will look like, let me quickly draw here the data connection as well with some other color. So now from device to device, you have the IPsec connection. By default, it will be full mesh. So here it's not in a bundle, but single. They have the IPsec connection, that is the data plane connection. So obviously the traffic will move only from one data plane device to the other data plane device, and from the control plane, that is your VSmart, you are sending the updates. The controller, that's the VSmart, they can send the update with help of OMP protocol, that is the overlay management protocol. They can use or they can send actually different type of control messages related to routing updates, security key exchange update, related to policy exchange. Okay, so that's actually the role of the controller. Now here you can see that this is the overall overview, or this is the summary of the architecture that we have inside the SD-WAN. Now why it is very interesting and important, because Cisco SD-WAN, they can scale. So here you can see, if I start from the bottom, any location, branch, co-location, cloud, any transport, satellite, internet, MPLS, 5G, LTE, any service. They can use branch security. We have cloud integrated services or security. We have the application quality experience for SaaS application, voice collaboration, cloud on ramp. Means you can integrate with any type of service in the SD-WAN. And then we have any deployment. Any deployment means on-prem, cloud, multi-tenancy, even MSPs like managed service providers, they are also offering these services. So you can say that how open and secure our network is. Open, that we can go and we are very much near to the cloud integration or we are near to the cloud. Even we can install everything over cloud as well, either it's a controller or data plane device. You can integrate with any services. It's so flexible. You can run the application over broadband or internet as well, because anyways they are forming very high level secure tunnel in between data plane devices. So adding all these points, you'll find that the SD-WAN is highly secure and desirable solution at the moment. And I think almost all the customers, they are going for SD-WAN deployment. Now, again, you can see the SD-WAN deployment architecture. You may have your branches spread across geography. You may have your physical branches. You may have your virtual branches as well. And then you can see that you can use software as a service. You can use DIA, directly use those services. The good thing about this, that whatever place you have your services or application, you can track each and everything from your vManage dashboard. So you have single GUI, single dashboard. From there you can manage or you can track all the applications. Okay, so not only you can track and manage the application, but you can do the configuration and changes, etc., etc. There's so much tunable options are there. So here you can see that software as a service, or it's a VPC, virtual private cloud, or it's enterprise controllers, or it's a private cloud. Everything, each and everything we can go and integrate with our SD-WAN fabric inside that architecture. Let us talk about the controllers. We have three different type of controller. One is the orchestration plane, that is nothing but the vBond. Management plane, that is nothing but vManage. Control plane, that is nothing but vSmart. So vBond, vManage, vSmart, or vManage, vBond, vSmart, etc., etc. Now here you can see in the bracket vBond and comma NAT and vSmart comma OMP, because actually these features are very important to understand, and we should understand these features. So for example, vSmart, vSmart is your control plane, and among vSmart, suppose if you have 2 3 vSmart, so among vSmart they are running OMP, and from vSmart to edge devices or vSmart to branch edge devices, again you have OMP. So we have overlay management protocol, that is nothing but your control plane. So for example, if your OMP is down, your control plane is down. So that's the importance we have. Let's learn one by one what are the baseline features with these controllers. Say, for example, we have the orchestration plane. What are the characteristic and what is the use of the orchestration plane is that they are used to do the secure bring up. So to bring up your Viptela fabric, first of all those devices, they are going to, or they have to go and they have to contact with the orchestration plane or the vBond. So what is happening? So suppose that's your day zero deployment and you want to deploy one of your edge device. What will happen that first of all, this edge device, they will go and contact the vBond. So let me draw here and let me try to explain. All right, so let me redraw here. So what will happen that these devices, they will go and contact first of all the vBond. Now what vBond will do, he will check what is the serial number, what is the chassis ID of the edge devices, and this edge device, they will go and check the organization name, org name of the vBond. Now once this vBond will satisfy, because they are doing some sort of whitelist modeling, they have the list of all the devices that is going to be part of the fabric. So once the vBond will be satisfied that, oh, the request I am getting is legitimate, they will form some sort of temporary, they will never form the permanent tunnel, temporary DTLS tunnel, because remember, vBond understand only DTLS. So they will form the temporary DTLS tunnel, and then he will offer this edge device what is the vManage and the vSmart IP addresses. Now next time, these guys, they will go and contact the vManage and the vSmart, and the same process will happen. vManage will go and check the serial number chassis ID of vEdge. vEdge will check the org name. That's a part of certificate. That's a part of licensing certificate. Then again, the vSmart will go and check the serial number and the chassis ID, and then the vEdge will check the org name of the vSmart. And then what will happen? What will be the end result? The end result is that the edge devices, so here let me try draw with other color, so they will form the permanent either TLS or DTLS connection. They will form the permanent connection with vManage, with vSmart, and your temporary tunnel will tear down. Okay, so here you can see the nodes. Let me try to read out the nodes here. We have the nodes that is telling that the orchestration plane is there to do the secure bring up of the all the component, securely bringing up the devices in the fabric. Orchestrate control and the management plane, first point of authentication, distribute list of vSmart and manage to the edge devices or routers, facilitate NAT traversal, require public IP, could sit behind one-to-one NAT, highly resilient, multi-tenant or single tenant. So that's the use of the orchestration plane. Its use is defined, their role is defined, and these are the main points. Now you can go and install this over the compute over ESXi or hypervisor, and here you can see some of the important point that they should internet reachable, they are doing the orchestration, they are securely bringing up the fabric. Now the next very important piece we have is the management plane. This management plane will go and integrate with third-party APIs, and it is there to do, you can see, to do day 0, day 1, day 2 operation, means all the day. You have to bring up first of all your vManage, and then you have to add vBond, vSmart. You have to do at least minimum configuration. You have to do the licensing process. Once your controllers are up and running, then only can add the data plane devices. And for that, you have to start with vManage. This is centralized provisioning. It can be multi-tenant or single tenant, where you can build the policies and template. You can do troubleshooting, monitoring, software upgrade, GUI with RBAC. It can be integrated with third-party tools for APIs and programming. This is also highly resilient. Now, this is also a software, so you can go and install the cluster over the compute, either ESXi or KVM, used for centralized management, API, configure, monitor, and management. These things then can be done via the vManage. Finally, in the controller section, you have the vSmart, that is the actual brain behind the scene. Now, with help of this particular vSmart, what you can do, that it will provide you the intelligence. So you can do app route policy, central policy, you can do any type of service insertion, chaining, whatever, all policies, IPsec key exchange, overall routing management, everything is done with help of a vSmart. That's your policy engine. That's your brain. Okay, and this is also a software, and you want to operate this vSmart uh, in a redundant manner in a group. So you can have group of 3-4 devices. You can have other group in other data center or other zone with 3-4 devices. Only thing is important that all those vSmart in a single fabric, they should have consistency. They should have same database. That's the important thing. So here you can see routing information, encryption key propagation, policy management, service chaining, traffic engineering, and so many things that we can do and achieve with respect to vSmart. All right, so that's the main thing we have with all the controllers. Next, we have the data plane device, and you'll find so many interesting things inside the SD-WAN data plane devices. Not only that, they are doing the actual movement of data within the IPsec tunnel, but whatever existing WAN features we have, say for example, we can do VRRP, we can do OSPF, we can do BGP, we can do EIGRP, etc. So all the traditional routing protocols they are supporting. We have advanced features as well, like zero touch deployment or provisioning. They have the physical plus the virtual form factor. So these things are there, that is there in the existing WAN as well, except this zero touch provisioning or plug and play options. Even plug and play option is there in the intelligent WAN or iWAN as well. But what new things we have? It can do application recognition. It's a huge feature. Now, so for example, in Viptela devices can go and they can do the application recognition. They have something inbuilt DPI, Deep Packet Inspection Engine in Viptela, that is Cosmos. Again, I'll repeat, Cosmos. In Cisco devices, we know that's very popular term as a NBAR, that is network based application recognition. Now Cisco has introduced new VM as well, and they have enhanced the NBAR. We have something called AVC as well, application visibility control, enhanced version of NBAR, you can say in other words. But yeah, you have the application recognition engine. So your devices now, the SD-WAN devices now, they can understand the application metadata like Palo Alto firewall or firepower firewalls can do, or you can say that next generation firewall, they have this capability to understand the application or recognize the application, and then as per the policy they can take the action. That's the same thing we have in the application aware routing feature. Okay, and that's one of the major advantage we have. Not only we can do the app aware routing, we can do app aware firewalling as well. Now apart from that, the edge devices and the control plane devices, that's the vSmart, they are forming the OMP session. Means we have the routing peer with my control plane devices, and then I'm exchanging all my routes. Either it's a Viptela route or TLOC route. Later on, we are going to discuss about these things like OMP, TLOC, and etc. etc. So either it's a security route or service route, it's a Viptela route or OMP route, or it's a TLOC route or next hop route. All these things you are sending to your controller. Your controller, because we are dealing with the SDN solution, your controller is working as a route reflector RR, and once they receive the route from one of the branch, they will reflect to the remaining branches, and that's the whole thing. Now if we compare this particular solution with, say for example, ACI leaf and spine, what leaf are doing, they are sending their endpoint uh, registration or their endpoint information to spine. Spine is working as a route reflector, he can reflect to everyone. Likewise, here also you can see these are your leaves. You think that these are your endpoint. These guys, whatever they are learning, they are sending to vSmart, and vSmart is reflecting to everyone. In between, the underlying protocol is OMP. And again, it's a huge OMP can carry so many things. But the overview or the top view is like that. Then obviously these are the data plane devices. So let's go and see that what are the variants we have in this data plane devices. You can see that there's a number of devices that is supporting for SD-WAN. We have enterprise network compute system, say ENCS 5100, where you can go and integrate, or we can go and deploy the SD-WAN images, the third-party firewall, load balancer, etc., etc. It's a very capable devices, and so many customers they are using ENCS devices. You can see overall throughput as well, 250 to 2 GB. As per your scale will increase, your compute, your memory, your RAM, etc., etc. increase. That means they will support more throughput. Now we have both the form factor. We have hardware, we have software. Here you can see the Viptela devices. In Viptela, you have a small end devices like VH100, then 1000, Then 2000, very much it is looking like Cisco device. Cisco maybe 1800 or 2800 type of hardware. Then here you can see that you have iOS XE image. Now this is the thing I want to explain here because I found some of the confusion around the community. Say we have SD-WAN, Cisco SD-WAN, and you have two type of operating system. One, iOS XE with something 16.10 or more, maybe 16.11. You can convert or you can upgrade the image of iOS XE. Inside iOS XE image, we have SD-WAN code written. So it will support features, SD-WAN features. But there is one native operating system that is nothing but Viptela OS. This Viptela OS, actually the evolution of this Viptela OS was due to SD-WAN. So SD-WAN was the core in the brain and then evolution happened. Now this Viptela operating system, it is coming with vEdge, Viptela Edge. But Cisco has introduced the same image you can run. Here you can see vEdge next generation ISR platform. You can use Cisco ISR platform to run Viptela OS as well. And that's a huge advantage we have with Cisco. Means you have the best operating system for SD-WAN and then you have the best hardware for branches. You can integrate both and they will do all the features, that whatever features we have in the SD-WAN and whatever features that is going to come in the SD-WAN, everything will be going to be supported. So that's the good thing we have. Okay. So apart from that, as per the scale, you can see we have the ISR. We have the ISR 4000 up to 2 Gbps speed. Then we have the aggregator routers, ASRs, that having up to 200 Gbps of speed. So if you are looking for the speed and throughput, you can go and choose your branch devices. I have few slides for edge devices. You can see 100 and 1000. How behind the scene this vEdge is looking like, very much like Cisco device. You have the management interface, you have the serial console, USB, LEDs, you have the fixed 8 gig Ethernet SFP port. Why I have added this slide? Because I want to tell you one nice thing about these hardware. These hardware, they are coming with TPM chip. Now this trusted platform module or chips, they have anti-counterfeit and secure authentication. Means what is happening, that OEM, Cisco is the OEM in this case, they are adding or they are putting the RSA keys inside this TPM chip. Those preloaded certificates or CSR, certificate signing request, they are shipped to the customer. So what customer has to do, at the moment they connect their WAN interfaces to the WAN, or they should be VPN 0. We'll talk about this later on. But at the moment you connect your interface to the WAN, they will do the auto authentication, or automatically they will get authenticated from the controller devices because you have the preloaded certificate inside the TPM chip. Now considering the fact that the edge devices, they are coming with the secure image or secure boot image, Cisco devices also coming with secure image. Cisco devices, they are using TAM module, Trusted Anchor module. I will show you this in the next slide. And the edge devices, they are using TPM. This TAM module, you can check. This is there in the UCS boxes as well. You can go and check. So how it is secure, you can see you have the anchor module that is very near to the hardware anchor, microloader, then microloader, and then bootloader check the operating system and the OS get launch. So it's like internal integrity checked by the anchor module, and then it will load up. Likewise, you can see that you have the common features between TAM and the TPM. So they are anti-tamper protection, non-volatile storage, policy and configuration. They have crypto services like key store, random number generation, and crypto image. Now all these features that you are seeing here, this is belonging to certificate plus to secure your hardware. And that's the power we have. And even the provider of SD-WAN, they have thought of all these things before putting or before giving the SD-WAN solution. So all these features we have inside the data plane devices. This is the last video in section 1.4. This is 1.4b, traditional WAN and the SD-WAN solution. Now, what exactly inside SD-WAN solution is that, so this is your existing WAN. Whatever things that you can't do in the existing WAN, or it's very difficult to do in the existing WAN, that I can go and do inside the SD-WAN. So the term is simplified solution, the scalability, inbuilt secure fabric. Those things are by default there inside the SD-WAN. That is although not there in the in the existing WAN, but you can achieve with certain number of codes. One of the major drawback we have in the existing WAN is that its visibility is not that much. And suppose if we have to create IPsec tunnel, now if you use DMVPN, that is very much the case we have inside the SD-WAN, is still that DMVPN or any type of IPsec VPN that we have, in SD-WAN you will find that it is 100% optimized. So at the moment you bring up the control plane, now the control plane, now I'm seeing that most of the customer, they are taking the control plane from Cisco. So you may have over the cloud control plane. So I have this cloud hosted, say for example, cloud hosted control plane. So my control plane burden is gone now. Now I am only worried for the data plane devices. Now these data plane devices, what are the major things they will do? They will do routing, they will form IPsec tunnel, they should do data plane policies, or they should do data policies, not data plane policy. But inside data plane policy, you have so many things actually. You can refer my SD-WAN course where I have explained this, and we have so many things to consider when we are talking about policies. But in short, what I'm telling, that what are the capabilities you have is the routing, you have the IPsec, you have the app, say for example, app aware routing, that is falling under data plane policy or data plane or data policy, etc. So routing, IPsec, data policy, and plus cloud integration. These things are the nature of SD-WAN. They are evolved with these capabilities. Although, in other hand, if you go and check the existing WAN, so you will find that for each and everything you have to write the code. So for example, if you want to form IPsec tunnel, you have to plan, and that DMVPN planning for hub and spoke and redundant DMVPN design itself is time consuming, and it should be constant throughout the devices. Correct? Means you should use some sort of a standardization for the configuration. On other hand, when you have the IGP and when you have the BGP, so those configurations should also be um, good. Although the routing capability of Cisco devices is the best, and Cisco is very good in the routing at least. They are very good in other features as well, but routing is the fundamental and core of the Cisco networking. Even Cisco is very good in switching and in data center and other domains as well. All right. So the thing is that you can do all those things, but it's restrictive. You have to write n number of line of codes. It's not that much scalable. You can integrate with API, which is very difficult. You have to uh, check what are the alternates there in the market. So you can use Ansible, Playbook, etc., to do full automation for the existing WAN, and it's a time consuming. You don't have full visibility, and its evolution is not that by default it can scale in terms of routing, security, cloud integration, etc., etc. Correct? So that's the major uh, differences we have in the existing WAN and the SD-WAN. Still, if you go and complete that SD-WAN course, you will get the complete picture of SD-WAN, because already at this point of time we know whatever network we are working is the WAN. One portion of that network is the WAN infrastructure. So we know about the WAN, and once you go and complete the SD-WAN course, then you will understand about the SD-WAN course, and then you will be at the better position to compare with the SD-WAN features with the existing WAN feature. All right, so let's stop here. Now we reach to 1.5, and in 1.5 we have to learn and understand about software defined access, SD access. The common term is DNA. Here we have to understand that what is SD access and what does it mean by control and data plane. And some of the examples also I'll add. We can uh, correlate this, or we can differentiate in a manner that what is the existing campus and then how it will look like inside the DNA or SD access. All right, so we know DNA, and what DNA is going to add value in the market is that we have the full automation engine, we have the analytic engine. Actually, we have NDP, network data analytic engines. What is happening here is, and I have explained this earlier also, that now you have management plane, you have control plane, you have data plane, and you have policy plane. Now this management plane is nothing but your DNAC engine, DNA controller. From DNA controller, you can write the policies, you can do the orchestration. It is open for the API. We have full automation support. We have full analytic engines. We can do the programming. We have the virtualization support. We'll see that. What does it mean by network virtualization? And then obviously we have this cloud integration and support as well. In short, whatever required for SDN, everything is supported in this particular module, in this particular feature. So this is nothing but the SDN type of LAN or campus area network solution. Now, why we are getting such type of enhancement in the existing campus network to the DNA is because now we have the full support from the hardware, and then we have full support from the programming as well. Full support from the hardware means now we have the programmable ASICs. So ASICs where we can write the program, they can understand the program. They have the analytics, means they can understand the analytics as well. They can understand the programming as well. We can do full automation in that. So here you can see that due to the evolution of ASIC, either it's a wired or wireless stacking, TrustSIC, SDN, they can do programming. They are flexible. Recirculation will be less. We have integrated stacking, visibility, security. Means we have mature and very extensive hardware, and that can be easily integrated with the programming. So whatever programming that we want to do, or in future we want to add it, that will be fully supported with the hardware. Generally we are using Catalyst 9000 switches for DNA. I will see that later on in this session, and I will point you to the URL where you will get the list of all the supported devices. So not only the switch, but routers, WLCs are also there for DNA. Now let's try to understand that what is fabric, because this fabric is a common term. Either it's a ACI fabric, application centric infra in a data center, or SD-WAN fabric, or DNA fabric. So everywhere you used to get the term fabric. What is fabric? Fabric is nothing but the overlay. So that means we have underlay as well, and the answer is yes. We have underlay and then we have overlay. So whatever connectivity, whatever physical connectivity you have, that is nothing but your underlay, correct? And then if you abstract this physical connectivity as per your networking, as per your topology, that will be the overlay. And different abstraction can be different virtual network or tenant. So tenant 1, tenant 2, tenant 3, these tenants are nothing behind the scene, they are the overlay or instances of the physical infrastructure or the abstractions, correct? So the overlay that we are using at this point of time is not a new concept. We know that we used to use Lisp, OTV, DFA. ACI is new, but CAP, web tunnels, IPsec over DMVP, and MPLS, GRE, these are actually the old terms. So what Cisco has done nicely in DNA is that they have used the old mature technology only. So for example, Lisp and VXLAN, we are going to use inside DNA, and with that we have the SD access, this DNA, a campus area network, that is software defined access network. Again, we have some slides that just to differentiate inside the underlay and overlay. So with one particular fixed underlay, you may have multiple overlay. So you can create overlay for tenant 1, tenant 2, tenant 3, or customer 1, 2, 3, etc., etc. Correct? And that's the true power you have. So now you have fixed your physical devices and connections and interfaces and wiring, and then you can abstract that. Now, if you do this uh, overlay, or if you are in the fabric, then what features you have? You can do the mobility, scalability, programming. Now you have all sort of flexibility with you, correct? Again, one more example with the overlay, and this is actually specific to the DNA. In upcoming session, we'll go and learn about DNA terminology, and then you will find that you have terminology used, say for example, edge devices. So you have edge devices, then you will go and learn that you have the border devices as well. You have edge devices, border devices, and then edge devices and the border devices. Then again, we'll see in upcoming slides other terminologies as well that you can abstract inside the overlay. So you may have multiple overlay with the fixed underlay. So you have underlay and then you have overlay. For underlay also you have the control plane, overlay also you have the control plane. Just an example, underlay control plane may be VXLAN, overlay control plane may be Lisp. Okay, we're going to discuss about Lisp also in the upcoming session. Maybe after this, we have session for Lisp. Even if you go and check the syllabus, you'll find that section 2.3 is for VXLAN and Lisp. So after this section, when you go and start your section 2, that is for virtualization, there you will find the topics related to VXLAN and the Lisp as well. Now there is some uh, best of both in the world. So L3 and L2 overlay examples, and VXLAN you can think as a, even VXLAN is used for L2 and L3 as well. But at this point of time, you can think that VXLAN can be used as a L2, and then Lisp can be used as a L3. Although VXLAN can be used for both, generally it is used as a L3 overlay, is VXLAN. All right, so what type of planes we have? We have control plane, we have data plane, and we have policy plane. And one by one, we are going to learn actually in section 2.3. I think A and B, you can go and refer. We have VXLAN and Lisp. And then you have the policy plane. These are the key components of SD access or DNA. The differences: L2 plus L3 overlay versus L2 or L3 overlay, host mobility with Anycast gateway, VRF and SGT. We have topic related to VRF as well in section 2 in the virtualization, virtual tunnel endpoints, no topology limitation. Why, if we have any limitation not in DNA? Because we are going to use the scalability method with respect to Lisp, locator separation protocol or locator ID a separation protocol. We'll see that. We have complete things related to that. We are going to check that. So what are the terms we have in DNA? You have control plane, that is the Lisp map server. You will find this term MSMR, map server and map resolver. Then you have the edge node, they are Lisp tunnel router. So XTR, it may be inward and outward. We'll see that. So you have tunnel router as a edge node, and then you have proxy tunnel router PTR as a border node. I will go and refer this topology. And then we have the intermediate nodes as well. These terms we are going to use so many times in the DNA. So fabric domain is FT, that is the Lisp process. Virtual network, we have the VN or the VRF. We are going to check this, and these are the loose term. So VN is the loose term for Lisp instance, is the loose term for VRF. Endpoint ID group or EIG is a segment that can be used inside the TrustSec that we can check. Host pool is the dynamic endpoint ID or VLAN plus the IP subnet. So these are the terms actually are going to be used inside the DNA. All right, so I hope you understand that's overall DNA term. At least three planes are there. Three things are there: Lisp as a control plane, VXLAN as a data plane, and ICE actually is for policy plane. This is the last recording in section 1.5, and we are going to study about which type of devices supported inside DNA. Plus, I'm going to do the summary as well for section 1.5. We know that we have three variant. We have the edge node supported devices here you can see, and we can go and check the data sheet as well, which is the hardware and which is the software supported for DNA as edge node. Then we have the border node. Here you can see that 3K, 6K, ASR 1K, ISR 4K, Nexus 7K, they are supported as a border node. Again, these are the old iOS XE and iOS images. We can go and check the latest image, latest plus the stable image for SD access. And finally, we have the control plane devices as well. So we have the Catalyst 3K, 3850, 6K, 6800, and ASR 1K and ISR 4K. You can see here that in the border node and the control plane node, devices are common as well. So there are devices, they can work as a border and they can work as a control plane node as well, that will be there in the fabric. Now if you want to check the new and the latest number of devices and how many devices are supported, you can go and check this particular link. There you will get the Excel sheet, and in that you will get so many supported devices with different product ID, different devices and their hardware capabilities as well. If you want, you have to go and check the data sheet. All right, so let's summarize that what we have a study. We know that we have the management plane, we have the control plane, we have the data plane, we have policy plane, and we have the WLC as well. So in the DNA or SD access, what are the key components we have? We have the DNAC server who can do the automation, assurance, plus management, correct? Because he has a full visibility, because the telemetry is supported inside this, so that's why he has the full visibility. He can do management, automation, and the assurance. That policy plane is ICE, so we can create Pixie grid feature and the ICE. So from ICE they can send the input to the DNA center, all the contextual information, and DNA center can analyze those and then it can give the output. But the policy plane is ICE. Then we have the edge node here. You can see the edge devices where you have EID connected, endpoint identifiers, and then those will be registered inside the control plane nodes. Then we have the border node to do the communication with non-Lisp environment. We have the wireless controllers. The APs are not shown here in the diagram, but yeah, APs and wireless controller, they can use Fabric to build the tunnel to do the communication. So this is the overall picture of the DNA, where you have single unified fabric that will be controlled and managed from the DNA center or the DNAC. Okay, and finally, this is the overall thing that we want to achieve. So we want to do the we want to achieve actually virtual network, or we want to achieve the overlay. Beginning of this section, we have discussed that yeah, you have fabric, you have underlay, fixed hardware, and then you can abstract that as a virtual network or the overlay or tenant. So here you can see that you have the fixed hardware connection, where you have the border node, edge node, intermediate nodes, etc. And then you have multiple instance as a virtual network A, virtual network B, virtual network C, up to N, etc. Okay, and that's the overall goal we have with the fabric, and this is the thing that we can achieve with SD access or DNA. 1.6 is again important section where we have to learn about quality of service, both related to wired and wireless. Apart from that, we are going to discuss about QoS components and the policy in detail as well. Now, why we need quality of service? We know that if we have congestion, if we have bandwidth issue, at that point of time you need QoS. Even if you have bandwidth issue and still you need QoS, means if you have sufficient bandwidth and still you need QoS, because how you're classifying the traffic and which traffic you're giving the priority, that's important. In the next slide, I can show you here. So here you can see that there are chances that you have uh, high sender, slow receiver, and vice versa. So at that point of time, you need a quality of service. Suppose you have 10 gig, 10 gig. So let me highlight here. Two interfaces with 10 gig, and then here you have uh, only one link with 10 gig. So suppose 10 plus 10 become 20. So with 20 Mbps or 20 gig, you are sending the traffic, but the receiver having a speed only of 10 gig or maybe 10 Mbps. So in that case, you have 2:1 of oversubscription, and this is the classical case of high sender and slow receiver. Obviously, in that case, although whatever speed or bandwidth you have, still you have to categorize the traffic, classify the traffic, and then you have to map with the certain hardware queues inside different type of Cisco platform. So why we need QoS? Because the primary role of QoS is to manage the packet loss. There are traffic, they are very much delay sensitive. So if much more delay and congestion there to deliver the packet, uh, they will lose their meaning, and it's actually very difficult for those packets to do the reassembly. So first thing is that manage the packet loss. The second thing is that obviously the end-to-end delivery should happen, and for that you have trust, classify, and the policing. In this section, we are going to learn uh, all these things with respect to all the hardware. Now, when I am talking about all the hardware, we'll see in the next slide that which type of hardware it is expected to learn about QoS. Before going there, we should know our tool. So we should know the hardware we are going to work on, what is the CLI command or the GUI command, or what is the software or syntax, what is the global setting to that hardware, what will be the default setting to that hardware, where you want to set the trust boundary, where you want to apply the QoS, either it's a physical or logical interfaces. You should understand this NBAR, network-based application recognition protocol. This is not very new thing, but Cisco has done so much innovation inside NBAR, and now this NBAR along with DPI, Deep Packet Inspection Engine, they are working inside SD-WAN images or SD-WAN devices as well. So for example, Cisco ISR, they have NBAR 2, so they can do deep packet inspection. Somehow they come to know about the metadata of the protocol, and according to that metadata protocol, inline. So packet, when it is coming to the ingress, going to the egress, at that point of time you can go and apply app route policies and different type of policies as well. So nvar is important, who is going to do the uh, application discovery. Once you discover the application, then you can apply the policy for that, and the apply policy either ingress and egress as per requirement. Now let's quickly see that what type of hardware we have in this. Um, we have hardware 2960, 3560, 3750. They are very much similar type of hardware, and by default QoS is disabled. You have to go and write a code MLS QoS. Then the QoS will get kicked. It will get a start. MLS is nothing but multi-layer switch QoS, MLS QoS. Okay, so here you can see this is one type of hardware. Now the second type of hardware you have is 3650, 3850, where you can go and use modular QoS CLI command. Modular QoS is very much iOS XE images are using. Even the Cisco routers are also using MQoS format of QoS or syntax. QoS is enabled by default. You can go and allow this, means apply this QoS. Okay, we'll see later on that what are the syntax and what are the queues, etc., etc. Then you have 5006800 modular chassis switch. Again, you can see, so here you have MLS, here you have MQC, and then in these chassis you have C3PL, Cisco Common Classification Policy Language QoS. Now here you can see that QoS is enabled by default in SUP2T, Supervisor Engine 2T, and 6T, disabled on by default on SUP720. So even the common hardware is still different. Supervisor engines has different type of setting, and that's the thing, that when you're using QoS, you have to learn the QoS for all different type of hardwares. Okay, all ports are trusted at layer 2 and layer 3 by default. C3PL presents queuing policy similar to MQC. The good thing is this, that C3PL and MQC format will be similar. Only difference is there that you have to use the type of policy. Likewise, we have Nexus 7K 7700 Nexus, where QoS is enabled by default. All ports are trusted at layer 2 and layer 3 by default. NXOX queuing policy similar to MQC, but as defined type and with default class names. So again, here also you have to learn the QoS policy syntax. Different hardware, different type, different way to write the policy. Good thing is that MQC is very much common for all the platform except the access layer type of switch like 2960, 3560, and 3750. Now let's quickly discuss about the trust boundary, where you want to put the trust boundary. And when we are talking about QoS, remember that you have layer 2 QoS, that is class of service. You have layer 3 QoS, that may be type of service, and we'll see that how we are going to map costs with DSCP, layer 3 DSCP marking bit. Okay. So here in the diagram, you can see that you can set the trust boundary for Cisco phone, for telepresent system, IP camera, media player. Your trust boundary may be at the level of switch also, or you're not using any type of trust. So that's one thing, that you can go and use the trust boundaries for QoS configuration. Suppose if you want to map your COS to QoS, so here you can see that you have 8 COS and then you are mapping with 64 DSCP bit. Now in very easy term, how it is that actually you have 8 bit, and let me try to write, say 1, 2, 3, 4, 5, 6, 7, 8. Now last two you can reserve as ECN, explicit congestion notification. Then first these three, and again you have to count from here. So these three you can think as that can be used for DSCP, or actually there are complete list of AF, assured forwarding, and hence. Then you have the first three bit, actually those are used for COS, class of service. So that means you have 000, 001 up to 111. So that's why the number will be from 0 to 8, because these you can read as 2 to the power 1, 2 to the power 2, and 2 to the power 3. So 1, 2, 3, like that. So binary to the decimal conversion, etc. So that's why here you can see that you have COS bit like this, and then you are mapping with the DSCP, and inside DSCP you have 64 values. You can map like this. Now again you have to understand, and that will come with experience, that which is your high priority traffic, which is your low priority traffic, mid priority traffic, default traffic, etc. So when we are using COS 0, generally the COS 0 marking will be for default. If you have high priority traffic, so here you can see that you have high priority traffic where you are using COS 6 and 7. These are for control plane traffic. These are for network control traffic. So for example, OSPF is there, or STP is there, or any type of control message exchange. These queues, even these are reserved for that. Then you have EF, explicit forwarding. This EF, or expedite forwarding, these EF are for voice type of traffic. Then you can have this is, say for example, high priority traffic, mid traffic, and default. Like that you should categorize all these things. But never mind, we have the slides in the upcoming session that we are going to discuss about that. Here again you can have the trust boundary, and boundary doesn't mean that you are going to apply the policy at that point of time. So you have trust boundary here to mark the packet for the VoIP or for IP phone. Now for this particular IP phone, the policy may apply it at switch level, it may apply to the router level. This PEP is nothing but policy enforcement points. So it doesn't mean that if your trust boundary is there, you are going to apply the QoS policy at the same point. You can change the policy enforcement. Now, when you are applying the QoS, here you can see that you can apply per port QoS, you can apply per VLAN QoS. When you apply per VLAN QoS, whatever interfaces inside that VLAN, that will come into the picture. Correct? So policy map is applied to the logical VLAN interface. You can go to the VLAN, you can apply service policy input marking, and then you have, because suppose if this is 2960 switch, so you have to go and use this command mlsqs VLAN west for all the interfaces, and then over the VLAN you are going to, or you are applying the policy. Now if it is per port QoS, so you can go to all the ports and then you can apply the QoS service policy input marking. Correct? So these are the starting point of QoS. In upcoming session, we are going to learn more and more about QoS. Before winding the session, I have given one extra slide here for N bar. N bar, they are using UADP chip. This is nothing but the ASIC, and due to this ASIC, we have that much capability to understand the metadata, or to understand 1400 plus applications. So with help of this unified access data plane chip, if we are capable to understand the application, and once we are able to understand the application, then we can create and put the policies. Correct? Everyone knows that Cisco is one of the best company who's making high quality hardware, and N-bar 2 embedded inside the hardware, providing very nice application recognition features. All right, so this is it for the introductory session. Let's stop here, and in next section we are continuing from here. Let us discuss about QoS design and implementation for these hardwares or for these platforms. So we are going to start with 2960 and we'll see the QoS design. Later on, we are going to discuss about remaining hardwares and platforms and design. Before starting anything, we should understand this chart, because all the time you are going to get too many things actually. You are going to get different type of code words, say for example COS, DSCP, TOS, AF, IPP, IP precedence, CS, class selector, drop probability, and ECN, explicit congestion notification. Now I already told you that you have to focus on 8 bit. So 1, 2, 3, 4, 5, 6, 7, 8. Last two you can exclude because they are used for ECN, explicit congestion notification, but these 6 you can consider. So now if you see this particular table here in your right hand side, from here you can easily figure out that what is the cost value and how we are going to map with the cost to DSCP. Again, this particular diagram and slide actually is important. First of all, we have the category of application from high priority to low priority. So here you have high priority and then you have low priority traffic, correct? So you have routing and control. So for example, control information, or you have control packet. For that you are giving class selector 7 and class selector 6. Now the first column that you are seeing is COS, class of service or IP precedence. Starting from 0 going to 7, that means we have 8 option. So here the option number 8, that is 7, and option number 7, that is 6. So 7 and option 8 is for the control traffic. You can think for this point of time that is reserved. That is reserved for the system, correct? Then you have high priority real-time traffic. Oops, let me clean this. So we have the high priority real-time traffic, and for that high priority real-time traffic, we should go and classify and do the marking. So let me go back. So again, you can see in this particular chart that you have class selector 5 EF, that is for voice. Likewise, class selector 4 and then AF, assured forwarding 41, 42, 43. So 41, 42, 43 means these are the high priority. So actually this chart is from high priority to low priority traffic. Likewise, you have the streaming video, mission critical, call signaling, class selector 3 starting from 31 to 33. Likewise, you can read this. Now, if you want to convert this in terms of bit, so here you have to go and check the bit. What you can do here, that here you can see that you have the DSCP. So obviously the first one is the default, so everything is 0. But the second one, that is the scavenger traffic, CS1, class selector 1. Again, you can see that one is for class selector 1, AF11, AF12, AF13. 8, 10, 12, 14. How you are getting this number? So you are getting this number starting from bit 3. So 1, 2, 3, 4. That means this is 2. It will start like this: 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. And since these bits are 0, 0, 0, so that's the reason you have 2 to the power 3 means 2 into 2 into 2, 4 into 2, that means 8. So that's why this is 8. Now how it is 10? 1 0 1 0, we know this binary will be 10, and then again 8 plus 4 will be 12. Likewise, suppose if you want to go and calculate this EF, how is this EF is 46. So that calculation here you can see that you have starting from here, 1 0 1 1 1 0. So that means you have leave this. So you have 2 4 8 16 32. You are not taking this 16, so if you add this, 32 plus 8 is 40, 40 plus 4, 44 plus 2, 46. Like that you can check this, correct? This is the maths. uh, you can pause the recording here and you complete this mathematics. Otherwise, whenever you want to write the code, you can go and take the snapshot of this particular slide and you can refer it all the time, correct? Or you can make your own slide like this as well. All right. What is the best practice? The best practice for QoS is that if you have QoS in hardware and software, you prefer QoS in hardware. First thing. Second thing, classify and mark application as close to their source. So do the classification and marking nearby the source, because it is easy to classify and mark nearby the source. You polish unwanted traffic, and if it is unwanted traffic, put into the default queue. Then enable queuing policy at every node with the potential for congestion. If you see that congestion is there, you can go and enable the queuing. Correct. So very straightforward. Suppose if you are seeing congestion on all these three switches, you can go and enable that QoS there. Now this slide you can see that you have trusted port. So all these yellow color are trusted. Then you have conditional trusted endpoints. So you have IP camera or IP phone, etc. Those are the conditional trusted endpoint. And then you have printer you don't want to trust. Okay, so you can classify, you can mark in terms of trusted or untrusted. Here also, here you can see that you can have yellow ones as trusted, then black one is not trusted, then green is conditional, and then this red one is the classification and marking. So what is the summary for these things is that you should know that where you have to trust, where you have to do classification and marking, where you have to apply the QoS policy, either ingress or the egress. Correct? Now suppose if you are dealing with the hardware type of QoS, and that QoS type with that particular switch model is 1P, 1P stands for priority, 3Q and 1 threshold. So in that case, you have one priority queue and you have three queue. So priority queue, obviously you are going to put the voice traffic or real-time traffic, and then you have three queue. In these three queue, you can go and classify your traffic. We'll see that in upcoming 3-4 slides. You'll see that how it can be utilized. So again, here you can see it's just next after this. We have, so for example, one priority queue, 3Q and 3T. Now this example is for one threshold, but here we have the three threshold values, and that's why you can see T1, T2, T3. So all the queues you have three threshold. Anyways, whatever number of thresholds you have with the queue, that is not a big thing. How you can apply this? Here you can see that you have the classification of traffic. So that's fixed thing you have, classification of traffic for a scavenger, for bulk, for network management, for transactional data. Remember, this thing again mapped with QoS, how it is. So here you can see that scavenger, bulk data, you have CS1, AF11, 1213, low priority to the high priority, and a related DSCP marking or DSCP table is 8, 10, 12, and 14. Okay, so while you are doing this, you should know the calculation. So for example, this is say low priority to high priority in this diagram, and in the last diagram that is up, actually this is low priority up to high priority down, and here it is a high priority up to low priority down. Okay, all right. So now here you can see that you have different classes, obviously you have one priority queue. So let me show you that which particular category is falling inside priority queue. EF, CS5, CS4. Now here you can see that where is your EF is VoIP, CS5 is broadcast traffic, and then CS4, here you can see CS4 is real-time traffic. So these traffic are falling inside this. Then you have three queue. So you have queue number 2, I can see queue number 2 here. You have queue number 4, and suppose you are using one queue as a default queue. Okay, so this is your queue number 3. So I have Q2, Q3, and Q4. Now Q2, I'm using CS2 up to CS7. Now again, it depends that inside Q2 you are putting threshold 3 as CS7, CS6, and then CS3 as the threshold 2, and rest of the AF assured forwarding 2, 3, 4 inside Q2 T1. Then Q3 you are using 35% as a default, and then finally you have Q4 you are using as AF4 and CS1. Now AF1 and CS1, you can go and check. This is used for scavenger. So I am giving 5% of traffic to Q4 for default traffic or for scavenger. AF1, here you can see the bulk data. So bulk data and scavenger, we are using 5% only. Means after that it will do the tail drop. But what is there in default queue? So here you can see that inside default queue, we have the default traffic. Default traffic I am using for default queue. So Q3 and Q4 actually is used for default and scavenger and bulk data. For that I reserve 40% of traffic. Remaining 60% of traffic we are using for Q2 and priority queue. Okay. So this is the thing that you have to design the QoS before doing the actual implementation. Now, when you are doing the implementation, we know that this is MLS, multi-layer switch queuing methodology. So you have to go and enable the queue. You have to go and enable the trust model, conditional trust, service policy model, and then you have to apply it. Correct. So we have policy map, marking, mapping table, and weighted tail drop. How it look like? The first step for 2960 series switches are that enable QoS with command MLS QoS. Then um, the good thing that you can go and use COS DSCP, or directly you can use COS as well. We know COS, we know DSCP. Both have mapping as well. So here you can see that COS mapping. If you have any doubt to understand this mapping, what you will do, you can go and check the reference slide. So where we have the reference slide, the first one here. So here you can see the COS to DSCP mapping, the column 1 and column 3, actually technically column 2 and column 4. So 0, 8, 12, 0, 8, 10, 12, 14, 16, 18, 20, 22, etc. If I go here and see, I can clearly see that 0, 8, 16, 24, 32, 46, 48, and 56. That's the marking. If you are using the DSCP model, we can simply go and use MLS QoS trust DSCP. You can go and trust different type of Cisco devices like Cisco phone, CTS, IP camera, a media player. So this is the way that you can go and do the enable the QoS and do the DSCP marking. Again, here you can see that you can go and enable the DSCP marking. Now the next phase is that you will go and enable the policy. You have to create the class map and policy map. Class map will be called inside policy map. So here you can see that I have class map called VoIP, media, signaling, transactional, bulk, and scavenger. Once I have all this class map, then I am calling this class map inside policy map one by one. So policy map VoIP set, again you can see we are setting the DSCP bit. So we are setting the DSCP EF for VoIP. We are setting for multimedia AF41, and again class signaling CS3, transactional data AF2. And when you are doing this thing mapping, then this diagram will come into the picture. So according to your classification, your marking, you have to go and apply the policy. So obviously you have the class or classification of traffic, and then you are doing the DSCP marking while you are putting the policy. Now, once I have complete policy, then I can go to the interface and then I can apply it like service policy, input marking policy, and that's it. Okay. Now it seems little bit complex if you are new to QS, but if you go a step by step that whatever we are following here, then you will find it that it's logical, and after few practice or if you do little bit of practice, you'll find that QS is a interesting interesting topic to learn and do the mastery for. In this section, we are going to discuss about 3650, 3850, and 9300 platform. Here you can see that we have the trust model, means which particular interface is connected with what type of device you want to trust and you don't want to trust, or you have any conditional trust. Now, in case of 3850 or 3650, we have these steps to follow. So when we are doing the ingress QS model, we have trust DSCP/US model, conditional trust service policy model, and finally for the egress queuing, that is the hardware queue, we have 2P, 2 priority, 6 queue, and 3 threshold. So let's understand that ingress trust model. We can go and go to the interface, and then we have the CLI command, trust device, Cisco phone, CTS, IP camera, etc. Or we can use conditional trust. Example here, you can see that you can go and create the class map, say voice, whose cost value is 5, signaling, cost value is 3, and then you can go inside the policy map called Cisco IP phone, where you can call the class whose cost is 5, and then you mark the DSCP bit as EF. Likewise, you can call the class signaling and then you can mark the DSCP as CS3. Obviously, then you have class default, set DSCP as a default. Then you can go to the interface and you can apply this policy. So we have option that which particular methodology we want to use for the classification or at least for the trust model. Now, in the upcoming slides, I'm going to show you that how you're going to create the policy and apply over the hardware queue or over the queue model that we have is 2P, 6Q, 3 threshold or 3T. We know that we have the N bar supported in these hardwares, and N bars can have 1400 plus application recognition. When we are supporting N bar, at that time how we can create the class. So I can go and use, say for example, class map voice, and then I can match the protocol. That's the keyword, match the protocol, Cisco phone, Cisco Jabber, link audio, Citrix, etc, etc. If you go there, type match protocol and question mark, you will get a long list of application that is supported to that particular platform that you can match it. Apart from that, we can go and create other classes as well. This protocol is related to NBAR. So again, you can see that you have the broadcast video, match protocol, Cisco IP phone. You have the real-time interactive, the protocol is telepresence. Call signaling, the protocol is skinny. Telepresence control, the protocol is Citrix, SA, etc, etc. Okay, so we can do the classification of the traffic with respect to N bar, and then the next phase is to call those class map inside the policy map. So I can go to policy map and then I can call the class voice. Now voice will call all these 4 protocols, and I'm setting the DSCP as EF. Likewise, we can create all this policy and then we can apply over the interface. Correct. Now N bar, which is supporting 1400 plus application, and it is supporting 12 class model, and this is one of the reference we have. So here you can see that we have class voice, broadcast video, interactive, multimedia conferencing, multimedia streaming, signaling control, management, transactional data, bulk data scavenger. So 1 2 3 4 5 6 7 8 9 10 11. And let me show you the last one as well. So while you apply inside this policy, you can see that you have class voice, video, and all up to 11, and last is the class default. Okay, so you can have protocol matching with all of these classes, and then you can go and do the DSCP marking, correct? So this is the way that we can efficiently use this N bar feature inside 3K platforms. Again, marking and policing, how we can do. So here you can see that the configuration related to marking and policing. So for example, I have class VLAN VoIP set EF, set DSCP as a EF, then police 1 to 8K, conform action transmit, exceed action drop. So what is it? What does it mean? Again, the concept of policing you'll find at each and every point. So what you can do here, that you have, say for example, B sub C, conform burst, and then you have B sub E, that is excessive burst. So what you want to do at this point of time, if you have conform action, you are doing the transmit. So you transmit it, and then you have certain buffer. Exceed action, again exceed action, you have option that you want to transmit or drop, but in this case, say for example, I'm dropping. So B sub C, transmit, and excessive burst you can drop because we are using the policing. Likewise, you have all the policies, correct? So here you can see all these policy in the list for all the class of the traffic. Then for transactional data, you can see conform action, exceed action, set DSCP transmit. DSCP table is table map, then class bulk data, and set DSCP transmit DSCP table as a table map. Then you have the table map, that is map of DSCP table, and here you can see that you are mapping 0 to 8, 10 to 8, 18 to 8, etc. Now if you see this diagram in this slide, you'll find that how it is called. So here we have the table map for 18 to 8, then you have table map for 10 to 8, and then finally you have the table map from 0 to 8. Okay, and obviously you have the class default, you have class scavenger, you have bulk data. For those you are using the table map as well. So this is the way that we can use the policing as well. Let me quickly go and show you the full policy configuration. In case of per port per VLAN policy, we have VLAN. So for example, match VLAN 110. Class map is DVLAN, that is 10. Again, you can go and call these class map inside the policy. Now what we can do, that rather using all the features that we have, we should standardize the configuration. Like we should create the class map like this, and then policy map like this, and then we should apply it. Okay, obviously if you want to do the policing, you can do the policing as well, and that's very much required as well. So let me quickly show you that how this queue look like and what will be the final configuration. Here you can see that because this is two priority, so you have priority queue 1 and priority queue 2. Then you have 1, 2, 3, 4, 5, 6. 6 queue with 3 threshold. And how we can map the traffic, this slide can be your reference slide, that how you are mapping your 2 priority and 6 queue. So for example, I have priority queue 1 and priority queue 2. Here you can see, let me try to highlight here. So here you can see that you have EF and the priority queue level 1 EF for VoIP, and then you have CS5 and CS4 for broadcast video, and then for real-time interactive. So you are using your priority queues 10% and 20% here. Then you should use your AF4. So AF4 is used for multimedia conferencing, where we are using the bandwidth remaining 10%, and then the weighted tail drop is in conjunction with both. Then we have AF3 for multimedia streaming, where bandwidth remaining percent, DSCP based weighted tail drop. You are using the tail drop, means whatever left over, it will start dropping. Then finally you have the transactional data. Then you have AF1, means you have bulk and scavenger. So like that you can use all your queues in this manner. And if you draw the configuration, how it will be looking like, so here you can see that you have voice priority Q1 matching DSCP EF. So when you are creating the class map, you are matching the DSCP value. So you have class 1, 2, 3, 4, 5, 6, 7. 7 class plus 1 is default, so you have total 8 class. Now how you are utilizing those classes? So for example, policy map, the name of policy map is this, for example. Then class priority Q1, priority level 1, percentage of bandwidth 10. Then Q2, priority level 2, percentage of bandwidth is 20. This is very much like this, correct? So once you do that, then you have the other class, that is control management queue. If you go and check, you have control management queue where you're mapping this high level class selectors. What you are doing for that, you're giving bandwidth percent remaining 10, and you are giving the buffer as well 10%. Now you are moving to the standardization. If you go at this point of time and if you check the SD-WAN quality of service configuration, you'll find they have a structured in this manner, means even better than this, because same place you are getting all those things, and even you can do the configuration with GUI as well. Then you have the conferencing queue, 10%, buffer, queue limit DSCP, remaining percent, 80%, 90%, etc. So the configuration, although here it is using the strict priority, the remaining bandwidth percent, the tail dropping, etc. So whatever you are seeing here, all the configurations, you can drill down and you can check the same way we have the configuration here. So finally for bulk data, we have bandwidth remaining percent 5, the queue buffer ratio is 10, queue limit DSCP is 80%, AF 11% is 90, means for the scavenger traffic. So when you have the scavenger traffic, you are using the DSCP based weighted tail drop, correct? So that's why you have the DSCP based weighted tail drop 80 and 90. So after that particular limit or point of time, they will start doing the tail dropping. And finally, you have this class default where you have the bandwidth percent remaining is 25%. So here you can see this bandwidth remaining percent is 25%. So this is the way you can design the uh, policy. So first of all, do the classification, then design the policy, and you can apply it. Correct. So do the classification, create the policy, and before applying, suppose if you want to use the shaping as well, so you can do a nesting of policy as well. I can go and create one parent policy for 50 Mbps traffic, and I can map inside class default shape average. I can give this particular subline CIR for shaping, and then I can call my child policy inside the parent policy, and then the parent policy I can apply over the interface. Okay, so this is the standard way of doing the MQC, modular QoS CLI configuration, or even most of the iOS XE platform. We are creating the policies and applying the policy like this only. All right, so let's stop here. Now we are going to discuss rest of the platform. We have 4500, 6500, and 7K and 7700 platform. Whatever knowledge that we have gained so far, those knowledge we are going to use in these platform. So we need not worry to relearn all those things. Now directly here you can see that in case of 4500 platform, we have, so for example, one priority, 7 queue, and one threshold. So overall we have 8 queue. Out of that, one is priority queue. And if you have 12 class model, here you have 12 classes. You can see that how these classes are mapped. So priority queue is mapped with EF, CS5 and CS4. And then here you can go and check what is CS5, what is CS4, what is EF. Likewise, then you have queue number 1, 2, 3, 4, 5, 6 and 7. So here you can see that Q1 is starting with default queue 25%, Q2 is uh, bandwidth remaining 1%, Q3 bandwidth remaining 4%, Q4 remaining 10%, 5 10%. Like that we have all the queue to class mapping, correct? So this is about the 4500 QS design. Now inside 6500 and 6800 QS design, you can see that again you have 12 class model and you have say 2 priority 6 queue, means you have 2 plus 6 queue plus you have 4 threshold. Here again you can see that Q1 up to Q6 and then 2 priority queue. So first of all you can figure out that how you are mapping priority queue level 1 and priority queue level 2. 1 and 2 we are using EF, CS4 and CS5. Then rest of the queues here have been used. Now for example AF4, which is using multimedia conferencing, it is used for multimedia conferencing queue where 20% is bandwidth remaining, and then we have a DSCP based weighted random early detection. So if you want to do congestion avoidance, you can use either tail drop or you can use a random early detection method, that you start discarding the packet before you reach to certain threshold value. In AF3 also we have 20% bandwidth remaining plus weighted random early detection. In AF2 also like same, but in case of bulk data you can use 5% of bandwidth remaining percent, because you don't want to give more bandwidth for bulk data, or maybe in case of a scavenger as well. Okay, so this is the model, this is actually the standard format, but if you want to change anything you can change as well. Okay, then finally we have the Nexus platform, and inside Nexus platform you can see that you have 4Q1T. Now this 12 class model, again you have the costs. So for example you have 8E4 4Q 8Q in 1Q1, like that. Actually if you go and log into the Nexus platform, you'll find that you have so many inbuilt QS, and it is recommended that do not change it until unless it is required. So how the mapping is, here you can see that you have Q1, you have Q2, you have Q3 and Q4. Q2 is used as a queue default, correct? So Q1 it is matching cost 567. Q0 obviously it is for default. Q3 is mapping cost 234. So if I start with cost 1, so cost 1 for Q4, and again you can check the subsequent mapping. So cost 1 is mapped with bulk data and scavenger. Best effort is mapped with cost 0, that is your default queue. Then here you can see that you have Q3 mapping with cost 2, 3 and 4. 2 is transactional data network management. 3 is, so here you can see the 3 is multimedia and signaling, and likewise all these queue have been mapped. So once we know this mapping and this queue methodology, obviously we can then go and write the syntax, write the software commands. That is again it's easy. Again here you can see that you have 4Q1T, 1T, how it is mapped here. Uh, Apart from this mapping, we are giving the bandwidth percent and the queue limit as well, bandwidth percent and queue limit as well, because we have one threshold as well. In 7700, where you have 8 queue and one threshold, it's very much that we have 6K design where you have 2 priority and 6 queue. But anyways, you have 8 queue, and how you're mapping the 8 queue. So first of all, you can go and check your priority traffic. Priority traffic is COS 5, 6, and 7 used for priority, and here you can see the COS values. Then you can see the Q2, 3, 4, 5, 6, 7, and then you have one default. All these 12 classes model, how they are mapped with Nexus 7700 F series line card. So this is the way that all these wired QoS can be used and mapped, and we have discussed a lot in detail each and every component and things inside the QoS. Now next section onward, we have to study QoS for wireless network or wireless infra as well. Last topic in section 1.6, we have WLAN QoS. Now WLAN QoS may be become the weakest link in the chain because there are some, you can see that actually there are three primary reasons for that. Means there are some issues, or there means these WLANs are not that efficient that we have the wired LAN. So that's one of the reason. So here you can see the primary reason are typical downshift in speed and throughput. uh, Here you don't have any dedicated pipe. You have some sort of shared media. Here you can see in the diagram, and all the mobile devices or devices who are using WLC, SSID, etc., they are using the shared network. One thing. The other thing here you can say that shift from full duplex to half duplex. So these are the issues. These are the constraint we have that may be causing the weakest link in the chain. The other important thing here to understand is that wireless LAN supporting four level of services. So if you have wired LAN, you have to map your, say for example, 8 class of wired LAN to 4 class of wireless LAN. So that is also one of the limitation you have. Now because the wireless media, they are going to use a CSMA CA, that is collision avoidance mechanism. So there are chances, we'll see that in upcoming slides, that you have to wait for some period of time or a small duration of time, but that is a small fraction of time also can cause trouble. So for example, voice, if we have 15 millisecond jitter versus 5 millisecond of jitter, the improvement is 300%. Say for example, transactional data, 14 millisecond latency versus 2 millisecond of latency can have 700% performance issue or enhancement in performance. Both ways we can think. So these are the things that is considered for wireless media, and for that obviously we want to apply QoS as well. What are the tools we have? We have the user priorities, and later we'll see that how we have to map DSCP to the user priority. We have access category, we have arbitration, inter frame spacing, we have contention windows. We'll see that AIFS and CW in next slide. What does it mean? But they are associated with some sort of collision avoidance mechanism. Then finally, you have enhanced distributed coordination function. We have to map the DSCP with a user profile. You can define the trust boundaries. We have discussed about policy enforcement points earlier. So you have PEPs, and obviously the WLCs, they are supporting AVC as well, application visibility and control. Now here you will understand about AIFS and contention video. Since we are using CSMA/CA, that is the collision avoidance technique, uh, if you compare with the LAN technique, that is CSMA/CD, collision detection. So if collision will happen, then the algorithm will start recalculating the refresh interval, and then next time they will avoid. But here this is by default, they will wait until they will find that the link is okay or the transmission is okay, means I can do the transmission if it's ready to send, correct? So it's something like collision avoidance, and that's the reason that the sender have to wait for fixed amount of time, and that is nothing but AIFS, correct? The other waiting time you have is the random amount of time, that is the contention window. So not only that you are waiting for fixed amount of time, but you have the contention window as well. And then finally, this AIFS and contention window timers vary by access category. So here you can see that you have access category as defined by voice, video, best effort, and background. Now this access category, you know that you have high priority to the low priority data, correct? And according to that, your access category in conjunction with AIFS, in conjunction with contention window minimum and max, everything will work together. So for example, here you can see in the diagram below, the background having the longest contention window plus the longest AIFS, rather than the voice has less contention window plus the AIFS, etc. So voice and video AIFS is same, but contention video for voice and videos are different. Let me quickly show that how these models are going to map. So you have 802.11 access category. You have access category for voice, video, best effort, and background. Likewise, wireless media mapping, you can see that you have voice, video, best effort, background. If you are using Cisco AirOS WLC, you have this category like platinum, gold, silver, and bronze. Let me show you much more information related to that. So we know and we have a study about this model. This is our RFC 4594 based DSCP based model. Now how you are going to map all these classes or traffic classes with the IEEE 802.11 model. You can have a reference for this particular slide. So in future, if you are designing the wireless QoS, you can map in the same way that you are seeing here. So for example, CS1 is mapped with UP1, AF1 is mapped with UP2, UP user priority 0 is mapped with best effort. So like that, you can go and check each and everything. Then we have the high priority data as well. So for example, multimedia conferencing or voice plus DSCP admin. So here you can see that voice plus DSCP admit is user priority 6, and this multimedia is user priority 4. So like that, the mapping should be happen. Now the next question here is that how the 3-bit user priority can map with the 6-bit DSCP. So in that case, when you have user priority to DSCP default mapping, here in the diagram you can see that you will map 3-bit and rest 3-bit will be zeroed. So they will mark as a 0. So in that way, the frame will processed, and obviously your actual header or actual DSCP marking will be kept inside the IP packet. So whenever you are marking your user priorities, that is going inside the cap web tunnel from your access point to the WLC. So here you can see the marking will be like this, and they will mark only last 3-bit. So user priority has 3-bit, that will be marked with the 3 last bit of the DSCP. Okay, and in this way the flow of frame will happen. Now, if you want to learn more about the QoS related to WLAN, you can go and check this RFC 4594, and also you have the Cisco validated design as well. So you can go and refer the design document from Cisco as well. Finally, we reached to section 1.7. This will be the last subsection actually of section 1. And what are the topics we have in 1.7? We have to understand about hardware and the software switching mechanism, how CEF, Cisco Express Forwarding working, what does it mean by TCAM, MAC addresses, and FIB versus RIB. So all these things we'll study step by step, and before coming to 1.7 A, B, and C, I just wanted to explain you about hardware architecture of 9300. Although we have a study in our QA section that in Cisco, we have long list of switching platform. Obviously, in routing platform is also there, but we have long list of products. Now, because this core exam and upcoming exams, Cisco keeping track, or they are thinking that in future people will go and in enterprise network they will use DNA, they will use SD-WAN. So when we are coming to DNA specifically, in DNA we should use DNA ready hardware, and that's the reason in the hardware section I just wanted to focus on 9300 hardware. Now this 9300 catalyst switch is security integrated, means you can enable MACsec and other security related things, means whatever there in the switch generation related to security you'll find inside 9300. It's a mobility ready, it's IoT ready, because we know that IoT is a big topic nowadays, and it's a even bigger topic in Cisco DNA, and it's ready for the cloud as well. So here you can see that you can connect with SDA, you have web UI, you have patchability, etc. So let's understand this 9300 and at least 3 to 4 very important features related to 9300. Now here you can see the family. So we have 1G data, uh, 9300 specifically. Even you can go and refer the data sheet as well. So you have 24 plus 48 port, then you have 1G unified PoE slash PoE plus 24 port, 48 ports, and then you have M gig PoE switches. So first of all, at least one thing we can understand here, that they are PoE ready, and not only they are PoE ready. So here you can see that line rate on all port. They will give you line rate throughput on all the ports. All the ports are PoE ready. So you can connect in any port you can connect the uh, IP phones or Cisco phones, so it will get the power. Then you have 24 multi-gigabit Ethernet ports. Here you can see you have 10 gig, 5 gig, 2.5, 1 gig ports available. So you can see that port availability, PoE, line rate, everything is enhanced here. Now, which type of SFP models they are supporting? Here you can see that you have uh, online insertion and removal SFP supported, like 4 into 1 SFP or SFP slash SFP plus. You have QSFP as well, that is 2 into 40. Then finally you have the copper support as well. So 4 by 1, 2.5, 5 and 10 gig. Correct. So all sort of SFP, SFP plus and copper interfaces are supported. Now here you can see that we have the power capability, means what type of power modules you have. You have 350 watt AC up to 1100 watt AC. It's very much similar to Cisco 3850 switches. And then we can do the stacking as well. So a stacking capability is also there. When you are doing the stacking of the switches, then you can stack up to 8 members in a switch, and in that case obviously when we are doing the stacking, they have active and a standby feature. So someone is active and who is taking control for all the switches, so from there you can go and log into all the switches, and from active you have to configure the active, and rest of the members are supporting the active configuration. So that means we have the centralized control plane, we have distributed data plane, and that's the power of stacking. We have one-to-one stateful redundancy, and again we have discussed this earlier, that we have a stateful switchover SSO, plus we have NSF, non-stop forwarding as well. So you have a stateful switchover, you have NSSN. Let us continue our discussion about the innovation inside Catalyst 9300. Here you can see that it is built in RFID. Uh, apart from that, apart from uh, regular catalyst switch like 3850 or any other platform, what extra you have. We are going to check and discuss about what extra capability we have inside 9300. At this point of time in the overview section, you can see that you have RFID, and I want to highlight this extra capability that we have in terms of ASIC. So here you can see, let me try to do a spotlight. We have flexible ASIC UADP 2.0, and that's the extra thing we have inside this 9300. Due to the ASIC is it's quite extensive, high performance, programmable, and it's actually amazing innovation from Cisco that this unified access data plane ASIC, we have 3-4 slides for that we are going to discuss more about this. So here you can see that you have extensible ASIC, you have RFID capability, and then you have the line rate capability. So let's move on and see that what other features you have in terms of hardware. Obviously, we have discussed about a stack, so we can have a stack of 8, and we have NSF and SSO supported. That's okay. Now let's try to dig deeper inside the switch, and let's try to understand the core difference, that where 9300 is standing and moving onwards if we are comparing with the other catalyst switching platform. So you have this UADP, rest all the things you will find same, like redundant power supply, power stack connection, fan FRU, back stack connection, USB. Rest everything is okay, but you have this UADP, that's the ASIC. Now let's discuss about this ASIC. Before moving to that ASIC, you can see that you have x86 CPU who can support different type of programming options. So they can host Puppet, Ceph, Wireshark, Ansible, iPerf, Kibana, Perf, Sonar, etc. So they have this debugging options, and they can integrate with any third-party vendor for API integration or programming. Yeah, so we are waiting for this ASIC study, and now you can see that we don't have the traditional ASIC where things are monolithic, although this new ASIC, this UADP, they can understand different type of encapsulation as well. Say in traditional ASIC, if you put load on the frame, means if you are doing some encapsulation, you have VXLAN encapsulation overhead, GRE encapsulation overhead, etc. Those are not supported because they are doing a normal lookup related to MAC, IPv4, ACL, QS, etc. But in the new UADP, you'll find that it is supporting most of the things. So here you can see that you have the architect, you have the RTL design, synthesis, floor planning, fabrication, etc. Everything is there inside this new chip, and this chip is looking like this. So you have UADP, Unified Access Data Plane, which will provide you high performance, flexibility, and programming. So we have PFP, performance, flexibility, programmability, and that's the reason that it is used inside Cisco DNA. It has investment protection, universal deployment, enhances scaling, and it can have 7.46 billion transistors. It is using 28 nm technology. This is actually very much related to the hardware features, correct? But yeah, the summary is this, that because we have very high capable data plane related ASICs, that's why the capability is very much good, and you can think this 9300 as a next generation catalyst switch. Apart from that, we have some key features that they have flex parser, programming pipelines, recirculation capability, micro engines, adaptable tables. Okay, and no compromise on performance. Although they are giving you lot of features and capability, but there is no compromise on performance. Finally, let's quickly see this architecture. So for example, we are seeing 930024 port layout. How it look like if we are new to this uh, hardware type of a structure. So how we can understand and read this? Obviously, you have IO module, input output module, means you have to give something in the input, correct? So maybe the end machine or PC, anything is connected. So let me try to mark here. So you have your PC and it is connected, or maybe you have some other switch and it is connected. So where it will be connected, obviously to the port. This is 24 ports, so 12 plus 12 port, it is divided like this. Then you have octal physical connections. So that means the ports are mapped to the octal physical. Obviously, you have the network interface. Then you have the forwarding controller, packet buffer. Now, all these things, suppose if you have a stack of switches, then you have 480G stack interface. But all these things are mapped with the ASIC, and then you have your quad core CPU, you have your flash memory, USB management console, etc., etc. So you can study, or if you want to understand this design, go from bottom to top, and then you can understand more about this. Now, quickly let me show you this multi-gig uh, Ethernet or multi-gigabit 9300, and here you can see this capability is even much more enhanced. So now you have 12 port unified PoE, and you have multi-gig quad physical, multi-gig quad physical. You have core 0 and core 1 inside ASIC. You have core 0 and core 1 inside ASIC 0 and inside ASIC 1. Obviously, these are mapping with a unified access data plane. Here you can see this overall clock cycle. Then you can see this quad core CPU 1.8 gigahertz, and then you have a rest of flash memory and USB management, etc. Okay, so these are the hardware level details of the switch platform. I have covered 9300 because that's the catalyst switch that we are looking for in upcoming networking technology, and that's the innovation we have. Next topic, we have traditional MLS, multi-layer switching, and Ceph Cisco Express forwarding. So what's the fundamental here? The fundamental here is route once and switch many. And again, if you correlate this with the SD-WAN, means you have the control plane and data plane. Control plane who will take all the decision, and then the data plane, it will forward the packet. Correct? So here also you'll find that you have the control plane called route processor or RP, and then you have the data plane, that is the switching engine, that is the SE. Route processor will take the decision, and then it will program the switching engine that now I have taken the decision, this is the source, this is the destination, and you need to forward the packets. This is the way that the forwarding will be very fast, and this is the way that the multi-layer switch or switches, they are providing the line rate speed. Correct? Now, Cisco Express forwarding, how it is working and what are the key components we have. Again, the core of Cisco Express forwarding is take the decision once, and then everyone will follow that decision. So route once means that you have the brain, and in the chassis type of architecture, the brain is the supervisor engine. So either we are using the Catalyst 6K or 4K or 4500 series switches. We have the supervisor engines who will take the decision, and then they will program the line card to forward the packet. If you have the fixed type of switch, so for example 3850, 3750, etc., so there also Ceph can be enabled in the hardware. Okay, so Ceph is the feature. Here you can see in the diagram and understand more, that will provide you the fast forwarding of the packets, because all the time the request is not going to the CPU. CPU will take the decision once, so you are punting the packet to the CPU, who is building the routing table and the ARP table, but they will program the switching engine, or they will program the line card, where you have the dynamic engine called fib, and then you have the next hop adjacency, or you have IP to next hop mapping from where the packet will move to the destination. Correct? So here in the diagram clearly you can see that the different rows of all these components. Routing table, it will build the routing table, that's the route processor, and then you have the ARP table, that's the L3 to L2 mapping that will resolve the MAC address. Now you have the dynamic entry, that's the fib table, forward information base, and that fib table will be arranged in a way that you have the longest prefix match to the lowest prefix match. That's the beauty of this fib table. And then finally, this fib, whatever information they have taken from the ARP table, so now you have IP to next hop mapping, or you know that who is your next hop agency, and then you can forward the packet as per layer 3 forwarding engine. Actually, this is the mechanism that MLS is using. So now you have different type of terms. You have routing information base who will form forwarding information base in terms of longest prefix match. So that is the LPM. And then you have the ARP table that will do the L3 to L2 mapping. And then you have the adjacency table that will be used by the FIB. Okay, so I have put all these points here. If you want to read these slides, you can read it. But whatever we are discussing, the same thing here also. Now, once you have your RIB, once you have your ARP table, once you have your FIB, once you have your agency table, if you want to verify, you can go and verify like show IP CEF. And if you want to check the CEF entries in detail, you have that detail option. So you can come to know that who is the network you are looking for if you want to check that particular network. So we have option that we can go and check the particular destination network. So for example, show IPsec prefix IP, and then if you want to check the longer prefix matches, because this fib entry or the CEF entry, they will be in a manner that they will have the longest match and then the least match. It's like that. Obviously, if you have the longest match, then only the fib entry, that will be the natural choice for the fib entry, that you have to check the next hop for the longest match, correct? All right, so in this way, this fib entry will come into the picture, and when you check the fib entry, you can see that you have multiple next hop like attached or in the same network in the other network. Again, it depends that who exactly is your next hop. According to that, they will build the table entry. Now, again, if you want to see this in detail, so you can go and check show IPsec, the network and detail, where you will go and get the detailed information about the agency, about the next hop, dependencies, etc. Okay. Now the next important thing we have is the agency table. So we know at this point of time that you have the fixed components. So for example, RIB table, and then you have the ARP table. Now you have the dynamic entry as per the longest match, that is the fib table, and then you have the agency table. Now this agency table obviously will be taken from the ARP table. So ARP is doing L3 to L2 mapping, and then when fib they are looking for their next hop entry, they are contacting the adjacency table, and then as per the longest match, they can get the next hop. Okay. So that's the thing we have, that's the important we have in the agency table, but there are so many other stuffs as well inside the agency table. If you want to check that, you have this option show agency table. You can go and check that. You have the summary and detail option as well. The agency table will be look like this. So first, you can see that first few numbers belonging to MAC address, and then rest of the keywords are there. But what is important there in the agency table is to understand a different type of keywords. So while you are checking your agency table, you will find that you have null agency. Now, what does it mean by null adjacency is that used to switch packet destined for null interfaces. The null interfaces always is defined on a router or switch. It represents a logical interface that silently observes packet without actually forwarding it. So you may have null interfaces. They are not actively forwarding the packet from one place to other places, but they are silently uh, absorbing the packet. Then you have the drop agency. Obviously, drop agency, as name suggests, that they are going to drop the packet, and the reason may be you have encapsulation failure, unresolved address, unsupported protocols, no valid route presents, no valid agency, you have checksum error, etc. Now, if you want to go and check this drop agency, you have this option. You can go and type show ceph drop, and then you can check encapsulation failure, no route, etc., etc. Okay. Then the third one is discard agency. Discard agency means your next hop is discarded by some blocking rule, ACL rule, etc. Then finally you have the punt agency. Punt agency means that you don't have your adjacent table, you don't have your next hop, and directly you are forwarding the packet towards the CPU or towards the route process. If you want, you can go and check show ceph no ceph switched, means they are not ceph switched, rather than they are CPU or the RP switched or RP processed. So according to that, you can go and check these important keywords. So here you can see that you have null urgency, you have drop urgency, you have discard and punt urgency. Finally, when everything is happen and the packet is ready to go, so at that time the rewriting of packet will happen in the egress, or when it is leaving to the switch or the router. So what are the things they will change? They will change the layer 2 destination. Obviously the layer 2 destination will be the next hop MAC address. They will go and change the layer 2 source address. That will be the egress MAC address of that particular interface. They will go and check the TTL, means they will go and decrement the TTL by 1. They will go and check the layer 3 IP checksum. They will go and check layer 2 checksum as well. So these are the things that the switch will check before actually sending the packet to the egress. Finally, ceph will be enabled. Nowadays it is enabled to all the routers, all the switches. But suppose if you want to disable ceph on certain platform, you have option. You can go and type no IP ceph. In some platform, we have to write no IP route cache, or maybe both. Okay, so in this way, we can disable the ceph. So obviously everything will be handled from the CPU or from the routing process in this case. And this is not the recommended way, but sometimes for the sake of troubleshooting or some other reasons, we used to do this. All right, so let's stop here. This is the last session in section 1. We are going to verify the ceph, and we'll see the TCAM as well. Let's discuss or start with the ceph verification. So first of all, what you can do, you can go to the CLI and you can run the command show IP interface VLAN, and show IP interface and the interface name. Suppose if it is a VLAN interface, you can go and give the VLAN and the number. Here you will see that ceph is enabled. So that means this particular interface ceph is enabled. Although you have other important informations as well with this command. So this is very simple and easy to run command, and you'll get a lot of information related to that particular interface. To understand the ceph or to verify the ceph is enabled or not, to run the ceph command, we have show IP ceph command. If we run that command in the next column, you can see that you have receive, attach, and other information. So what does it mean? The first entry here, you can see that you have 000/32. This is nothing but, suppose if you don't have the agency table, if you don't have next hop, then the packet will be pointed to the CPU or the route process. That's the first entry you have. Then suppose you have 192.168.199 dot 0/24 and attached as a next hop. That means that this is your interface. That's why it is showing attached. Then again, you can see that you have 199.0/32. That's the network. This network, and this network is receive. So that means that uh, obviously your network, but the thing here is that this is a reserve entry. Here you can see the more explanation. So if it is dot 0/24, and if it is attached, means it is connected interface. If it's dot 0/32, that means it is a reserve for exact network or network address, and this is used to contain adjacency for packets sent to network address. If the network is not directly connected, in this case there is no adjacency and the entry is marked as a receive. So I think you understand that dot 0/32, this is for network. Then you have dot 1/32, and this is also a reserve entry. This is very much like host route /32 host route. So you have network route, or you have network, you have host route, reserve entries. Then again you have dot 2. Dot 2 means that you may have dot 2 as your neighbor switch. So you are connected with your neighbor switch whose IP is dot 2. And then finally you have 255/32. That is nothing but the broadcast address, and that is also marked as a receive, and this is also a reserve entry. If you want to know detail about CIF, you can go and check show IP CIF, and then the detail will get the detailed explanation. Now finally we have to understand about the TCAM resources. So here you can see that you have forwarding resources. Inside that you have MAC, host route, IGMP routes, LPM route, multicast route, SCT. Now this particular output or this particular reference is belonging to 9300 catalyst switch. In 9300 catalyst switch, you have output like this. Then in the TCAM resources, you can see that you have security ACL, QoS ACL, service ACL. Inside that you have PBR, NetFlow, SPAN, MACSAC, SecCop, Tunnel, Lisp. And even you have the entities for NetFlow as well. Now here you can see the exact partition. So for forwarding resources, we have 32K reserved, the host route 24K, IGMP 8K, longest prefix match 8K, multicast route 8K, SGT 8K. And then again you can see and have a reference for the feature resources for TCAM entries as well. In bottom you have the NetFlow entries 64K ASIC as well. If you want to see this in detail, so you can go and run this command in Catalyst 9K show platform hardware FED fed switch active forward ASIC resource TCAM utilization 0. And here you can see that unicast MAC addresses, max value, use value, IGMP L2 directly or indirectly connected states, and all those informations we have in this particular output. So if you run this output, if you want to see the detail of this from the CLI, you can go and execute this command and get it. Finally, just for the reference, you have the default STM template network interface. You can see the forwarding resources and the TCAM resources and the reserve entries. All right, so let's stop here. In our enterprise core curriculum, section 2 is belonging to virtualization, and the percentage is 10% weightage. Here you can see the topics related to little bit of VMware type of thing. Like you have to learn, understand hypervisor type 1, type 2, virtual machine, virtual switching. What I have done that I'm going to record small 14 videos, and I'll go a little bit beyond whatever there in syllabus just to our knowledge and study purpose. So you'll find it very informative, all these 14 videos that will cover actually not only the Cisco aspect of hypervisor, virtual machine and virtual switching, but the VMware aspect as well. So I'm going to touch both. Then we have 2.2 where we have to learn about VRF, GRE and IPsec tunneling. And then 2.3 we have Lisp and VXLAN. Now for Lisp and VXLAN, I'm going to upload the same video that we have done in section 1 for Lisp and VXLAN. So one video for Lisp and one video for VXLAN. So here 2.3a and b, you'll find some sort of repetition in terms of just section 2.3a and b that we have already done inside section 1. Okay, so this particular section you'll find that it will go over very quickly, and you'll find this section also is very informative, and it will add up your skill set and knowledge base.
What is virtualization? And with help of virtualization technique, what we are going to achieve? Last section we study about the servers and the definition of server and operating system. You think virtualization is a type of emulation where you have fixed hardware. On top of that, you can use some emulated program, and then you can install various operating system. So what is the traditional way to install an operating system? Say I have my laptop, I can go to my laptop. In that laptop, that is my fixed hardware. Inside that laptop, I have fixed CPU, memory, RAM, etc. So I have my laptop, and on top of my laptop I can install operating systems. So for example, I'm using Windows operating system. Now think like this, that you have the hardware. So I have the hardware. On top of that, so let me write here hardware. On top of that, I can install some sort of emulated software. So I can install emulated software. This is actually termed as a hypervisor. So I can install a hypervisor on top of hardware, and now whatever, say for example, RAM, CPU, network interface card, memory, etc. I have, those fixed hardware they can use, and they can think that I have my own RAM, CPU, network card, memory, etc. I can install operating system 1, operating system 2, operating system 3. Obviously there should be some limit that how many operating system you can install. I'll write here N on top of the fixed hardware and the hypervisor. Now if we use this particular emulation or emulated way to install the operating system, actually this is termed as a host. So on top of host, and in this course we are going to study about VMware hypervisor, that is nothing but ESXi. So on top of host I am installing a various guest operating system. So these are nothing but guest operating system, and in this way we can save a tremendous amount of hardware resources, and that's a term, actually something termed as a server virtualization. Now there is difference between the server virtualization and hardware virtualization, and you will understand this thing coming forward or going forward. So for example, when you perfectly use the hardware resources, that is nothing but the server virtualization. And suppose if you know the term, so for example, unified computing system inside Cisco. So you have unified computing system. Inside that you can install so many servers with server profile, etc. That is one of the example of server virtualization. The other example, just now we have seen that you have one big hardware resource, and then you are installing some sort of hypervisor emulated software on that, and then you are installing the guest operating system. So that is the example of server virtualization. When we are talking about network virtualization, now it is everywhere. So this network virtualization is used, say for example, SDN solution. So for example, my SD-WAN is a type of network virtualization, or inside that I have network virtualization. So for example, Cisco application centric infrastructure, VMware NSX, these are using network virtualization concept. Easy example, can I give the easy example? Yes, the easiest one is the VRF, virtual routing forwarding. This is again a type of network virtualization. Okay, so virtualization technique means, now here you can see this is the example of server virtualization. You have, suppose if you have one hardware, one operating system, that is, we are not using any type of virtualization, but we can use in between the hypervisor or the virtualization software that is known as a host. On top of host, we can have n number of operating systems. So here you can see OS, different operating system we are installing, and then on top of that we are installing the applications. So in this way we can reduce the cost, and it is actually quite efficient. Almost all the companies are using that way, this method only. Again, here you can see that you have multiple ESXi, so you may have host 1, host 2, host 3, few of the host having a few of the operating system or guest operating system, few of the host having few of the guest operating system. And suppose if you want to manage entire infrastructure, later on we'll see that how to manage the hypervisors, cluster of host, data center, etc. So we have one VMware popular tool or popular software or suite of software, protocol suite, whatever you tell this is. You have one management layer, that is a vSphere server and vSphere client. And in our lab also we are going to use the vSphere client to manage. So here you can see that you have the server and here you have the client, and with help of one web browser, one application, you can manage the entire big infrastructure. So now you can see the complexity has been reduced, the overall virtualization of hardware has been enhanced, and in this way companies, they can save lot of money. So now what is the hypervisor? The definition of hypervisor is, a hypervisor can be defined as a software that can emulate the hardware like CPU, memory, RAM, and storage, etc. for the installation of guest operating system. In the context of server technology, a hypervisor is essentially a program that allows creation of virtual server. So whatever we have discussed, the same thing. Again, if you want to see this diagram, you can see that you have your server, your hardware, you put your operating system and the application. But in this way, you are not using the virtual way or you are not using the hardware resource efficiently. Instead of that, what you can do, that you have your hardware, put the host or the hypervisor, and on top of that you put operating system and application. So easily you can enhance the performance, reduce the cost, better use of the hardware resources, single plane of management for different guest operating system or application, etc. Again, we have one more diagram here. You can see that you have one big framework. You have fixed hardware, the 86 architecture. You have your virtualized software here, and on top of that virtualized software, you are installing operating system application, operating system application, operating system application. Now all these CPU, RAM, NIC card, disk, whatever you are seeing here in the diagram, actually those are termed as a virtual RAM, virtual memory, virtual NIC, etc. So you have your real CPU, memory, NIC, disk, and on top of that you are using everything as a virtual. And that's the power of the hypervisor we have. In this course, basically we are going to focus on the VMware ESXi, but there are so many good vendors. There are vendors like VMware ESXi is a hypervisor, Microsoft Hyper-V. These are the popular vendors. Then we have the Linux KVM. These three are the topmost trending hypervisor. Apart from that, we have the Red Hat Citrix Zen Server. This is also very popular, Citrix Zen Server. We have Oracle VM. Then we have, we'll see later on that we have two type of hypervisor as well. Then you have Microsoft Windows Virtual PC, Oracle VM VirtualBox, Pallor Desktop for Mac. You have these many vendors who are providing these hypervisor softwares. So I hope you understand that what is the meaning of hypervisor, why we are using the hypervisor, and in long term how we can go and manage them. Let us quickly discuss that what type of hypervisors we have and what is the benefit we have with the hypervisor. So clearly you can see that in case of physical server, you have your hardware, operating system and application. In type 1 type of hypervisor, you have your bare metal, your server. On top of that, you are installing the hypervisor, and then you have the guest operating system and the application. In type 2, you can see that you have the bare metal, or you have the server, operating system, and on top of operating system, you are installing the hypervisor and the operating systems, like the guest operating system and the host operating system. Now, this type 1 is actually popular and it's quite hardware efficient. So this is the preferred hypervisor technology that we have, and most of the places that companies, they are using the server. So you have the hardware, you have the host operating system, that is nothing but the hypervisor, you have guest operating system, and then you have the application. Now doing so, we have benefit. Let me quickly show you the benefits. We can reduce the capital and the operating cost, minimized or eliminated downtime, because in this case you may have redundant host. So suppose if one host go down, still you have your different host and your VM can move to that particular host. So that's why it is redundant, means you have the redundancy in terms of host, in terms of guest operating system, plus the application redundancy. You will see the design and architecture of virtualization with respect to, say, for example, VMware, and you'll find that the downtime is reduced. Obviously, if your operation cost is less, your downtime is less, it will increase the productivity, efficiency, agility, and responsiveness. Faster provisioning of application, yes. We'll see that how easily you can install a guest operating system on top of host. It's very easy. You can do with few clicks. It has greater business continuity and disaster recovery. We have some mechanism, we have some methods that we can do the disaster recovery, and it will simplify the data center management, and that's the key. So when we are simplifying the things with higher efficiency, agility, more productivity with lower cost, that's the goal of all the businesses nowadays. Let us discuss about the virtual machine and try to understand that how we are going to install over the hypervisor. We'll see the installation lab in upcoming session, but here we'll try to understand that how it will be emulated over the hypervisor or over the ESXi. So now what is happening, that we know it is clear up to this point that I have the server on the top of server. So I have server, on top of that I have ESXi or the hypervisor, and on top of that we are going to install the operating system. Those are nothing but guest operating system. Now these guest operating system, whatever actual hardware is there, they are sharing. So inside that guest operating system they have shared, or you can say that they have shared actual physical hardware in terms of virtual CPU, virtual RAM, virtual hard drive, virtual storage, virtual NIC. So everything is virtual. Whatever actual we have, all those emulated virtual hardware they have. That's the first thing. The second thing, and very important thing, we'll see in the upcoming slide, is that everything is in form of folder. Okay, so here you can see I will log into the vSphere client and I'll show you that you'll find that the CPU is virtual CPU, virtual memory, virtual hard disk, everything is virtual here, correct? So I will log into that vSphere client and I'll show you. The next important thing here you can mark or highlight is that everything is in the form of folder. We'll see that. I'll show you that database and the folders inside that. But now let's see the terminology and the extension. So we have .vmdk extension. What is this? This is nothing but your internal storage. So your virtual disk internal storage having extension .vmdk, correct? Obviously VM is for virtual machine disk, that is internal. Then you have the swap memory, that extension is .vswap swp, and that is used for what? So here you can see that is used for virtual memory whenever the process running on the VM reaches the VRAM predefined limit. It's nothing but virtual memory. Virtual memory is swap, vswap. Virtual storage is v.mdk. Then you have the log. Why? So there in the .log extension, all stuffs related to troubleshooting purpose they will stored. So the file store all the information AVM produces for troubleshooting purpose. Then configuration that will be stored inside .vmx. So here you can see .vmdk, .swap, .log, .vms. Why I am explaining this thing? Because when I log into the vSphere client, from there you can go and check these folders and extension. So once you are seeing .vmx, that means it is there for virtual RAM size, VNIC information, and other references for the other files. Then we have non-volatile RAM, that is .nvram extension. Again, the use of non-volatile RAM, here also the use is same, correct? So these are the important extensions we have, but apart from that also you will see further more extensions. I took the snapshot from there from the file system, and here you can see that .nvram, .vmdk, .vmst, vmx, .log, etc. Okay. So what's a virtual machine? Virtual machine is nothing but a machine which is installed on top of hypervisor as a guest operating system. They are using the virtual resources. Actually, they are using the actual resource in terms of virtual resource to run their operating system, or you can not or but and you can install the application on top of operating systems. So let me quickly go and log into the vSphere client. From there I will show you the virtual machine, how it looks like, and the various type of file and folder system. Here I'm inside the vSphere client, and we'll see later on that what are these entries or items inside the dashboard. So think this is a vSphere client dashboard where you have host and cluster, virtual machine template, storage, networking, content libraries, global inventory system, and other stuff. So we'll see that these things later on. At the moment I am focused upon only on the VM virtual machine. So what you can do, you can go and click VM and template. Once you click, you can see a list of VM over the ESXi over the hypervisor. We'll go and check ESXi and their architecture as well later on. But suppose this is the tiny Linux, and I want to see the summary, what type of virtual hardware it has, what type of emulated hardware it has. So here you can see the list of hardware, the VM hardware, the CPU, memory, network card. I will discuss more about network card later on, video card, VMCI, and the other hardware related stuffs. Storage area, memory usage, and CPU info, the IP address and the hypervisor. ESXi 02A corp.local. It is having 32-bit of Linux operating system. The hypervisor is ESXi 5.5. These are the tools that is running. Okay, so this is the hardware. Now if I want to see that their file and folder structure, I can go to the data store. It is attached with this particular data store, and I am very much looking for my tiny Linux file and folder system. Here on the top you can see you have this expand button. If you go and expand that, you can see it is coming up, and now if I go and click to tiny Linux, the folder will open, and inside this particular folder you can see all the extensions that we have discussed: .nvram, vmdk, vmx, log, etc. Correct? So this is the way that we can go and check few of the things inside that. Later on we'll study more and more about this, and we are going to learn each and everything. Let's go through the hypervisor architecture of VMware ESXi. Now in the diagram you can clearly see that there are multiple ways actually to do the management of the hypervisor and the associated guest operating system, etc. So suppose if we have cluster of hosts, say ESXi 1, 2, 3, and I will log into the vSphere client, and I'll show you that from one particular management plane, and that is nothing but a web browser, from single web browser, with help of vSphere server, with help of vSphere client software, you can actually manage, or you are able to manage, the entire VMware infrastructure. That's the uh, overview or the top view of the architecture of the VMware. This is the VMware client, that from where we are going to manage everything. This is the web browser, and here you can see that vSphere web client is a web browser based application that you can use to manage, monitor, and administrate the objects that make up your virtualized data center. And that's the key. See, from one application, I am going to manage the entire virtual data center. And that's the power we have from the VMware. And that's the reason that VMware increased so much in terms of software defined data center. So from a single software, you can manage the entire data center objects spread across the globe. Now here you can see that what are the things that we can do from the vSphere client. We can go and check the health, the status, performance of the objects. We can do the management and the administration commands from the vSphere object. We can create, configure, provision, and delete the vSphere object. So think everything that whatever guest operating systems we have on top of host, or maybe cluster of host, everything can be managed from one application, and that application is nothing but vSphere web client. So vSphere web client, it's very popular in terms of vSphere client. So we are not telling okay vSphere web client, but vSphere client. From vSphere client we are going to manage, monitor, organize, check the health, and there are so many things. Plus we have so many added new application. From there we can actually go and add certain new capabilities inside this management plane, inside this management web application. Correct? So once you log in, how it look like, here you can see that the first, this is the navigation tree or the navigator. Then the second is the main content area. So what's the inventory list, host cluster, VM, storage, networking, content libraries, vRealize orchestrator. So many things we can go and check from here. Then on top you have the search bar. Now my login will be a little bit different because again we are using some new or the latest version of vSphere client. But more or less you can see that you have work in progress, you have alarm, you have recent task, etc. It will look like that. You can go to the home button where you will get the list of all those objects or all those operations that you want to check. Once you click the global inventory list, it will give you the inventory list related to data center, host, cluster, network, storage, virtual network. So all the objects associated with these variants or these operations you will get from the global inventory list. Likewise, I can go to the home. From there I can go to virtual machine. I can go and log to a individual virtual machine. I can go and check their summary, their hardware, their capabilities. You can see I can go and check their hardware things. If I want to add any new vNIC or the NIC card, I can go. You can see 1, 2, 3, all these things. I will show you in the lab as well. So I can go click and I can add one new NIC. Once you add a new NIC, what will happen that you will find that that particular NIC, once you add, you can see the work inside the recent task and the progress also you can go and see. So work in progress, all those things you can go and verify. So let me quickly log into the vSphere client and let me walk you through all those things that just now we have seen. All right, so I logged in inside the vSphere client, and here you can see the task, the navigation, the task here, the main content page, the navigation, the search, all those things. The home button also here in the menu is little bit different than what we have seen, but more or less is the same thing. Now what I can do, I can go click to the menu, I can go to the inventory list. Here you can see the objects related to a resource related to data center, host, cluster, resource pool, data stores, data store cluster, network, virtual distributed switch or port groups, etc. All those things we have here. Here I have the task and the alarm also. So you can see the task, I can see the alarm. And all right, so what I'll do, I'll go to the host. Once I am inside the host, actually I want to go inside the virtual machine. So let me go like this. You have multiple ways. You can click to the menu, you can click VM template, you can reach here, or you can click here, you can go to the global inventory list. Once you are inside the global inventory list, you can see your hosts are there. Once you are inside the host, likewise you can go one by one. Inside host also virtual machine I can go. Here I have the TinyURL. I can go back. That's the power we have with this management. I can tell this is the management plane, or I can tell that this is the management web client URL from where we are going to manage, or from where we are going to give the instruction to all the objects inside the VMware data center. Think like this is a data center. We are managing a data center from a web application. All right, so I want to go to the this Windows client, and let's see what is here inside this particular hypervisor. Remember, when I'm going to global inventory, host is nothing but the hypervisor. Inside this hypervisor, I have the guest operating system. So how many guest operating system you have? You have two guest operating system, Tiny Linux and the Windows. I want to go inside the Windows. Once you are inside the Windows, you can go and click here. You can have the summary. These are the hardwares. I want to add one of the hardware here. So I can go click edit setting. Once we are inside the edit setting, I want to add one network adapter. So let's add one of the network adapter. And here I'm not getting the network adapter in the bottom, but here you can see on top you have the add new device. So this is actually a little bit newer display we have. So you can go click add new device, what you want to add. You want to add the network adapter. Once you click add network adapter, you can see the new adapter option came up. I want to select that. What is your network? So it is asking about which particular distributed switch, and let's add this one. Once I add this, and this is showing the connected as well. Connected on power on, yep. And then what we'll do, simply click OK. And if you click the recent task, here you can see that task is on. Let me show you this 6 millisecond, and this is related to Windows. This is the way that you can actually go and see the recent task. So task is going on with the Windows 10, we have added one of the NIC card. Task is completed. So let me quickly do one more thing. Let me do one more time so you can understand. Add new device, add one more network adapter, and VM reason 1, something like that will add. So I will go here and I'll click browse, VM reason 1. Okay, and see the task queued, completed. Have you seen that? It was queued and now it is completed. So now we have the 2 tasks. Here you can see in the taskbar. So this is the way that see how easily we have added one of the hardware component, one of the networking component. Like that, it's very easy. Just with help of few clicks, you can manage, operate, check the health. You can do each and everything from this particular vSphere client. This particular session is very important because we are going to start virtual machine networking, VM networking, and there are so many nice terms that we should learn and know. So let's start this. Now you can see that what's the problem we have. So once you have the host and once you have the hypervisor, so we know that we have the say for example host, and on top of that we have operating system or the guest operating system. So I have server, host, and the guest operating system. Now problem here is, so let me try to draw here. The problem here is that once you have host and you have operating a guest operating system, the first problem is that which software element should control the physical network adapter drive. So here you have your physical network adapter in the server. Who will control that? The hypervisor or the guest operating system? Obviously hypervisor has to control, but how? That's the first thing. The second thing, that how should communication occur between VM and the external resource. So now in this diagram you can see that you have your VMs and you have your server as well. Now these servers may be connected with switch, so for example L2 or L3 switch, and then you may have a router or you may have external world. So now this VM, how this VM will come, because this VM has their virtual NIC. So the virtual NIC adapter will come to the server and then it will go to the outside. Here we have the diagram. In this diagram you can see clearly that how these VMs will go and communicate to the outside. This is nothing but south to north or north-south traffic. So how this will happen? That's the second point, second challenge. The third challenge is that how the host will communicate to each other. So inside that I may have, so for example 25 VMs. So how this east to west traffic or east to west communication happen, and who has the control over this communication? Correct? So those are the questions. The solution that VMware came with in early 2000, that once you install this particular host, this particular hypervisor, at that time you have network standard switch. So you have host standard switch or vSphere standard switch, VSS. Now once you have the VSS, that means this particular VSS, obviously they have the VNIC from the vSwitch. You can think this as a switch in between. So now this is the switch, and then this switch will control the east to west or north to south or south to north traffic, etc. Now once we have this particular standard switch or the standard switch in terms of vSphere or network standard switch, we'll see the problem. Further, we have some problem. So before going to that particular problem, let's see this particular diagram here. So here clearly we'll see that you have your physical infrastructure, and if I try to analyze this with a switch, you think like you have one switch and here you have north. Just to analyze this particular diagram, here you have south, means here you have server, virtual server. So here you have virtual server,
and here you have, for example, outside world, a router domain. Now you can think like this particular standard virtual switch or virtual standard switch that in Cisco domain we used to study about access port. So access VLAN 10, access VLAN 20, access VLAN 30, access VLAN 40, etc. Then you have one interface that is going towards the router, that is nothing but trunk. So you can think at the moment this trunk is nothing but your uplink going toward the external router domain, and then you have this access port. These access ports belonging to certain VMs, you can think this as a port group. We'll learn about port group in the upcoming section, but you think this as a port group, and you may have certain specific port groups as well, certain specific VM port as well, that may be used for management traffic, that may be used for fault tolerance, that may be used for vMotion. So here you can see that the blue color is nothing but complete VM related ports, and there you have the uplink or your physical interfaces. So here you have port group related to management, port group related to vMotion, maybe port group related to fault tolerance, etc. Then you have port group related to test, port group related to production, and this is over one host. So this is nothing but host 1, and same type of thing. That's a problem here. So if you want to scale up same type of port group with the same name, everything, you have to create across, say for example, if you have 25 hosts, 25 ESXi servers, then you have to go and create the same name throughout, and that's why we have evolved to the distributed virtual switch that we'll discuss later on. But yeah, here you can see the production, here you can see the test, the port group. So the attributes having common properties or common properties inside the same group, a group of common properties, anything you can tell, that's a port group. Then you have the vMotion, you have the management. So here you can see the uplink, and you can see the downlink, or you can see the VM link. So this is nothing but my VM link, and this is nothing but my uplink. Everything is defined inside the port group. Common property, attribute group, or grouping of common property or common task things. So clearly you have, say, VM1, guest operating system 1, guest operating system 2, 3, and 4. 4 VMs. 2 of the VM, they are part of, for example, sales. 2 of the VMs, for example, they are part of HR. So they belong to HR, they belongs to sales. Like that, you can group the ports and you can connect with the virtual machines. All right, so you can analyze like your normal Cisco world also like this, but again now at this time we should understand that virtually how they look like, correct? We should understand that those terms. Now what is the issue we have when we are using the standard switching system? In that you can see that the standard switch is created. So at the moment you will install ESXi, you have your VSS up and running. Now the problem here is each switch on every ESXi must be created and configured individual. So you have to go create, etc. This can be time consuming, although we can do some sort of automation, but it is taking some time to do this. The second thing, one important note when using vSphere standard switch, and some of the high availability features with vCenter in the standard switch must be named. You have this naming convention. So your naming should be common throughout the vSphere domain. Okay, and then also note that the features like input out network IO control, LLDP, network health check, and the backup and restore means some advanced features, they are not supported in the standard switch. So these are the issues we have, and that's why we want to use the distributed virtual switch. We'll see in upcoming sections. In this important section, we are going to study about
a VMware vSphere port group. That's the port group and the standard switch or the vSwitch. So what is port group and what is the significance of the port group? Now in this section we'll understand 100% about the port group and the standard switch. Next section we'll go and perform the lab task. So what is happening? I'll give you one example. Suppose you have one VM virtual machine and it has the VNIC. Now likewise you have other VM, say VM2. This is VM1 and VM2. This has VNIC. Now what you can do that these particular interfaces, virtual NIC, you can connect with a port group. Now again, what is the port group? So port group having common properties. Port group having common policies. So suppose if these VMs related to HR, so you can go and set common properties, common attributes inside the port group, and whenever you are associating different VMs to this particular port group, they are part of same port group. Okay. Now, one interesting thing, suppose if you know ACI, application centric infra inside Cisco ACI, inside that we have concept of endpoint group EPG. So suppose if you create VMM domain and then if you go and create endpoint group, this endpoint group inside ACI is equal to port group as well. Now the concept of endpoint group is also same. You may have common EPG. So for example, EPG related to web or HR or sales, etc. Now those common EPGs, that means here part of port group or the port group is equivalent to endpoint group. Okay, so VMware port group and then Cisco has evaluated their endpoint group. Both are actually same. Common attribute, common properties. You can common properties interfaces or interfaces that you are going to connect with the common properties. Those are nothing but the port group. Right. So what's the definition here? Let's see. So definition of vSwitch connectivity policy, which essentially define how the virtual device handle traffic that belongs to group of VM. In case of VMware vSphere, this policy is called as a port group. So you have one group where you are collecting all the ports and this group having the policy that will be applicable to all the interfaces or all the ports connected inside this group, like that. Alright, so later I will log into the device and I'll show you how you can select or deselect the port group. With respect to this particular image that is here, you can see that I have, this is the vSwitch. I will log in and I'll show you all the properties in 6.7 vSphere client, and you will find the display is a bit different, but these policies or the properties will be the same. We'll see that in the upcoming recording. So they are belonging to, say for example, VLAN 105, then you have the security policy, traffic shaping, and the teaming. If I go back in the slide, so let me go back in the slide. Here you can see that, let me go back one slide back. So here you can see that your vSwitch having security policy, traffic shaping, failover policies, and the VLAN tagged with that. We'll see that. We'll see that you have VM port group belonging to 100, and how we can we'll go and connect all these things. We'll see. So at the moment, just think common properties interfaces grouped inside a group, or common interfaces grouped together with the common policies and properties of the port group. I'll show you. I'll log into the VM, I'll go to the network adapter, and that network adapter I'll connect with the port group. This network adapter is nothing but virtual interface, VNIC. Alright, so we have already discussed that once you have the standard switch, at that time you have issues. What issues you have? That suppose if you have same type of port group, you have to go and create those port group in all the host. So host 1, host 2, host 3. Suppose you have HR here as a standard switch, you have to create here, everywhere. That's the problem. Means you can think like Cisco access switch. So all these VSS standard switches are working as a Cisco access switch, but again all the access switches are going to be connected with the distributed switch, and that's the term that we'll see later on, that what's the use case of the distributed switch. I have complete set of slides for that. We'll discuss inside that. But yeah, for the operational efficiency, to support new features, you need a distributed virtual switch, and inside that also you can go and attach the port groups. So port groups belonging to distributed switch we'll see later on. Alright, in this section mainly we are going to focus inside the standard switch. So how I can go and add the standard switch, I'll go and I'll show you all these steps. Now there are multiple ways to create the standard switch. First of all, we'll go to the host and see that do we have a standard switch already. If not, then we'll go and add that. This is one of the way, but we have multiple ways. I'll show you different ways to go and add the network. So you can right click to the host, you can add the network. Once you go inside that, you'll find that what you want to add: VM kernel, physical network adapter, or virtual machine port group for a standard switch. Now VM kernel, clearly you'll see here that it belongs to vMotion. So vSphere, vMotion, iSCSI, NFS, FCOE, FT, that is the fault tolerance, and virtual SAN. If you are creating the VM kernel, I'll show you all these ports, interfaces, port group, and switch, or the standard switch, in the upcoming recording. Then you may have the physical network adapter. A physical network adapter handles the network traffic to the other host on the network. Then you have the standard switch, and then we have the group for a standard switch. We'll see that. So suppose if you select the third option, then you will get the option either you want the existing standard switch or you have the new standard switch. You can go and add the adapters. So you can click on use adapter, click plus sign, then you will get the option for the physical network adapter. You can use one adapter, two adapter. Once you have one and two adapter, you can use this up and down arrow. You can set the different networking parameters or the properties of the adapters. All these things I will show you. And finally, you can see that this network having label network label, and the VLAN at the moment is untagged VLAN 0. That's it. So this way we can create the standard switch. Now suppose if you want to go and edit something, I'll go and log in and I'll show you that you can edit the vSwitch also. Obviously you select the vSwitch, you have the pencil button here for the edit. You can go and edit. So you can go and change the properties. So for example, if I go and select, it is asking about what's the MTU, what's the security policy, what's the traffic shaping, teaming, and failover. All those things we can go and select one by one. But it's still, just for knowledge purpose, we are studying that, okay, we have the standard switch option or vSwitch option, but later and in the production, generally we are using the distributed virtual switch. So this is also an option we have that we can go and check. Likewise, in the next section, in the lab section, I'll go there and I'll show you that you can go and select the physical adapter as well. And this is the way I'm going to show you. So I will go to the dashboard first. From there, from the dashboard, I will go to the ESXi. Once you go there, you have this networking option. So you can go and check the virtual switch, VM kernel adapters, physical adapters, TCP IP configuration. Once you are inside the physical adapter, here you can see you have the add network options. You can go and check all these things. I will show you one by one, all these operations. Yeah. So what is the takeaway from this particular section is, the takeaway is that what is port group. You should understand what is port group irrespective of virtual switch or a distributed virtual switch. The significance of port group is there, means you are going to connect the interfaces or
VNIC interfaces having common attribute properties with a same type of port group. Once you have the port group, that's the first thing that we study, the port group. Second thing we are going to study, or we have studied so far, or we have seen the slide says, how to create the standard switch. And then again, few of the slides you can see that how you can go and edit the physical adapter as well. So all these things, when we see this in a lab, then we'll understand more than these slides. But still, these slides are just for your reference, that you can go and you can do any type of change. Say for example, if I understand that what's the theory behind all these port groups and the standard switch and the distributed virtual switch, then it's actually very easy and straightforward that we can use the GUI, and inside the GUI we can go and do all sort of changes. Correct? So here it is showing that how we can go and do the load balancing in between the physical adapters, say for example active or active standby, etc. Correct? So let's stop here, and in the next section I'm going to show you the port group and the standard switch, and I will see that how we can edit, create, even if you want we can delete also. This recording session is going to be very small. We are going to understand about a distributed virtual switch. And now suppose if you see this diagram, now this diagram is a little bit confusing, but let's come back to this diagram after this. So now if you see this particular diagram, you can see that the distributed virtual switch having host wide visibility. So all the hosts, they can connect with the distributed virtual switch, although these hosts, they have their own standard switch. This particular own standard switch, you can see that they have VM kernel NIC, they have uplink, these are nothing but the physical link, you can think VM NIC as the uplink, and they have a VNIC, that is VM hosted NIC. So if I draw this diagram, you can understand, say you have guest operating system, this is nothing but the guest OS and hosted over the host. So you may have multiple guests. All these multiple guests, they may be part of this vSwitch. Here you can see, just for an example, it is shown like this, and they may be part of DVS. But what is interesting and important to note here is that you have VM kernel NIC, you have VM NIC, you have VNIC. So you have three different type of NIC. You have NIC for management, you have NIC for uplink, you have NIC for virtual machine. Correct? And the difference here is that this distributed virtual switch has a global visibility. So it will be visible for all the hosts. Now here you can understand this diagram now. So let me change the color of my pen. Now here you can see that you have the physical interfaces here. Now these physical interfaces are nothing but VM NIC. So you have VM NIC 1, VM NIC 2. Here you have VM NIC 1 for this, VM NIC 2 for this particular host. Like that you can think. And you can see the uplink. Now you have the VM. So this particular VM, what is the name? This is nothing but VNIC. So they are VNIC, they are VNIC, VNIC, VNIC. So they are VNIC, they are VNIC. Now you have the distributed virtual switch. Here we have the port group A, B, C, D, etc. Now in the diagram you can clearly see, suppose this A belong to HR. A is a placeholder for HR. So these two VMs, they are belonging to HR group. So these two guest operating system, they are, for example, HR server 1 or HR server 2. Okay? Or generally we are giving this name like web server 1, web server 2. Okay, then you can see that you have VM, and here it's showing like this, but you have VM with multiple VNIC. So here I have VM with two VNIC. They are part of, for example, this is app server 01. Then you can see the other host inside the cluster. So there may be all these hosts are part of DC cluster 01. So other side that VM, they have their VNIC. This guy having the VNIC, they are part of one of the other port group that is nothing but DB. So this VM name is say DB. I'll write DB server 01. This is DB server 02. So now you can understand that you can group all those different VMs as per their attributes to the same type of port groups, and then you can apply certain uh, rules, certain policies over the distributed virtual switch inside the port groups, and those will be applicable to all these endpoints or all these VMs. So here you can see the endpoint is nothing but your virtual machine. So either the traffic is going to east to west, or traffic is going from south to north or north to south. But when it is going outside, it is leaving the uh, cluster, or when it is leaving the vSphere, at that time they are using the physical interfaces. So this is actually the important analogy, and I hope that you understand that. You please pause the recording and then you can check these definition. Whatever we have discussed so far, you'll find the same thing written here. In 2.2 and 2.3, we have to learn about VRF, GRE, IPsec tunneling, Lisp, and VXLAN. So let's start VRF, virtual routing and forwarding. What is the use of VRF? When you're creating virtual routing and forwarding instance, so at that time you can segregate or segment the routing table. So for example, you have one global routing table, and then you may have a routing table for uh, segmented, or for example, you can think like for customer A, you have one, customer B, you have one, customer C, you have one, like that. So it's like segmentation in routing. And what's the use case for that? So you may have business VPN services, network segmentation, data center access, etc. Now, this term that VRF that we are seeing here is actually layer 3 virtualization in terms of routing. But if you see and verify that, do you have any layer 2 virtualization technique? Yes, we have VLAN, virtual LAN, as a layer 2 virtualization technique, where you have, say for example, every VLAN having their own spanning tree instance. Every VLAN has its own MAC forwarding table. Likewise, if you go and check VRF, you'll find that all the VRFs, they have their own CIF, they have their own routing processes. Means most of the routing protocols, they are supporting VRF. And in the diagram, you can see that you have one global table, and then you can have VRF. So what we are doing that we are creating a VRF, and then we are associating that VRF to one of the L3 interface. So that means that one L3 interface, or one interface specifically, can have only one VRF. And later in the lab section, you'll come to know about this. Now we have various techniques related to VRF to provide fast switching or fast pathing. VRF Lite and then MPLS. MPLS is quite a bit popular. So what's the idea behind this is that you may have end-to-end segmentation. So suppose if I have diagram, so here you can see that maybe you have one end where you have VRF A and VRF B, and then you want this segregation, or you want this virtual routing forwarding instance to propagate throughout the network, means end-to-end routing instance or end-to-end segmentation. Now, if you go and use VRF Lite, so in that case, whatever devices you have in between, here you can see, although you have only one switch in between, but it is showing green and red, means you have two VRF, two routing forwarding instance, two inside process or two virtualization inside one box. We can think like that. So the idea here is that if you are using VRF Lite, then you have to go and enable VRF Lite to all the devices. And that's the problem, that VRF Lite, although they are very easy to use, but they are not scalable. So that's the reason we are using MPLS, multi-protocol label switching, where again you are using LDP as a protocol to create the labels and then to exchange the label. Okay, so this is one of the use of the VRF. Although we are going to have, so we are going to perform one lab, and in that lab you will see use of this VRF or front door VRF with IPsec and with the tunneling method. So we have that lab. At this point of time, VRF is a technique where you can create uh, or where you can divide a global routing table into a small independent routing tables, and all these VRFs, they are holding their own forwarding table and the route process. Okay, if you want to propagate it end to end, you can use VRF Lite, but in that case you have to enable VRF Lite and those VRF to all the devices in between. One other thing here, you can see that this VRF, they are supporting encapsulation as well, that is 802.1q. All right, so this is the things related to VRF. We can stop here, and in next section we are going to learn about GRE. Next topic, we have generic routing encapsulation. What's the use of generic routing encapsulation is that you can create the tunnel from one place to other place with the use of GRE. Now, the interesting thing about this GRE is that as long as you have IP reachability and you don't want to expose your intermediate devices, you can create a GRE tunnel from one place to other place. Now, maybe we can think at this point of time, okay, I'm creating the GRE tunnel, so what about security? Now, we can integrate GRE with IPsec as well. We can integrate GRE with IKE as well. So in the lab section, I will show you that not only that will create the tunnel in between two endpoints, so whatever intermediate devices we have, uh, we are going to create tunnel on top of that. The source and destination tunnel will be the endpoints of the source and destinations egress interfaces. In this case, what we are achieving is, first of all, that we don't want to go hop by hop and take the routing decision, although we are directly reaching from one tunnel endpoint to the other tunnel. So we are creating the tunnel. Then for security reason, for security purpose, we can integrate our GRE with IPsec as well. So both the things or both the features we are achieving here, we are doing the routing, we are doing the IPsec as well. Originally it was developed by Cisco, but later on it becomes industry standard. And later on in this session, I'll show you the packet format as well. Here you can see that the usefulness of GR is that you can integrate with IPsec for security reason, first thing. Second thing, one of the great advantage of GRE is that it allows routing of IP packet between private IPv4 network which are separated over public IPv4 internet. So that is also very interesting use case we have, that you can create the GRE in between the private and the public network as well. Okay. Now this GRE also supports encapsulating IPv4 broadcast and multicast traffic. So these are the high level features we have for GRE, how this packet format will look like, taken from the RFC 1701, this GRE header. So here you can see that you have certain flags. Let me quickly go and highlight those flags. So we have flag says C, checksum, route, key, sequence, source route. Uh, then we have this recurrence is something like recursive routes. So it is written in short like recur, but this is for recursive route. Then you have the flags, you have version, what protocol type you have. So for example, if you are using IP packet, then what will be the protocol type? Checksum. Now interesting thing here, so that's the reason I'm highlighting this thing, that this checksum, if you have checksum, this field will become 1. If we have routing, this field will become 1. If we have authentication key, this will become 1. If we have GRE sequence, this field will become 1. Okay. Although I have the explanation in the upcoming slides, so let me quickly show you that. You have the checksum, see routing present, that will become R. So here you can see R and routing means if your flag is 1, that means you have the routing. If you set the key for authentication, then key flag will become 1. If you have the sequence number for the uh, packets, then this S flag will become 1, and here you can see the sequence number for the GRE packets. Correct. Again, if you have a strict source route, then the small s will become 1. For recursion, control and version number, generally they are set to be 0. A protocol type for IP field, it is set to 0800. Means suppose if you are doing the packet capture to understand that what type of packet is it, if you are getting 0800, that means it's GRE IP packet. Then the checksum, then the key and the sequence number, same that we have discussed. All right. So let's finally discuss the packet format, the normal packet or original IP packet, how it look likes, and then when you are doing the GRE encapsulation, how it look like. So once you do the GRE encapsulation, here you can see that your original packet, so you have the your original IP TCP UDP application layer. On top of that, you are putting the GRE header, and then you have the outer IP header. Okay, so now you can think like this, that you have the inner header, and then you have the outer header. Inner header, that's your actual IP and your payload, and the outer header is the encapsulation with GRE with the tunnel IP addresses. All right, so let's stop here, and next section we'll start IPsec. Next topic, we have IP security. Nowadays you will see that almost all the companies, they are using IPsec, because nowadays we are sending our corporate traffic over internet or public media. So at that time we have to take security measures, like we should provide the authentication, confidentiality, integrity, key management, etc. Now the popular term is CIA, C for confidentiality, I for integrity, and A for authentication. Confidentiality means that your data packet is not seen by other. You are sending encrypted packets. So if someone is still, if they are spoofing the packet, or somehow they have those packets or those files, still they are unable, or it's very difficult to decrypt and get the value of that data. Integrity means it is not altered by others. So whatever you are sending, whatever data you are sending, that other side, they are getting the same information. Authentication means you have the valid source, and maybe you have the valid destination as well. Means two parties, they are authenticating and then they are exchanging the data. Now here you can see in the diagram that you may have two types of IPsec. So IPsec actually has two flavor. One is a remote access VPN, where you are putting the VPN client inside the machine, or maybe it's a client or less, or maybe client full, or you are using site to site VPN. Now this site to site or point to point VPN may be point to point, or slash point to multi-point. So either it's a IPsec, or it may be DMVPN, or any other type of advanced IPsec methodology. What's the fundamental behind this? That any case you are doing the encryption, you are doing the authentication of the packets, and then you are sending the data from one place to other place. Now, IPsec is actually a suite of protocol. It's not an individual thing. It is an umbrella where you have so many other things as well. So you have IPsec here, but you have ESP or authentication header. ESP is nothing but encapsulating security payload, and the supporting things we'll see that you have, say for example, phase 1 and phase 2. In phase 1 you have ISA-KEMP policy, say Internet Security Association Key Management Protocol, and phase 2 actually you have IPsec itself, and we are telling it as a transform set policy. You'll see that. So you have phase 1 and phase 2. Inside phase 1 again you have so many things that you can do in transform set, where actually you are moving the data with help of either ESP or authentication header. Here also you can put various security parameters that I'm going to show you in the coming slide. So let me quickly go and show you phase 1. What are the things you can put? Say for example, in phase 1 you can put the encryption, either days, triple days, or AES. Again, AES having bits, say AES, advanced encryption standard, etc., where you have bit either 128 or 192 or 256. uh, Again, tighter the security, tighter way or tighter encryption methodologies we are using. You can use hash MD5. You can use authentication either pre-share, or you can use certificates as well. Then you have the group, Diffie-Hellman group, and inside Diffie-Hellman group, again you have options to choose. All right, so this is phase 1, where exactly you are building the framework, and then you have phase 2, that is the IPsec transform set or IPsec transport, where you are sending the data with the header, so ESP header, and again you are doing the combination of encryption, you are using MD5, HMAC, etc. So phase 1 and phase 2, if you go and check the IPsec theory, you will find that not only you have the phase 1 and phase 2. So suppose you have completed ISA-KEMP, and suppose I have two devices. In between I want to create IPsec tunnel. So you should know, first of all, you should have IP reachability in between these devices. And suppose outside IP here is 111 and here is for example 11.1.1.1. So these outside interface should ping to each other, and over these interfaces you are going to create, or we are going to apply the IPsec policy actually. So phase 2 is IPsec, for example. Then you have to create the ACL. So what type of interesting traffic you have that you want to put inside the IPsec tunnel, or for that you are creating the IPsec tunnel. Then fourth number, that you have to go and create the crypto map. Inside crypto map you can define the ACL, you can define the peer, you can define the transform set, correct? And finally you have to apply over the interface. So these are the steps, but the phase is phase 1 and phase 2. All right, so let's quickly go and check other theoretical aspect. So you have security architecture. Inside security architecture, you have two security header, AH and ESP. We'll go and discuss more about those parameters. Then you have the security association. All the tunnel, they are associated with security parameter index, that is SPI. But this security association having three component: SPI, destination address, and security protocol. Okay, and now this security association have a database of security association, determine IPsec processing for sender, determine IPsec decoding for destination. Essays are not fixed, generated, and customized per flow. So per flow, you will find if you go and check the security association for phase 1 and phase 2, Actually, for phase 2, you can go and check show crypto IPsec essay. We'll see that later on in the lab section. You can check that SPI indexes. Now they can up to 32 bits large, and according to the agreement with the header, what are the things you have inside security association? Inside security association, you have SPI, destination IP, IPsec protocol, either AH or ASP. Correct? So that's about security association. Now let's quickly discuss about AH and ESP, authentication header. It is used for data integrity. Entire packet has not been tampered with authentication. Can trust IP address source. Use MAC to authenticate. Symmetric encryption like this. One-way hash also. They can use anti-reply. They can use integrity check values as well. So what does it mean? Let me quickly show you here in the diagram that this is the actual IPv4 packet. Now you have two mode to use IPsec. You can use transport mode, you can use tunnel mode. Correct? Now transport mode is that you are not changing the IP. So whatever IP you have, you can see the packet is going with the original IP. So what you are doing that you have data, you have TCP field, and then you are putting the authentication header. You are sending with the actual IP. Correct? But in case of tunnel mode, and that's the preferred mode, we should use tunnel mode that cover entire original packet. So here you can see in the diagram, we are covering entire packet. Then we are putting this authentication header, and then we are sending the new IP header. That's the difference, but still you can see that we are doing the authentication for packet. So that's why the need of ESP, encapsulating security payload, that will provide message content confidentiality. uh, Again, this is coming with the encryption, so we are putting extra thing, that is the encryption. Provide limited traffic flow confidentiality, can optionally provide the same authentication header service as AH, support a range of ciphers. So they are robust than AH. They are supporting DIS, triple DIS, RC5, IDEA, CAST, etc. A variant of DIS most common, pad to mid block size for traffic flow. Now here you can see original data, then transport and the tunnel mode. And you can see that we should use this tunnel mode, because when we are using the tunnel mode, then we are changing the IP, means we are protecting the IP as well, because whatever actual payload we have, so here you can see that you have the payload and original IP, and then you have the ESP header. So up to your original IP you are doing the encryption, and up to your ESP you are doing the authentication. Correct? So here we are providing both the features, encryption and authentication, and that's why the ESP is the preferred way that we can do in the phase 2. All right, so remember that we should use the tunnel mode because we want to use uh, gateway to gateway, or we want to encrypt our IP from one gateway to other gateway. We are in the lab section. What we have to do in the lab, you can see the topology diagram here. We have three routers. Router number 2 will work as a transit router. So what I'm going to do here is that I'm going to provide the IP addresses over these physical interfaces, and then router 1 and router 3, I'm going to create first of all normal tunnel with respect to front door VRF. So we are going to learn about VRF, about how to create the tunnel. Once we have the VRF, once we have the tunnel created, once we have the IGP up and running, after that I will go and add the IPsec configuration. So whatever we have studied in these sections, these sections like VRF, GRE and IPsec, everything you can see here in this lab section. So let me go and log into the devices. Alright, so we have three routers here. You can see router number 1, 2 and 3, And let me show you the IP addresses over these interfaces. So I can go here and type show IP interface brief, and you can check that. So what I have done that I have created one interface as per the topology and assign the IP. Let me quickly go to the loopback 0 and assign the IP address there as well. Say for example 10.111.10.10.1/24, and you should give like the subnet mask. Alright, so we have the IP address assigned here over the loopback interface over the physical interface. Let's do the rest of the configuration. So what I want here, first of all, I want to create one VRF. Say name of VRF, I am giving say front door VRF. So front door VRF is the VRF. Now if you go inside that, you can see that you have options that you can define: export, import, route distinguisher, route target, etc. At the moment, what I want to do, that this particular VRF I want to assign to the physical interface. So what physical interface we have here? Now here you can see that we have physical interface gig 0/1, and we have assigned the IP address as well to that interface. Now if you go to gig interface 0/1, and if you assign this, say for example IPVRF forwarding front door VRF, so FVRF, you will see that it will erase the IP address over that interface. So that means you have to give that particular address one more time, correct? And that's the important point we have. Now if I go and check show IP interface brief, and if I check show VRF, so now here you can see that you have the VRF, and we haven't defined any import export RD route distinguisher or any other things on this. All right, so these are very basic and very initial steps that we are doing at this point of time. So what we have done, that we have created the VRF name called front door VRF or FVRF. We have assigned to one of the physical interface. We have one loopback interface as well. Next, what I want to do, that I want to create one tunnel. So let me quickly show you the diagram. We have this topology, and I want to create one tunnel interface as well, and I'll give the IP 192.168. So let's go and create one tunnel, say tunnel 0, and the IP address is 192.168 1.1 255.255.255.0. This is the tunnel source IP actually. Now over this tunnel, what I want to do, that tunnel source is obviously my physical interface. And what's my physical interface? Gig 0/1. And what will be the tunnel destination? Now tunnel destination I haven't assigned yet, but if you go to R3 and if you check the tunnel interface, that is 222.3. That's the tunnel destination for router number 1. So this will be the tunnel destination, and tunnel VRF is front door VRF. That's the name actually. All right. Now once I created this tunnel, I can go and check the tunnel configuration. This is the tunnel configuration, and then you can go and check the tunnel interface. Now if you go here and check the tunnel interface, the loopback is tunnel, and tunnel protocol is, here you can see that protocol is GRE and transport is IP. So by default, whenever you are creating the tunnel, that will be GRE. Okay. All right, so once we have the interface configured, once we have the tunnel configured, then we should give the routing as well. For this routing protocol, I'm going to use, say for example, EIGRP in this case. So I'll go and start EIGRP. What network we have? We have one network, say 10.10.10.0, and I can give the wildcard like this. Then I have other network 1.0, and I'll give the wildcard like this. I'll do not assembly. So one last thing I have to do, that for front door VRF, I should create a route for that as well. So I'll create one static route for my front door VRF, FVRF, and that is default route pointing towards the gateway. Okay, so here you can see section IP route, or I can go and do include IP route just to check the IP route command, and then we can go and check the GRP as well, and then we can go and check the tunnel 0 configuration as well. So these are the configuration that we have done for router number 1, that is source of the tunnel. Likewise, I'll go and configure the router 2, that is going to become the transit. So here if I come and if I check show IP interface brief, this is a transit router and we have already assigned the IP addresses, so no need to do any further things to that. Now we'll go to router number 3 and we can do the same thing that we have done for router number 1. So here we can follow the process or follow the steps. IPVRF is the name, and then obviously I'll go to 0/1, and then I will forward to front VRF. Then I'll go and assign the IP one more time, and we can verify that. So this is the step number 1. Then in step number 2, that I want to create a tunnel. So interface tunnel 0, IP address for this tunnel as per our diagram. Say IP address is 192.168.1.3.255.255.255.0. Now once we are inside the tunnel, I can give tunnel source as gig 0/1. Tunnel destination will be 1111, correct? That is router number 1 physical interface. And then finally, tunnel VRF is FVRF, and we are very much done. So this is step number 2. I can go and check interface tunnel 0, and here you can see this configuration. Likewise, here you can see the configuration. So we have almost same identical configuration matching. I'll quickly go and enable the EIGRP process. We know the network here. So what network we have? I have network, say 192.168.1.0.000.255. That is one network. And other network is that I want to give this loopback, that is 30.30.30.0. If you go to router number 1, here you can see that you're advertising your loopback, you're advertising your tunnel. All right, so we are very much done, and next thing we have to do that we should create one default route for the transit router. So that is IP route VRF, front door VRF 000, and what will be the IP for these interface? That is this IP. All right, so we have created this tunnel. I can see that tunnel is up and we are getting the agency as well. So if we go and check show IP EIGRP neighbors, show IP route, and we are getting the routes. Likewise, if I go here and check show IP route EIGRP1, you can see that they are receiving the route. So this is the very first basic step that we are doing here. We are enabling the VRF, and then we are checking the GRE as well. So you can go and check show interface channel, and here you can see that your encapsulation is GRE. This point you can see the source and destination as well. So let's stop here, and in the next section I'll go and add the IPsec configuration in this. We can continue our lab, and now we can add the IPsec profiles in this. So let's start with router number 1. What I can do here, first of all, I'll go and create the keyring. So here you can see that you have crypto, and you have this keyring. I can give the name for this as well. So GRE IPsec is the name, and VRF is front VRF. Okay. What's the key you want to give? So pre-share key, and the address for the destination is so 2.2.2.3, and the key I will use, for example, Cisco. Okay, great. Now once we have this keyring, then I'll go and create the ASICemp policy. So let's go and create that. All right, it's a bit slow. We can wait here. All right, it's back. So now what we can do, that we can go and create the ASICemp policy. So for example, 10, and then I can go and use the authentication as pre-share. Okay. Now, once we have the keyring, once we have the ASICemp policy, next I want to create the profile for the ASICemp. So let's create the crypto ASICemp profile, and the name of profile I want to give, say, GRE IPsec. Okay. So a profile is deemed incomplete until it's matched the identity statement. So we'll go here inside the profile and we'll give the keyring. So keyring is GRE IPsec, and then match identity for the address 222.3, that's the destination address, and then 255.255.255 for front door VRF. So what we have done so far, let me quickly show you that we have created ASICemp configuration, and we have created the keyring as well. So better I will use crypto. From crypto, you can see everything that we have created. So first of all, we have created this keyring, then we have created ASICemp policy, and then we have created ASICemp profile. Correct. Now these commands we can copy and then we can reuse inside R3 as well, and we can change the address and we can use it. So let's complete. So now we have the SICAMP policy. Next, we know that we should create the transform set. So we can go to crypto IPsec transform set, and this also I can give the name as GRE IPsec, but we can give different name as per the standard. I can go and use say ESP, and what options we have, say for example DES, and we can give the mode as well. At the moment I'll use mode as a transport. Now we have phase 1 configure. Now we have phase 2 configure. Finally I'll go and create the profile for IPsec as well, because this profile I'm going to map inside the tunnel. So crypto IPsec profile, and name also I'll give the same, GRE IPsec. What are the things we can set here? So transform set is GRE IPsec, and then the SICAMP profile is GRE IPsec. We are very much done. Let's quickly check the configuration, show run, and then section crypto, because everything is starting with crypto. Here it is. So we have created the keyring policy, then SICAMP profile, then transform set profile, and then obviously the IPsec transform set profile. So this is the configuration. Finally, what we need to do here is that we should go to interface tunnel 0, and inside interface tunnel 0 we can go and match this. So I can go here, use tunnel protection. Once I'm inside tunnel protection, then I can go and apply it. Tunnel protection, and then you can see IPsec profile, that is GRE IPsec. Okay. So I'm not using shared at this point of time because this will solve my purpose. Great. So what we can do here, that now we can go and use this section crypto. What it is telling this log here, you can see that you have this GRE. You are sending some encrypted packet, but you are not receiving, etc. Because one side you have uh, created this configuration, but other side you haven't done anything. So what we'll do here, we'll go and open the notepad, and we know that other side the IP will be 1111, rest everything will be the same, correct? So we'll copy and paste this configuration to here, and we'll go to interface tunnel 0, and here also we'll run this tunnel protection IPsec profile GRE IPsec. Alright, so this is the way that we can go and do the configuration. Now you can see this, we are getting the up message. So we can stop here, and next section we can do, or we can run few of the verification commands. Let us run a few of the verification command. So first of all, I want to ping from here to the source or to the other side of the tunnel, and behind the tunnel we have some loopback. So I want to ping that loopback address. My source is loopback 0 itself, and now you can see that I'm able to ping from this source to this destination and vice versa. Let's go and check the phase 1 security association, and you can see that we have QM ideal, that's correct. And now I want to check the phase 2 that is the IPsec SA. Now here you can see that you have tunnel. Actually, you have two tunnel, inbound and outbound. First of all, you can see that you have the local ident, you have the remote ident. So you have this source and you have this destination. Actually, the front door VRF IP addresses it is showing. We have some allow flags. Origin in is ACL. Now here you can see that in cap and decap packets almost same number of in cap and decap. That means the transmission is happening properly from both the ends. You can see this local endpoint and the remote endpoint. Few of the policy we haven't set here, so that's why it is showing none. PFS is showing no, etc. Now we have learned about the SPI index. Here you can see that you have the inbound SPI index, and then you can see that you have the outbound SPI index as well. Correct? Now here also everything is okay and correct. The final output that you want to check is the crypto session, and here you can see the port number and the protocol number. Everything is working up and fine. So this is the minimum basic configuration that once you do the configuration you can go and verify from the show command. The best thing or the best command to verify all of your crypto configuration is show run section crypto. So if you run this command, you'll get whatever crypto related command that we have run, it will show. Okay. So this is the baseline verification that we can do once we complete our lab section. What I'm going to do here that I'm going to save the configuration. Topology obviously will get with the slides. This configuration I will put there in the slide as well. So if you want to practice, you can practice from your side. Either you can use GNS or you can use Virl. In my case, I am using Virl. Previous session we have discussed about a Lisp, that is the control plane for DNA. The data plane for DNA is a VXLAN, and let's learn about VXLAN. So now here you can see the header formatted. That before going that, let's try to understand that what type of headers information we have inside VXLAN and Lisp. So normal IP packet will be looking like this. You have the payload, you have IP, you have Ethernet. But if you go and check Lisp, Lisp is actually the L3 overlay, but VXLAN is L2 plus L3, means it supports both L2 and L3. Uh, Lisp is referred as, you can see here, this is something IP in IP, and VXLAN you can think as a UDP in IP. So you have IP packet, even you have Ethernet packet, and then you have the UDP encapsulation, and then you have the outer header format as well. We have the document, we have the slide actually that is referring some of the points. I'll come back there as well. So MAC in IP, but you can think VXLAN as a UDP in IP as well. And here you can see Lisp as IP in IP. Okay, so VXLAN as per Cisco, you can refer as MAC in IP, and Lisp you can refer as IP in IP. All right, so here you can see that you have the header format for VXLAN. You have your IP and payload up to this point. Then you have VXLAN encapsulation. Then you have you have the UDP encapsulation, and then you have IP and Ethernet. These are the outer header, and then these are the inner header. Now, knowing up to this point, let me go back to the actual header format, and we have those in detail as well. Let's try to understand this first, and then I'll go and cover the next header format as well. So now here you can see that you have the actual payload, then you have the IP header, you have MAC header, you have VXLAN header, you have UDP, where you have the destination port as 4789. Then you have outer IP header and the outer MAC. Now in outer IP header, it's important that you have the source IP as a source RLOC related to Lisp, and then the destination is destination RLOC related to Lisp. That is the fabric outbound and inbound IP addresses. The rest of the things are very much similar that how the VXLAN used to work. In UDP, you will see that your source port is the hash of L2, L3, L4 headers. Your destination port is UDP 4789. Okay. Now, if you go and check the VXLAN header, you'll find that you have the segment ID that is going to integrate with ICE security group tagging. So you have 64K possible segments. Then you have this VNID, VNID, and this is actually 16 million. And actually 16 million is not supported, but yeah, it's very much and more than the VLAN ID. VLAN is actually we know that we have only 4K VLAN, and that's the restriction we want to overcome inside VXLAN, that we have 16 million of possible VLAN if we are using L2 VXLAN, VRF if we are using L3 VXLAN. Okay. Although this diagram is very busy, you have to take your time and at least draw the VXLAN, UDP, and outer IP header. These three are important. Now VXLAN, once you understand VXLAN, these are the fixed thing. Then UDP header, it's easy. Source will be the hash value, so you can do the ECMP. Destination will be fixed 4789, and then the outer IP addresses are the Lisp-based inner and outer IP. That is the RLOC, correct? Now we have one more diagram here. Let's try to understand parallelly Lisp header and the VXLAN header. Lisp, we know that IP in IP, so that's why you have the inner header as a IP. Then you have the Lisp header. You have one field here, that is the instance ID. This instance ID is the criteria for the virtualization. So if you want to do a Lisp virtualization, you have to put instance ID apart from 0. 0 will be the default. By default, all the configuration has 0 as a Lisp ID, but for different VRF, we can put different instance ID. Then you have the UDP destination port and source that will be randomly generated. Then you have the outer header. Outer header, we know that what will be the outer header for the Lisp packet. So you have the destination routing locator, you have the source routing locator. UDP protocol number is 17, like that. So we have referred the diagram, and here you can see the same thing. You have inner header, then you have Lisp header, and then you have the outer header, correct? Like that. Better you refer this rather than this. All right. Now, when coming to VXLAN, here you can see that you have inner header. So you have the payload here, and you have the Ethernet as well. Then obviously you should have IP as well. So once you have the IP, then you have the VXLAN. Here you have the VNID or VNI. You have L2 and L3 VNID. You have some reserve bit as well. Then you have the UDP encapsulation here, where the destination port is 4789. Source will be the hash of different values. Then you have the source routing locator and destination routing locator. And then you have this is actually your outer header. So you have outer header, your UDP, your VXLAN, your Ethernet, your payload, and optional things. Okay. So this is the way that you can understand VXLAN, and actually we have covered the detailed comparison of VXLAN and the packet format. Now we have one more slide here, that is that how this data plane is working. Obviously it will do the decapsulation and encapsulation at the edge point or the edge node. So if you have two edge node inside the fabric, they will do the encapsulation and decapsulation. So if I can draw and explain here. I have one device here as edge, and then I have EID. I have other device as a edge, suppose edge 2 and edge 1, and then I have EID. When the packet will come, it will resolve the Lisp. It will go and contact with the control device or MSMR, where it should know that how to reach to the destination. Then the dynamic VXLAN tunnel will form. In that dynamics VXLAN tunnel, the source and destination outer header will be the RLock source and destination IP. Correct? So that's the thing written here. The underlay address, advertisement, and mapping. This is your underlay, and this is your overlay or fabric. Correct? So this thing will happen. Then automatic tunnel, so your VXLAN tunnel will form automatically. Then frame decapsulation between routing locators. Obviously encapsulation and decapsulation will happen. So once you are sending the frame with VXLAN, it will do the encapsulation, and once it will reach to the destination over the tunnel, he will do the decap. So incap and decap will happen. Lisp is IP in IP, VXLAN is MAC in IP, and then we have some of the Lisp control events as well. So this was the detailed explanation of VXLAN, and I hope you understand the format, the encapsulation, the packet format, and how it is working. So in next section, we'll go and learn that what type of products supported inside DNA, although there are links where you can go and check the list of product, and there's a huge number of products that has been supported inside ST Access or DNA. We have very important topic now is the Lisp. Lisp is the control mechanism or control protocol for DNA. This is nothing but the locator ID separation protocol, means how you can differentiate or how you can separate the identity and location. We'll see that what is the mechanism and what are the uh, technical definitions or technology behind the Lisp. Correct? So let's try to understand this fabric and this DNA piece step by step. Now here in the diagram, you can see that you have edge devices. These are actually the edge devices. We have three components. You have edge, then you have border, then you have control. One by one, we'll go and discuss all. But these edge devices that you are seeing here, actually the endpoint identities are connected with them. Here you can see EID, EID. So this edge device specification is that one portion is connected with EID, but one portion is inside the fabric, correct? Now inside the fabric where you are running the Lisp protocol as a control mechanism, now this Lisp protocol has a R locator, means router locator, and then inside that you have one database. So that means that whatever edge devices you have, they will map to the RLock, and that EID to RLock mapping will be stored inside the database. And that's the case we have. It is doing like this. Now we have the other components as well. So let's try to understand all the terminology, and then I'll come back and connect all those pieces. Now, if you use Lisp, what will happen? Say you are storing or you are preserving the identity. So suppose if you move the system from one place to other place, before Lisp, they have to change their identity. But if you are using Lisp, you can see they are preserving the identity. So that's why they are supporting the mobility feature. And this mobility feature is huge in the campus area network because all the time users are moving from one place to other place. Now, how is Lisp used in the campus fabric? Let's try to understand this. In campus fabric, you have the a controller router, you can say at this point of time. So you have one controller router, and then you have the edge devices that is connected with EID. We know that they will use R locator, and here you have the database who will store EID to R locator. Now what will happen? This EID has the database /34 for IPv4, /128 for IPv6 or MAC addresses. So at the moment you're part of Fabric or you want to become the member of Fabric, you will send all the prefixes to the controllers or to the control plane. Now this controller, what he will do, that he have his database. Next time, suppose this is A and this is B. Next time, suppose the B wants to communicate with A, and he don't know how to reach to A, he will go and contact the controller. Hey controller, I want to reach to A. Now since controller know that this request is for A, why? Because he has the EID to R locator information, so he can tell, okay, this is the way that you can reach, and later on they can go and communicate directly. Okay, so it is working, you can think at this point of time as a proxy, but that's true. Why it is working in this way and what's the benefit we have, I will show in the next slide. But this is the mechanism behind the scene, correct? And you can read out these points as well. Now here you can see that you have the edge node or edge device. The Lisp term is Lisp tunnel router. So these are the Lisp tunnel router because they are going to do the mapping for EID to R locator. And again, this term is also huge. So provide Anycast L3 gateway for connected endpoints. So whatever EID to R locator, obviously R locator will be fixed for the EID, but they are going to check who is the group to near, who is the nearby endpoint, and then according to that, he has to store the information. Again, in the big fabric, you have or you should have multiple control nodes. Now, those control nodes, which particular group of endpoint is near to that control node, so there this Anycast will come into the picture, correct? All right, so you have the EID. They have to register to the control plane or the controller, and then the controller will have the database for EID to the allocator. Then again, you have the border node as well, and they are termed as a Lisp proxy tunnel router. So you have Lisp tunnel router and then you have Lisp proxy tunnel router. Why? Because if you want to go to Lisp to non-Lisp domain, or who will be your entry or exit point, so these border nodes will work like that. So here you can see the nodes. Connects traditional L3 network, that means non-Lisp domain if you want to go, where two domain exchange endpoint reachability and policy information. They can have VRF and security tagging group or group tagging. We'll see that these things are possible when we are talking about Lisp. The two very important feature of Lisp is one is the mobility, other one is the virtualization, or they are supporting VRF. Okay, provides a domain exit point for all the uh, edge nodes. So that's the usefulness of the border. So now we have three terms. We have edge, we have border, and we have control. Border is the entry point, the exit point for all the edge devices. Plus, if you want to communicate from Lisp to non-Lisp domain, this border will be getting used. This control plane or the controller device is to have the database for EID to R locator information, correct? And these are the terms actually. Apart from that, there is one other term as well, that uh, transient devices. So in between, if we have non-Lisp devices, so that is also supported. So it is not mandatory that inside the fabric you are running Lisp to each and every devices. All right, so we reached or we understand up to this point. Let's understand few more slides. What benefit we have, and that's the main thing. So I'm going to use Lisp, then what benefit that Lisp will provide to me. Now here you can see the benefit. First of all, mobility and then the virtualization. Both features are there, means devices can move from one place to other place, but they still have their actual identity. Why? Because they are responsible to manage their identity. That's it. They are not there to manage the entire topology table or entire database, because for that you have other devices in a network. Apart from that, these Lisp, they are fully supporting virtualization. So for virtualization, there are some code for VRF and all, but they are fully supporting virtualization. Now, before moving further, let's try to understand about this location and identity term. You have location and identity. You have the identity of yourself. So that is nothing but the endpoint route. So you have endpoint route, and then you have this color red is topology route. Now you can see in a big network, the topology route will be very big. And why you want to have the topology route and unnecessarily you are utilizing your tables, your CPU and processing, etc. Rather than you offload this. You offload this topology route to some database. Whenever you want to need it, just contact to the database and that database will provide you that information. So rather than adding or rather than putting extra burden to all the devices, you can put that in a centralized location like this. So now you can see that the efficient utilization of the CPU, they are not overloaded because you have you're storing the topology table to the central location, and whenever they need, they will go contact there, they will get the answer and then they can communicate directly. That's the overall idea. So now you can see the scalability feature, the better utilization of resource feature, and they are supporting mobility and they are supporting virtualization as well. So routing scalability is there, mobility is there, and virtualization is there. With help of Lisp, we can achieve all these target. Finally, we have the Lisp mobility in the campus fabric. We have the host pool. Now, this is nothing but you are preserving the VLAN and the IP subnet. So now you are creating the VRF, for example. So VRF A, VRF B, VRF C. Later, we'll go and study about VN, virtual network, associated with VRF. So different network or instances you can create, and once you have those instances or network, they are associated with VLAN ID. Everything will happen dynamically here, and they will manage the network. So you have the resource, but you are doing sort of virtualization in terms of VLAN and subnet. You are preserving the VLAN and subnet, and then you are doing the communication. That term is host pool. So host pool is based on IP, subnet, and VLAN ID. Okay. Again, these are the features we have inside the Lisp, but the core fundamental is the same. That means that you have to register somewhere. Where you are registering, he has the information of all the topology inside the fabric. You have local responsibility. Now you can think like this: you have local responsibility, and someone has the global responsibility for all the devices who has their own individual responsibility. Whenever one responsibility wants to communicate with other responsibility or who has the responsibility, so at that time they will consult the global member and he will provide the path. Obviously this will not having the lag, this will be very faster. Okay. Finally, the Lisp is supporting the virtual networking or VRF, and you can by default that will be VRF 0, but we have option, we can go and configure VRF 1 2 3 4 etc etc. So different fabrics we can create, or you can think like different overlay you can create inside the fabric. This overlay is nothing but the virtual network. This virtual network is nothing but a tenant itself. So tenant, overlay, virtual network, all together they are the same term or the same thing. Alright, so final thing is that how Lisp is working. Already we have discussed that you have one centralized database. So whenever your edge device who has the uh, identifier or edge endpoint identifier, they will go and register to the control plane or the controller, or basically we are telling this as a control router. Sometimes it is referred as a MSMR, map server map resolver. So bottom line is that once you are inside the fabric with help of rlock, so EID to rlock mapping is happening, and then you have the entire database is stored at this guy. You can think this as DNS as well. So you may have local DNS, you may have global DNS, like that you can think. And whenever you require, you are resolving like DNS. So these guys will resolve like DNS. They will send their query, and finally they will get the response, and then they will do the communication. So very much like how the DNS is working, the same way the Lisp is working. If you want to learn more about this, you can go and check these links. Plus, you can go and check, there are so many good documents in Cisco Live as well that you can go and refer.